directed after welcome address. There is a bouquet. You start maybe later.
Good morning, everyone. A very warm welcome to all the speakers, guest faculties, faculty members of IIT Kharagpur, students, and participants joining us today. On behalf of AI Summit, organized by Department of Computer Science and Engineering and Department of Artificial Intelligence at IIT Kharagpur, it gives me immense pleasure to welcome you to this special program on Workshop on AI for Science and Technology. To formally commence today's program, I now invite our respected Director IIT Kharagpur, Suman Chakraborty, to deliver the welcome address.
Distinguished Chief Guest Debjanidhi, distinguished speakers, our respected faculty members, including the head Computer Science and Engineering, Niloyda, and Plavon, the head AI, and several other dignitaries who have come from various places, and most importantly, my dear students. Today, we have assembled for one very unique event, which is a particular, what I would say, specially curated event, pre-summit event of the AI Impact Summit 2026, which is going to happen in the next month in New Delhi. And this is a pre-summit event, and every pre-summit event has a focus. And the focus of this particular pre-summit event is AI for Science and Technology. Now, I was just going through the AI Impact Summit, its mandates and so on, and it has been convened, or rather conceptualized. It will happen, of course, but it has been conceptualized by the Government of India. And I was looking for the most important keyword in that announcement, and according to me, the most important keyword is impact. So it therefore is not looking for any kind of development which we can say broadly innovation. It is important, but in the AI context, it is not just models, metrics, or even if you are thinking of the importance in the context of startups, not just market evaluation or market variation. Something which is measurable, inclusive, and sustainable. And very importantly, guided by people, planet, and progress. So in that way, this is not just another summit. This is perhaps one of the natural platforms by which the Vikshit Bharat realization dreamed by all of us in synchrony with our Honorable Prime Minister is going to happen. The pre-summit workshop on AI for Science and Technology at IIT Kharagpur, therefore, I am not really looking into it just as a conference, but a strategic intervention where the foundational science, it meets the natural responsibility, and algorithms are tested not just for accuracy, which people will anyway do for their academic work and research, but for consequence, what they are for. And science and technology is one of the key aspects which drives IIT's growth and of course the national development. So AI for science, or if we combine science and technology together, from acceleration to transformation. The next scientific revolution, what we all imagine, everyone is saying that the next scientific revolution will be driven by AI. It has already happened. I do not think that that's the revolution we are talking about. But it is not AI as a tool, but AI as a scientific collaborator, which is still missing. People think AI is something else and foundational science something else, and AI used for fundamental science itself, it is based on a premise of an idea as if AI is not science. So, those of us who are from different areas of subjects, we say that when people talk a lot of a subject and give science a name, that means they have an apprehension that that is not science. Some people say that people have apprehension that social science is not science, and that is why they say science. In our mechanical department, people say manufacturing science because some people think that manufacturing is not science. So the whole idea is that if we believe from inside that it is science, we don't have to really tell whether it's science or not. Now, AI, those of us who have been following the subject not from the very beginning, but as it has encroached into the research works of different other fields, AI initially was confined on recognizing certain patterns. I mean, people in different areas of science and technology were using that. And typically pattern recognition in data-rich domains has been one of the areas where people extensively have been using AI, although they may not have been knowing the details or nuances of AI. Now, what is most important for this pre-summit event is that from that, AI is now reshaping the way in which the science is studied in those subjects itself, and that is a big scientific transformation. Let me give some examples. In material science, AI is compressing decades of discovery into months. I mean, for materials discovery, people have been waiting for years and years. Learning structure, property, performance, relationships beyond the traditional way by which the researchers in the field wanted to do. In healthcare and life sciences, the foundation models which were unheard of several years back, these foundation models are bringing out several hidden manifolds in genomics, proteomics, and even physiological data, and opening the doors to predictive, preventive, and very, very personalized medicine, which in this way it was always conceptualized but not easy for a doctor to implement. But with AI based tools, this kind of personalization of healthcare is now possible. I mean, whether it is scalable or not is a different aspect. Fluid mechanics, climate science, and earth systems. AI is enabling real-time surrogate modeling of multi-scale, multi-physics phenomena. I am myself a researcher in those domains, so I keep on seeing that the kinds of flow patterns which really needed the resolution of very fine resolution to do the computations, and for a real life scenario it was impossible to solve those problems. And these were therefore at some point of time computationally not tractable at all. But now those are definitely within the realm of analysis. In semiconductors, energy systems, advanced manufacturing, AI is closing the loop between design, fabrication, testing, and optimization. And this is very much like design and manufacturing was not very seriously connected to an extent that there was always a gap between what is being fabricated and what's the basic design principle is talking about. That gap is significantly bridged with the help of AI. But these are something, these are not unknown. These are known, people are working on it, and these may give an idea as if AI's only job is speeding up the known science. That what science we know, simply we are speeding up the implementation to solve problems using that science. But the most important thing is AI is now being at least trialed to reveal some hidden or unknown science. It is not an easy job. I know in some of my talks, I give one example that we have all heard of that Galileo's famous leaning tower experiment in Pisa. So that object which is falling from that leaning tower, the time that it takes to reach the ground, that later on, much later on, when the mathematical theories came up, it indicated that h is scaling with t square, and that doesn't depend on many other things. So as if in the history books or in the junior level science books, which are mostly like history books, it is demonstrated as if this was a great event and Galileo was doing these experiments, and from that experiments this was perceived. Now what was perceived is a basic science, and whether Galileo did those experiments or not, actually nobody knows, because there is a lot of controversy if someone reads these articles. But the spirit of this is that when the experiments were done, very cleverly the role of the friction provided by air or the air drag force was isolated. If not isolated, you get millions of data, it will never be fitted to h equal to half gt square. It will not be. But even if it fits to, the science will actually tell what is the scale. So how do you bring up that science if people do not know about mechanics? Just those collection of data, and as if the basic laws of mechanics rediscovered through data. I imagine that this is one of the toughest problems to imagine, and I would request the AI fraternity to take some of these very classical physical problems and pretend to be ignorant about the physics and try to see whether the physics can be retrieved from data. It is, if that can be done, then many of such hidden physics can be uncovered. Now the Indian imperative, why AI for science or AI for science and technology matters nationally. We are all there for, of course, studying science and technology, but the most important idealization that should come in everybody's mind, at least sitting here, is nation first. So in India, what we would imagine that it is not just like a luxury that people are doing AI because AI is a fashion and like that, but it is a strategic necessity. And why it is a strategic necessity? Data is abundant in India. So whenever we go and interact with our foreign collaborators, we find that they get excited if we can excite them about the huge wide variety of data which is available in any problem, be it healthcare, be it rural development, water, energy crisis, huge data, but very heterogeneous data. And resources are constrained, but our aspirations are global. So with resource constraint and global aspiration, that gap where resources are not able to take us to a limit, can AI take it to a limit? Like I work on certain fields of medical diagnostics where we know that if you have a very powerful microscope and a very powerful camera and all those things, you can do wonders. But if you go to the remote village, that kind of microscope is not scalable. So can you use your smartphone as the simple, inevitable gadget that is now there with everyone and augment its capability with certain simple optics, which just like a do-it-yourself assembly you can do on a school level platform, and still get a kind of resolution which can screen out certain important diseases. So this is a fundamental scientific problem. Problems are therefore complex, interconnected and uniquely Indian, and that is where it is so emphatic. I still remember that in one of the Government of India Ministry of Education driven programs known as Imprint, introduced by our Honorable Prime Minister, and when it was launched in Rashtrapati Bhavan, I was fortunate to be there as one of the domain coordinators, national coordinators in healthcare. So there our Honorable Prime Minister Sri Narendra Modi made one very interesting remark. He was talking about India's specific India-centric perspective of science and technology. And one particular comment I still remember, and I think very much befitting to such cause, is science is universal but technology must be local. So what is very important for us to realize that how can we use whatever is the scientific know-how for a technology which is imperative for our national cause, and if it is imperative for our national cause, it will also be imperative for global cause, because not just India, there are many other places who are actually looking for similar technologies. Now this is where AI in the present juncture is immensely useful. AI would allow us the leapfrog legacy research pathways, reducing the dependence on prohibitively expensive infrastructure, experimental or whatever form of infrastructure, because you can try to make it up with your data driven perspective. Democratize access to high-end scientific capability, and this in India is very much important, enabling tier 2 and tier 3 institutions to participate in frontier research. I can still remember when I first started my microfluidics research in India. In those days it was not common, and in I have always had a passion of going to tier 2, tier 3 institutes and even schools to talk about what we are doing. And in some of those places I got a feedback that, well, what you are doing is very important and we can understand it is important, but we cannot afford to build up a lab like what you have done in IIT. It is impossible. But we have the scientific curiosity, and possibly they were not telling, but we understand they have equal talent as ours. But then this resource prohibition is taking them backwards. Now of course you can develop frugal technologies to make up for that, but it will not make up the entire thing, maybe 30–40%. It can go up to 80% makeup at least if you combine that with AI, and that is where it is going to create a big dent, and translating science to scale, ensuring that breakthroughs do not remain trapped in labs but reach the farms, factories, hospitals and households. And this scalability is something which can be brought without, perhaps it can't be brought without the intervention of AI. This aligns this pre-summit event directly with the theme of the main summit: human capital, AI native scientists and engineers. Developing this human capital is very important. Inclusion and social empowerment, science that serves the last mile, safe and trusted AI, physics informed, constraint aware and verifiable models, resilience and efficiency, anticipatory science for climate, health, infrastructure, some of the main issues. And these are very much India centric, like we talk about climate change. Climate change, what is happening in the Indian context is very much different from many of the climate changes which are flooding the research papers globally. The democratization of AI resources, open models, open data, open science. This is one of the things which can actually democratize science to the next tiers. Economic growth and social good, deep tech anchored in societal need. So moving beyond black boxes, we need to achieve new technical frontiers. These cannot be done without major advances in the technical frontiers. India does not need any more some black box AI and superficially apply that to scientific data. The frontier lies in several advancements in different scientific directions. I am mentioning a few: physics informed and biology aware learning, hybrid models that couple the governing equations with a data driven interface, and they couple it dynamically, not statically. Casual, interpretable and uncertainty aware AI, which is very, very important. Foundation models for science, trained on structured, symbolic and multimodal scientific language. These kinds of foundation models are going to be more and more important, and I believe even these can change the science teaching also. AI systems that respect the basic physical laws like conservation laws, symmetries and physical constraints. These are just not academic requirements. These are essential for trust, generalization and the deployment on scale, especially in safety critical domains. There are many domains where you cannot afford a little bit of lapse. This is where institutions like IIT Kharagpur must lead, not by some initiation, but the entire new idea should originate from this place. There are several unreached territories where India can lead the world, and in this context, where we can define our own goals. AI for population scale science. AI for population scale science is something, perhaps we are one of the natural, users, and therefore we should be one of the natural leaders. So models that are not designed for idealized data sets, but for noisy, sparse and diverse real world data across billions of lives. Number 2, AI for frugal and robust science. Scientific AI that works under constraints, limited sensors, limited compute, limited infrastructure. Number 3, AI for coupled systems. Health, climate, energy, economy, all they are actually entangled in a physical world. And how we can develop such coupled models that break disciplinary silos and capture the systemic risk. IIT Kharagpur should be one of the natural leaders. On one side we have the law and another side we have the medical technology. So what not we have? How can we harness this to create coupled real life models? And AI for translational speed, from lab to field, from paper to policy, from prototype to people at unprecedented speed. That only AI can do, otherwise the usual computations will run and run forever. And AI as a public scientific good, open, sovereign and ethical AI ecosystem that serve humanity and not just markets. So in this particular pre-summit event, it is about not just answering or giving solutions to problems, but asking for better questions. How do we train scientists who think in naturally equations and embeddings? How do we train them to think differently? How do we align AI research incentives with national missions? How do we ensure that safety, accountability and inclusivity happens without stifling innovation? And how do we move from AI in science to AI as science. So as India prepares for the AI Impact Summit 2026, which is going to happen in February, the signal is clear. India will not be a passive consumer of scientific AI. India will be a global architect of AI-driven science and technology of cyber physical systems for societal impact. I believe that if any institute in IIT in the country can lead it, the first IIT Kharagpur priority should come. Naturally, not just because it has a unique set of AI faculty members and researchers, but a collection of academic and research units, including a special hub for AI for cyber physical systems. And therefore, I would imagine that this pre-summit will act as a nucleus of driving the institution and driving the nation forward to a next gen AI as science and AI as technology. Thank you. Namaskar. Jai Hind.
Thank you, sir, for those inspiring and encouraging words about AI for science across different domains. Now I invite Prof. Nilay Gongori, Head of Department of Computer Science and Engineering, to kindly felicitate our director. Our next segment is talk that sets the context for today's discussion. It is now my pleasure to invite Prof. Nilay Ganguly to deliver his talk titled AI at IIT Kharagpur, Legacy, Landscape and Origin.
So, thank you, Honorable Director, for this wonderful talk. And I will just give a brief overview about the research which goes on in the AI fraternity within IIT Kharagpur. So, just to give you some idea that what's it? Okay. Okay. Yeah, now I am free. Okay. So, okay. So, I guess the director has already told about the vision and philosophy. The most important thing is we want to our programs are aligned to national priority and initiatives, and it is about responsible and inclusive AI for India. So, coming to the legacy, which is that our computer science department started at 1980s, and the classical AI research in India actually has been led by computer science department. The classical AI, symbolic AI research was led by computer science department. Then came the data driven research, which again took off in the computer science department. And one of the important milestone of this data driven research was so one of the important milestone of data driven research has been Indian language NLP. So in the 2000, early 2000, there was a huge effort to actually build resource about Indian language, and IIT Kharagpur was one of the leaders of this initiative. So this was how things went, and things begins to really take off in the 2015 area. And then also we responded accordingly. First we built up this data center, the center for data, the high performance computing center. We built up the high performance computing center CCDS. Then we built up the center for excellence in AI. And accordingly also we built various other things like center for excellence for manufacturing technology, which was also data driven. After 2018, we built up the data hub and the AI hub to guide innovation, and also we built up the center of excellence for affordable health. So all this was under a strategy to democratize AI, take AI to a bigger level, take AI to most of the faculty, and which ultimately resulted in the department of AI, the development of department of AI. So now we have two big vehicles, department of computer science and department of AI, who are taking forward, and there are other departments also, department of EC, department of EE, who are also in various ways supporting and developing this AI ecosystem. So, and this AI ecosystem, one of the most important thing about this AI ecosystem is if you see the widespread research activity which goes on in the area of AI, and there are thematic things, there are core AI ML things, and there are domain specific thing like AI for agriculture, AI for healthcare, AI for energy science, earth system science. So these are the three major pillars based upon which AI research is going on presently in IIT Kharagpur. And also research has to go with curriculum, So now we have a wide spread of curriculum. So almost all departments now offer some AI courses. We have a institute wide AI course going on, and we have both BTech in computer science and BTech in AI, which is widely helping in developing the AI ecosystem. And we are not just stopping in this curriculum business. Within the bounds of IIT, we are actually taking up this outreach activity to schools, to colleges, to industry, etc. So this is what is going on. And you see there is a lot of industry oriented or industry focused programs which are going on continuously in the departments. So just to give you the thrust areas which the departments, the institute is focusing on, one is important that we have a data driven responsible AI. And this is like the government of India's thrust, and Niti Aayog says that we have to have responsible design, development and deployment of artificial intelligence. And also more importantly, what we are targeting is developing domain sovereign models for domain specific problem. That is also very important, that IIT Kharagpur takes leadership in developing sovereign models. And if you go through this data driven responsible areas, there is a lot of things which are going on inside the campus. There are tools and algorithms, the systems building, and the various focus area on which the faculty members are concentrating. And some of these are AI for healthcare. I think Professor Chakraborty already mentioned a lot of this about AI for healthcare, and I can see that the AI for healthcare starts from medical technology, goes to the genomic part. So, it is the entire focus area where AI for technology is, AI for healthcare is taken care of. And there is another very upcoming theme, and I think this is one of the theme of this workshop, AI for materials, where we have the target of generating novel materials that are stable, synthesizable, and whose properties satisfy design requirements of target applications, maybe like 2D materials. And what we are now developing are technologies and method, AI based solution and end user services, which can be used by practitioners, domain specialists to fasten their innovation. So, last I would say about AI for law. So, there is a big push inside the campus about having introducing new technologies for the judiciary to reduce pendency of cases in Indian courts and also make them available in Indian languages. And some of our faculty members have already built foundation models around Indian legal system, which are widely used within the community. So, all this thing is becoming possible because organically we have developed a collaborative ecosystem. So, there are core AI methods, the AI system so the AI tools and algorithms which are mainly hosted in the computer science and AI departments. And then we have various responsible AI methods, the data hub for AI research, and above that various other domain departments are participating and building up this collaborative environment. And this is also leading to the research laboratories. I must here mention one important thing, that we have in-house built up the data hub, and this hosts most of our IIT Kharagpur data sets which are built by various labs, and this is hosted in the data hub. It is a unique AI Kosh sort of things within IIT Kharagpur. So, just to stop here, the task ahead, IIT Kharagpur has vision, talent and infrastructure. IIT Kharagpur nurtures the culture of interdisciplinarity, and it has a sustained core skill development coupled with coordination and execution. So, we believe the workshop is just a starting point for sustained AI and science program. Thank you.
Thank you, Prof. Niloy Ganguly, for that inspiring and insightful talk. To give us an overview of today's workshop, structure, objectives, and planned activities, I now invite Prof. Laban Kumar Bhaumik, Head of Department of Artificial Intelligence, IIT Kharagpur.
Thank you, distinguished guest delegates and the participants, and I welcome to you this pre-summit workshop, which is a part of this India AI Summit event. And I will take you through the program structure and the key tenets of this workshop that might be a kind of useful thing for the coming 2 days. So, slide please. So, the program echoes the thought that Professor Chakraborty and Professor Ganguly has already talked about. This AI is a kind of horizontal technology. So, it is imperative to ask questions like, we will not be asking questions like whether to use AI, but the most important question to ask is how to AI, and that is where the interdisciplinarity is the key, and that is the kind of tenet or the theme of this particular workshop. And this workshop, so it is basically we are looking at the things like people are from different disciplines, they are going to use AI, and that is already there, but they are being done in silos. And this kind of activities are done without having a kind of shared platform. So, the need is that we have to have a common language, cross domain dialogue with a shared vocabulary among the AI and the science researchers or the domain experts. And the primary goal would be to come to a kind of point where we can think about large interdisciplinary proposals covering AI and other disciplines. So the themes for this workshop, though it is not, it's like AI for X, but for the sake of time, we are having only 2 days. We'll be covering AI for material development, AI for weather and climate modeling, AI for bio and life sciences, but though AI for education and AI for other things are very important for us, but maybe you can take that up for other upcoming workshops. So the activities include keynotes and invited talks, student poster presentations, startup pitch sessions, and finally a kind of convergence through a brainstorming session. So to give a kind of glimpse of the events, we have a bouquet of events, very exciting ones. 2 plenary talks by Debjani Ghosh from Niti Aayog and Shiv Kumar Kollan Raman, CEO ANRF. We have 3 different dedicated themes or the parallel sessions, AI for materials, AI for weather and climate, AI for bio life sciences, and there are 2 types of exciting competitions, one being the student poster presentations, and we are overwhelmed to see a kind of response. We have received around 150 poster submissions, and that shows that the importance of such kind of workshops. And we have a startup pitch tomorrow, 20th January, and I'm happy to share that around 30 applications or submissions have been made in this area. And finally, we will be coming to a kind of convergence through a kind of brainstorming session, which is going to be a parallel session. For each of the themes, we will be having a brainstorming session, AI for materials, AI for weather and climate, AI for bio and life sciences, and finally a kind of summarization of the findings of the workshop. So that's how the workshop will be, or the activities of the workshop will be there. So the responses are fantastic. The participation are strong from IIT Kharagpur faculty and the students, nearby institutions, industry and startups and domain experts from different institutions. The key highlights are like there are extremely high number of registrations, around 600 registration requests we have received, and there are around 150 poster submissions, as I have told you earlier, and finally around 30 number of startup speech submissions. So the brainstorming session is a kind of a very unique event that we are holding in this workshop. This is a kind of culmination of the ideas that will be happening throughout these 2 days. So the idea is that the slogan is ideas to impact, and where the collaboration between the AI fraternity and the domain expertise would be very useful. And the key takeaway for this, so it will be a kind of 1.5-hour breakout session, and it will be happening today. The goals are like to identify high impact nationally relevant AI research problems and to foster academia industry and academia collaboration. And the hope would be that the research ideas that may evolve into sponsored project, mission scale proposal, translational activities or initiatives, and finally follow up working group efforts. So the takeaway is that let's make AI plus science collaboration a routine, not exceptional. So with this, I conclude my session, and I hope that the 2 days will be going to be exciting and fruitful, and we'll be having huge takeaway in the number of ways. Thank you very much.
Thank you, Professor Plaban Bhaumik, for setting the stage and giving us an overview of the workshop. Before we proceed further, Professor Plaban Bhaumik will now introduce us to the chief guest of this workshop.
So I'm extremely delighted to introduce you to Debjani Ghosh, who is going to be our first plenary speaker of this event. and she is a distinguished fellow in Niti Aayog, and she is going to talk about frontiers of technology and its importance for India. So, should she come on the stage? So, I'd like to invite you on the stage. Thank you. Should we be connecting her laptop?
Okay, I'll just keep this here. Are you going to put up the slides?
So, Debjani Ghosh is a senior Indian technology executive and policy leader who currently serves as a distinguished fellow at Niti Aayog and is the chief architect of the Niti Frontier Tech Hub, a think tank focused on emerging technologies and India's technology-driven economic growth and societal development. Prior to this, Debjani was the president of NASSCOM, becoming the first woman to lead the organization in its history and advancing India's role in frontier technology and global innovation. Earlier in her career, she was the first woman to lead Intel South Asia operations and held senior roles across sales, marketing, and business development at Intel. She is known for championing human-centric technology, responsible AI practices, and inclusive innovation, and for coining the concept of TechEd, a vision of a decade of transformative technological progress. Her contributions have been recognized with honors such as being featured among Vogue's Tech Leaders of the Year and Female 10 40 over 40 World's Most Inspiring Women list, and she was facilitated by the President of India as a pioneering woman leader. So, with a big round of applause, let me welcome you again, ma'am, and looking forward to our exciting talk.
Thank you.
Thank you.
Thank you so much.
Can you mute this? The collar mic?
It's okay, I'll use this, no worry, thanks. Thank you, and thank you, Niloida, for the very kind invite. It's wonderful to be back in IIT Kharagpur after nearly 2 decades. So it's fantastic to be here and see how this campus has grown. Professor Chakravarti talked about the India AI Impact Summit, and I am privileged to chair one of the 7 committees that the working committees that the summit has set up. The one I'm chairing is on economic development and societal good. And these committees have participation from across countries, so there are nearly around 40 countries participating in this working committee. And the one thing that is very clear is while the last maybe 3 years was really about the mass public waking up to AI and beginning to understand how powerful it is, and that power being defined by who builds the bigger models, who has the biggest compute announcements. The next few years is going to be about putting that infrastructure to work to create impact. Because the biggest challenge that the AI narrative is facing today is the fact that no one is clear what is that roadmap to impact. And if we cannot fix for that, then how do we justify the trillions and trillions of dollars that is going into building the infrastructure? So it's very clear that the future of AI is about impact, and I would go as far as to say the future of technology is about impact. And what's exciting is India prioritizing this word impact for the summit. The summit has different names. It started in UK over 4 years back, where it was all about safety. Then in Paris last year, it was about action. I think it's fantastic that India has prioritized the word impact, because this is going to be the benchmark for tech success going forward. How much of an impact does it actually create? So that's really what I'm going to be talking about in terms of what does the future hold, and what's there as far as the frontiers of technology is concerned, right? But before I do that, I'm going to very quickly explain what Niti Aayog is doing in this space and why it matters. So, the Niti Frontier Tech Hub that we have set up, the job is very simple. It's a forward-looking think tank, or action tank as I like to call it, because it's not just about thinking, it's also about converting that thought into action. And our job is to understand how is the technology landscape going to change? What are the key evolution of, that we should be following, that we should be unpacking, that we should be trying to understand? What are some of these key trends that's going to be tremendously disruptive? And then to spot the trends early, unravel them, understand what they mean, and once we've done that, then start figuring out what its impact is going to be, and we use 4 lenses. What is its impact on citizens? So for example, what do these trends do to jobs? What do these trends do to healthcare? What do these trends do to education? The second thing we unravel is, what does it mean to industry? How is it going to transform industry, existing legacy industries like manufacturing, agriculture, services? What new industries are going to get created in the future because of these shifts? The third thing we look at is, how does this transform government itself? What does this mean for national security? What does this mean for how governments govern? And the last thing we look at is, what does this mean for geopolitical shifts? If anything, I'm sure you all have been following the news in terms of the continuous debate as to who's the AI leader. Is it China or is it US? And what that means. It has impact on trade. It has impact on complete geopolitical dynamics. So technology today is no more an enabler of power. Technology has become the axis of power. Let's not kid ourselves about that. And it is impacting everything from geopolitical dynamics to trade. So what does that mean? I mean, those are some of the things we look at. And by the way, a lot of our work is available online, so you can go and look it up and download a lot of the recommendations, etc., that we are coming up with. So why is this important? Why is it important to have an organization that is just looking forward 5-10 years to understand what is happening? One, if you look at the success of tech companies, those who actually succeed are the ones who spot the trends early. Same with nations. And otherwise, you're perpetually in a catch-up game. You're going to be chasing what US is doing, what other countries are doing to figure out how to catch up on LLMs, how to catch up on semicon, etc., etc. It's usually a tech shift takes around 10 years to become mainstream. So if you're able to spot these shifts, maybe half of what you spot will happen, half won't. But even if half happens, you've made it. Because if you're able to spot these shifts early and you're able to invest in it today, then our actions we take today is what's going to shape where we will be with respect to these technologies tomorrow. So that's why it's important. Another reason why it's important, I don't know how many of you have seen, this is a very famous chart that does the rounds of presentations, but the correlation between tech revolutions and GDP growth. If you look at the first 1,000 years of stagnant GDP growth, then comes the steam engine, the invention of the steam engine, and you suddenly start seeing the curve moving up. Then comes the entire industrial revolution that we call, the printing press and onwards, right? And you see a step change. The the knowledge revolution, again you see a step change. And now with intelligence, the intelligence revolution, I won't even call it AI, I think the intelligence revolution is where people are expecting not just a step change, but an exponential change. The pundits have predicted that in the next 10 years, the intelligent economy is going to result in anything between 17 to 25 trillion incremental to global GDP. Now the question is, if that is going to happen, if it is going to be around 17 to 20 trillion, how much of it will come to India? If you look at all the analysts, 90% plus of that is just going to two countries, US and China. And the predictions of that 10% is broken up amongst all countries. A very tiny figure will be coming to Asia and particularly to India. I think that is where we have to challenge status quo or predictions. We have 10 years. We have 10 years in hand, and we have the technology that can drive the transformation. So is it fair to say we should be aiming for minimum 10% of that value creation? 10 to 15% of that value creation in 10 years has to come to India. And that's the problem statement that the Frontier Tech Hub, the Niti Frontier Tech Hub is starting with. If we have to get to 10 to 15% of that value creation, what do we need to do? And by the way, that 10 to 15% of value creation, roughly around 1.72 trillion, 1.5 to 1.7 trillion, is what is going to set us on track to be ready or to be on track to get to becoming a developed nation by 2047. That's going to get us to 8 trillion by 2035. So this is fundamentally important for various reasons: economic reasons, social reasons, national resilience, national security. All of that comes together. So this is sort of the problem that we have put out as we are looking at what changes do we need to make, what are the strategic bets that we need to make as India to capture that 10 to 15%, right? So if you look at, this is our lens. This is the Niti Frontier Tech Hub lens. But you know, there's so much of technology that's shifting. Everything is a moving goal, right? It's an infinite game that we are playing here. Everything is a moving goal. But when we look at all the shifts that's happening and we apply 4 lenses to it, what's important for national security, building national resilience, food security, water security, trade security. So how do you build supply chain resilience? How do you build national resilience? What do you need for accelerated economic growth? And what do you need for accelerated social development? Because economic growth without social development, again, is definitely a problem, right? When you apply those 4 lenses, we believe these are the 4 trends or 4 shifts that's going to be very, very important for India. The evolution of intelligence, the convergence of science and engineering, distributed compute, and then lastly, quantum moving towards applied quantum. And I'll talk briefly about this. Let me start with the evolution of intelligence. So again, when you look at the evolution of when you look at what's going to happen as we move from artificial intelligence to cognitive intelligence, I don't know when, the timeline is out there. Everybody has, some people say 5 years, some people say 10 years, etc. But it's not a matter of when, but I think the thing is, I mean, it's not a matter of if. We know we are going to get there. The question is when, right? Again, when you break down what that means, from an India perspective, there are 3 things that are becoming very important. Unlocking the productivity gains. How do we ensure that has an immediate, that's near term, short term? How does it impact us today? Accelerating scientific and technology discovery. And then last but not the least, how do we navigate the rise of digital labor? I think that's a very serious question India needs to ask. All countries need to ask, but especially India, given our young demographics. So, unlocking. Now, this is I've put the websites down so you can go and download. But this is a pretty extensive study that we have published on when you think of leveraging or unlocking AI for accelerated economic growth, you can't have a generic national strategy. It doesn't work that way. So what we did is we actually went and looked at across sectors, all the industrial sectors. And we worked with McKinsey to do a modeling of where are we going to get the highest incremental gains from AI automation, right? From integration of AI into the basic workflows and processes that define the business, the operation model. And it's a pretty extensive study that you can go look up. But what came out of it is, if we do this right, in the next 10 years, just focusing on 3 to 4 strategic sectors. We identified manufacturing, we identified finance, we identified pharma, and I think there was one more which I'm forgetting, but I think it was automotive that we identified. Just taking these 4 or 5 core sectors and really doing a deep unlock, which is not just, you know, the data analytics piece. That is being done everywhere, the conversational chatbots, et cetera, that's not AI integration. But really going deep in to build that intelligent layer that can completely transform workflows, we can unlock around 500 to 600 billion in the next 10 years. But it needs a very focused sectoral outlook. You have to go sector by sector, you have to build sectoral playbooks, and most importantly, you have to unlock the enablers starting with data. So again, I'm not going to go too much into it. If you're interested, go read the paper. All our papers, I was just telling someone, we filter out the gyan, so a lot of the gyan is left out. What we really put in our roadmaps, every paper is a 10-year roadmap with very clear action points for Government of India on what it needs to do starting now for the next 10 years to get to these points. So this is out there. The second one I talked about was accelerated scientific discovery. And I think Professor Chakraborty is right. Maybe we need to change the word accelerated. It's not just about speeding things up. It's really about reinventing science. It's about reimagining science. I mean, for example, how many of you have heard about the sleep foundation model that came out, I think, around a few weeks back, last month, if I'm not wrong? The first ever sleep foundation model, with just one night's sleep, it can track or it can predict 130 different conditions in human body, including heart disease, including kidney failure, et cetera, et cetera. I mean, that's the kind of science we haven't even thought about, right? And that's being done today. So again, looking at it from an India perspective of, you know, what are the non-negotiable priorities for sovereignty and tech leadership? And when I say leadership, I mean resilience, where India is defining the standards, not just becoming the biggest user of technology, but driving the innovation, defining the standards, and driving impact, right? These are the 4 areas that we recommend that India prioritizes: semiconductors, life sciences, critical minerals, and clean energy, from usually really putting our, you know, we have a country where we don't have it, you know, we have limited resources, let's be very clear. So when you have limited resources, you can't go and do it all. You have to pick your battles. So if we have to pick the battles in R&D, then, you know, and again, I'm sure there could be different points of view, but based on our studies, these are the 4 areas that's going to be critical for both sovereignty and resilience. For example, and the way we are looking at what we should be doing is very outcome driven. For example, when you look at just biopharma and you look at what accelerating scientific discovery in biopharma should be. For example, in the next 10 years, can India create up to 100 innovative drugs? And if we do, then what's the value? It's going to be around $3 to $8 billion added. So what is now needed to unlock this potential? So that's how we are looking at the entire process of AI for scientific discovery. And you know, I think one of our key recommendations is that it is time for a national mission on accelerated scientific discovery in India. And in fact, we've been working on this for many months, and Trump, US has just announced the Mission Genesis, which is very similar, which is about pulling the data together, creating that network of intelligence, connecting the universities to it, and then ensuring that they use that to solve for critical challenges and problems. And I think India absolutely needs a similar approach, and if government has to be involved, it has to be a whole of government approach and not silos to ensure that we can drive that end-to-end transformation, right? But this is something that, as Niti Frontier Tech Hub, we believe is the time is now, it's needed, and it's one of our key recommendations on what should be done. The third trend I talked about was the rise of digital labor. If anyone has been tracking CES news, you know it's all about humanoids, for humanoids that can cook, humanoids can do your laundry, everything is about humanoids, right? And the numbers sometimes can be a bit daunting when you see 4 trillion in the next few years, and most of that going into household services, and you sort of, I mean, I can't imagine a humanoid in my house, right? But it sort of hits you when you see the pace of progress. This is October 2023 on the left side of the screen. This is what robots or humanoids looked like, right? They were clunky. If they fell, they couldn't get up. And this is what 2025, just 2 years. The kind of progress that we are making in robotics is absolutely mind-boggling. And I think the question here is, what does this mean for humans? And how does this change the balance between human and machines? It's not just at work, but also in your homes. And I think this is something that we really have to be thinking very hard about. So if I sum up this section, the first section that I talked about, which was intelligence, you know, from a recommendations perspective at NITI, we are talking about unlocking productivity. We believe it can get us around 500 to 600. We are talking about accelerated scientific discovery with AI. We believe that's another roughly 300 to 500 billion potential. But again, the key is pick the battles, pick the focus sectors. Pharmaceutical is a key area. Physical AI is another key area. Automotive, by the way, tremendous potential for innovation leapfrog. So pick the areas, define specific strategies to go after it with clear outcomes being called out. And then comes the next one, which is what happens with human beings. Now, forget humanoids taking our jobs. If you just factor in productivity, today, and I'm talking about 2025, right? 2025 going into 2026. Today, just in India, AI has already displaced around 75,000 jobs. And it's not because there are humanoids doing our jobs. It's because of productivity. The current unlock you're getting out of AI in jobs is already around 15 to 20%. And in the next 2 years, it's going to reach 50%. That's where you're going to see a mass displacement happening. And it's not jobs, it's tasks, right? It's the tasks that form the jobs that are going to change. So you're going to see, our prediction is conservatively that we are going to see around 2 to 2.5 million displacements in India. Yes, there are new jobs that are getting formed, and those jobs can actually give incremental, create incremental jobs in India, but there's a big change. What we are being skilled for are the jobs that are going away. We are being skilled for the low-end jobs, data entry. I mean, I'm talking about IITs. I'm not talking about IITs. I'm talking about overall education as such. Data entry, that's where millions of kids get employed. Call centers, millions of kids get employed. L1 coding, etc., software engineers, millions of kids get employed. All of those are going to get displaced because you will not be able to justify to your customers or board that you need humans to do those jobs. In fact, one of the largest automotive companies in the world, based out of Germany, has already come out with an RFP which says, which asks in your bid, how many agents are you going to deploy? And if the use of agentic AI is not going to bring down costs by 30%, then don't even bother applying. That's the reality of RFPs bids today. Now think about it, what it is going to do in the next few years. the problem is the mass scale jobs are going away. What is getting created in its place are hyper specialized jobs, which at best employs 1,000, 100,000 people. But when you add them up, the opportunity is tremendous. But what that needs, or that challenges us, is a complete disruption of education system. Because one of the biggest differences in education when we looked at, and part of this work, we looked at our top 5 engineering institutes and top 5 engineering institutes in US. And to just see what's the difference. One, AI is integrated across, it's not a silo, right? Two, as far as the curriculum is concerned, not much of a difference. Yes, some of the things that we have to start doing, but I think that we can do very easily is move from skilling people on how to train models to really figure out model architecture. That's the requirement of the future, right? But the big difference is the agility of curriculum refresh. How often are these universities refreshing their curriculum, completely changing curriculum versus us? And I think that's where India has a huge challenge. So one of the things as part of NITI we are recommending is the need for a unified AI talent mission across India that focuses on embedding AI into the curriculum from K-12 to higher education to engineering, making sure that we are able to bring back a lot of AI talent. I think this has to be done, and and reskilling the industry pipelines, because all three becomes very, very important. Again, if you go onto the website, you can download and read. It's a pretty detailed roadmap with recommendations. But this is going to be one of the biggest social challenges that India will face if not done right. So that takes me to the next one, which was the convergence of science and engineering. Many people call it frontier technologies, which is where science, engineering comes together. Again, multiple areas that are coming into this play of convergence of science and engineering. From an India perspective, the few that we are prioritizing or focusing on as part of our recommendations to government is, first, the biorevolution. Right? I believe this is going to be way more disruptive than AI. And this is intelligence plus biology coming together. This is what leads to the creation of what we call in slang language programmable biology, right? Where you can pretty much go in and code the basic molecules of life. And imagine the power that gives you to do both good and bad. I think this is going to be the next big thing. It already is the next big thing. I think every company in the future, we used to say that every company is going to be a digital company, AI first company. I think the next big thing you're going to hear is every company is going to be a biotech company. It's a fact, right? And some of the areas under that we are focused on as part of digging in deep to figure out what India needs to do are bio-industrial, pharma, energy, bio-agri, bio-AI, et cetera. And this is work in progress. We are working on these to come out with the roadmaps to define these. The second area, one of the key things that we are, again, this is work in progress that we are iterating, but India has a lot of good work, especially under the Bio-E3 policy. There's a lot of good work happening in this space already. I think if we have to take that leap that we have to, if in the next 10 years, then one of the things is needed is to think much bigger and unify versus silos. So one of the things we are recommending is around multiple missions to go after critical problems like affordable gene cures, climate resilient crops, et cetera, and each of these is defined by clear outcomes for the next 10 years. Right? So this is something we are working on and hopefully will be coming out with very soon. But for example, in Gene India, under Genomic India, you have tremendous work going on. DBT is doing great work. There's just so much of good work happening across the ecosystem. Are they connected? No. So the idea of Gene India is really to say, connect the dots, bring it together. We need to be ambitious in the database that we are creating for genomics in India, where it has to go above maybe 1 lakh from the 10,000 or 20,000 or maybe 50,000 it is today. Right? How do we do that? And then how do we use that? So this is sort of what we are working on in terms of our recommendations. The second area is, I think, very relevant to all of you, which is materials. And what's going to happen with, I think this is going to be one of India's biggest leapfrog opportunity to break through some of the strongest choke points in the tech supply chain. And as you will agree, one of the biggest choke points in tech supply chain is semiconductor. And I do believe that this gives us, if we invest right, if we focus on the right R&D, etc., especially in 2D, this could give us that opportunity to break through the supply chain, the supply chain dominance and choke points that we are seeing. Again, we've published a full roadmap on this. Look it up, but this is Notebook LM doing a fantastic summary of the entire roadmap. But some of the key things we recommend in that in under 2D is national innovation hubs, specific, targeted, focused on outcomes. For example, one for semiconductor, one for energy, et cetera, et cetera. Under RDI, carving out significant amount to just go after this because this is critical for sovereignty. The lab to market translation is going to be tremendously important. So therefore, how do you connect industry with academia and with these centers, building global trust collaborations? You need trusted supply chains today. There's no way, if you think of the end-to-end stack, it's going to be pretty much impossible for most countries to build, make it completely indigenous, complete end-to-end. You have to figure out what do you need to really go after to build your sovereignty, to build indigenous supply chains, and that's going to take exponential R&D. And then the rest, where do you build the trusted supply chains, right? And how do you integrate this with national missions like semiconductor mission, quantum mission? I mean, all of these things have to start coming together. Then comes the third one, I'm going to run through this, which is distributed compute, right? And why is this big? Because again, this is going to be another opportunity for India to break the semicon dominance that we see around the world. I think most of us agree that the future is going to be compute moving out of centralized data centers to the edge, to distributed compute, where you are going to have the intelligent edge. And this is going to be powered a lot by trillions and trillions of intelligent sensors. Now, can India get into the game early and start preparing the ecosystem to design, manufacture, build the entire supply chain for the infrastructure that is needed to power the era of compute everywhere, or omni-compute as it's called? It's a pretty big market, around 18 billion in 2024, going up to over $1 trillion by 2035 in the next 10 years. It's a pretty big market. So there's tremendous opportunity, and I do believe that it plays to our inherent strengths in semicon and IoT. Tremendously plays to our inherent strength. So this is something that we are watching for, believe it's going to be very important. And last but not the least is applied quantum. Now, if you're following quantum news, especially what came out of Google the last few weeks back, we know that quantum is now moving from labs, from theory, to at least pilots of application. Right? And this can have potential to disrupt areas like drug discovery, climate, energy, and this can be, and security. Security is huge. So again, when we think about, this is another work that we've published, you can go look it up. When you think about next 10 years, where should India land with respect to quantum? Now, of course, there's the National Quantum Mission, which has given us a very early start on building the core infrastructure of compute and R&D. But we now have to build on top of that. We have to build on top of that and unlock the application accelerators. And some of the things that we are looking at is what should be success. So in 2035, can India have 10 quantum champion startups that are 100 million each in critical areas like health, drug development, energy, etc., etc. So you know, can we go after the quantum services market, get 50% of that market? That is projected to be huge. So how do we build our targets, and what do we need to do to go after it? Because this is again going to be pretty disruptive. And as we do all of this, you know, those are the 4 trends that at Niti Frontier Tech Hub we are looking into, we are studying, going in deep and figuring out what should government be doing, what are the 10-year roadmaps, what's the 10-year action plan for Government of India and industry, right? But as we do this, I think it's important not to forget that as these trends evolve, so does the risk surface for India. In fact, the risk surface is completely changing. I mean, if you look at it from a citizen perspective, we broadly classify it into 4: cyber, social, emerging, and operational, right? In cyber, we used to be worried about devices being hacked. Today, honestly, that's not that big a concern. The bigger concern as a nation is my power grid going to get hacked? Is my digital infrastructure going to get hacked? Social impact, bias continues to stay a concern, but I think the biggest concern is going to be cognitive warfare. It's already happening. You see it play out in elections every time, right, in all countries. The second one is the job displacements. For a young country like India, this is going to be a huge social challenge. And then emerging threats, bioethics. We talk about quantum security. I think bioethics is another huge one. Biosecurity is another huge one. And then the operational gaps that exist in the system, the biggest one being silos. We don't talk to each other. And I think that's going to be, that's the one thing that doesn't work in frontier technologies or AI. Silo is the biggest enemy of impact. And unfortunately, that's got ingrained into a lot of work we do, both in government, industry, and academia. So I think mission 1 has to be, how do you break the silos? And you know, risk that's a citizen risk. Then there's a whole lot of work we are doing in understanding what's the risk to national security. And the entire risk landscape is changing. As you can see, it's not just anymore about weapons getting more sophisticated. It's about cognitive warfare. It's about biological risks. It's about aerospace. So, you know, I just want to give you an understanding. The world is changing very fast. The opportunities and the risks. And this is something, if we don't factor in, we are going to wake up to these things after they happen, and then we are going to always be in the mode of figuring out how do we catch up, which is what, to an extent, we've been doing the last 10 years, other than DPI, where we completely changed the game. Right? So I think this is why it's important not just look at today, and not base, and if you talk about academia, not base our learnings and curriculum on what is happening around the world today or what has happened in the past. But we have to get comfortable with the uncomfortable, which is predicting what will happen in the future. It is uncomfortable because there's no surety. It's very uncomfortable. You can paint 10 scenarios, 3 will stick, 7 won't. But that's great if 3 sticks, right? And I think this is going to be the need of the hour for India. This is some of the work we have done. Again, do go through and please send in feedback. I'm at debjani.g@gov.in. Please do send in feedback if you want to, or you want to collaborate in any of these areas. It'll be an absolute pleasure. But this is what I want to leave you with. I think the time today is to move from incremental benefits of technology to figuring out how technology can transform, how technology can reinvent. And this is, now that's not going to happen in a day. That is going to take time. That is going to take 10 years. But that will not happen if in 10 years, if we don't act today. That's very clear, right? And this re-engineering needs to happen across 4 pillars. First, R&D. We have to completely re-engineer how we think about R&D. I mean, I'm a fan of Jugaad. I'm a fan of frugal R&D mindset. It has served its purpose. But don't let it become a handicap. Don't let it become a limitation for you. You have to break through. If we want to do these things, we need abundance R&D. We need exponential R&D where we are not worried about failing, where we are not worried about what happens if we fail. And this is a change that has to happen both in government as well as academia. And it has to be R&D that is leading to outcomes. I think we have to very quickly prioritize translational R&D over everything else. The second one, are our education systems still building for the past or building for the future? It is an uncomfortable question. I know you will not like it, but for those of you who are either professors or students, are you teaching or are you being taught for jobs that exist today? Because if you are, you should be worried. Because by the time you get out there, those jobs may not exist. They'll be completely new jobs. And I'm dead serious about this. If there's one thing you take away, please take this away. We have to ensure our education systems are building for the future. How do you change governance and how government comes out with policies? I think that's another re-engineering that's needed, because for one thing, you cannot hardwire policies for 50 years anymore. You have to build policies that are flexible, that can continuously be adapted as technology changes. And last but not the least, I think partnerships for trusted supply chains becomes tremendously important. India is good in building ecosystems, but we now have to take it beyond. We have to start building global partnerships and alliances to ensure that we protect the supply chain, especially when it comes to the critical choke points, semicon, energy, critical minerals, etc. I think those are going to be very clearly, but none of that is going to happen unless we have a fundamental pivot of how we think, our mindset, the human. You know, the technology is going to be available to us. The question is, are we equipped to use it the way we need to use it to transform, or are we going to continue to use it to drive incremental benefits? And that's the question I will leave you with. Thank you very much.
Thank you, ma'am, for this exciting talk and taking us to the future roadmaps and things that we should be mindful about. So I hope the audience has taken important cues about the future programs that we want to take up, the research programs as well as the collaborations, etc. So there is, we have some time for a couple of questions, if that is. Sure. So if there are any questions from the audience.
Yeah, hi. Yeah, thank you, ma'am, for this comprehensive overview. My name is Ayush from NVIDIA. So my question is, like you mentioned, encouraging R&D is one of the focus for Government of India. And we know like the R&D investment with respect to GDP is like less than 0.7 or 0.8%, which is like less than probably a couple of companies R&D investment from US. So my question is, like how government sees encouraging R&D investment from industry. Like one of the ways you reduce tax outgo for the investment made by industry for R&D. And do you have like any opinions on this particular, or like what are the different ways that can be used to encourage R&D investment by industry specifically?
I think you all have heard about schemes like RDI, ANRF, and these are mega schemes. They're much bigger than government has done anything, you know, in this area earlier. And the whole objective of these schemes is, and I know Shiv is here in the afternoon, so I'm sure he'll talk more about it, but the whole objective is to change how we do R&D, to move us towards higher risk taking, more exponential R&D. So I think government is definitely coming out with the right kind of schemes, etc. But the fundamental reset that has to happen is, in my opinion, and I'm not speaking on behalf of government, but strictly in my opinion, is how we measure R&D, or the work that academia does in R&D. It can't be measured in terms of how much of the budget spent or how much of, you know, the checklist, it has to be measured in terms of exponential outcome. What happened to that outcome? What did it result in? And unless that fundamental shift happens in R&D governance or whatever you want to call it, I think for the dollars to get fully utilized, that has to happen. And as far as industry is concerned, I think it's time for industry to wake up to the fact that R&D is not something that you do on the side. It's a good thing to do, but it is now a basic necessity of competitiveness. If you're not going to innovate, you are going to perish. It's very clear. And in today's world, IP creation is becoming a must-do. Whether you're a service, even in services, because everything is, the business models are changing. Service is changing from the typical way we delivered services to now service, you know, pretty much people paying for outcomes and not the service that you give them, right? And that's going to happen. I think the agentic AI era is going to drive that. It's going to completely disrupt the business model. So IP creation is going to be a must-do, and I think companies are waking up, but maybe a bit slowly. That has to happen very fast. They should do it irrespective of what government does or not, because it's fundamental to their success and survival. I think there's a question here.
Hello.
Yeah.
Thank you, ma'am, for that talk. It was really nice. One thing that you said which really touched a chord was how the GDP keeps growing, but there's also a lot of job displacement, and I think we run the risk of what is known as jobless growth. And I just want to know, one of the things that, like, say, problems that AI could create is...
I can't hear you too clearly. Can you just hold the mic up a bit?
Sorry, can you hear me now?
Yeah.
Yeah, okay. Thanks for the talk. There's some really nice points you brought up, and one of the things that you mentioned that really touched a chord was how you keep showing that the GDP growth is increasing, but there's also a lot of job replacement, and I think this is a really major concern because we run into the risk of having, and maybe we're already a bit there, of jobless growth. And I think one of the things that AI is going to do is just increase this sort of income inequality that we have.
Yeah.
So are there any specific studies that you can speak to on how we can insure ourselves against that? Because a lot of the jobs that are getting created are so niche, and not only do they require very specific skill sets, there are only few institutes can actually prepare people to get those jobs. So I just see this as an increasing problem of, and what your ideas on how to deal with that are. Thank you.
You should go through the paper we've put out. It's on our website on this. For this one, instead of 10 years, usually we look at 10 years, but for this we've looked at the next 5 years because it's a now immediate problem. It's not a problem that will come in the future, right? You should look at that definitely, and please give feedback when you do. You know what we found, and we did, this study actually went on for over a year because we did extensive research on this. What we found is the new jobs that are getting created, actually when you add them up, today the overall tech workforce in India is around 8 to 9 million. 6 million is employed just in the tech industry, the rest is across industry, right? If we do nothing, if we continue as is, that will shrink to 6 million by 2030, right? If we can change, and it's a skilling challenge, fundamentally it's a skilling challenge, how we are skilling and what we are skilling on. If we can change education system and skilling, we have the potential to take that up to 10 million. Because the new jobs that are getting created, each job is narrow, hyper-specialized. For example, anyone knows what's one of the largest openings on LinkedIn today? Anyone knows? In these new jobs, haptic engineers. Now, how many institutes are actually training people to become haptic engineers? Right? You know what haptic engineers are, right? You basically build in touch. into your compute, sensory. So you go into Amazon, today you're seeing curtains, you can actually feel the texture. That's what haptic engineers do. How many of us are teaching it? So while these are hyper specialized and they have hire maybe thousands, hundreds or thousands, etc., but when you add up these jobs, it's huge. So what this means is we have to move away from the comfort of an education system that has been churning out people so that millions will get employed in one job, to completely change the game. And basically we have to skill for forgetting what you learned in the past and quickly learning new skills with the fundamentals. And I think statistics, the AI fundamentals, I do call out statistics because I think that's so important in this world, right? Just the statistics, understanding of AI fluency, building the architecture, it's data analytics, data science. These are now life skills. They don't belong to a department, they are now life skills. So how do we quickly convert these into life skills and then build on top of that and continue to change? That's going to be it's very difficult, it's not easy, but that's the future world.
Hello, ma'am. Thank you for
so I guess there will be many questions, but for the interest of time, I guess we can accommodate one more question.
Okay. Hello, ma'am. Thank you for your wonderful talk. So I was just going through the roadmaps of Viksit Bharat. So the articles that are there. So I found that there is separate article for climate or weather or environment. In the roadmap.
So if you're talking about the Niti Frontier Tech roadmap,
Yes.
Please don't read articles, read the paper. Okay, articles, don't go to ChatGPT and say give a summary. If you really want to understand, read the paper, right? The paper is focused on industrial productivity. This paper, particular paper. There is work, as I said, a lot. We've been in existence for less than a year. So in this 1 year, what we have focused on is industrial productivity, job security, quantum, a few other 2D materials, few other around 7, 8 areas. Now the work continues. We are working on not so much climate change, but we are working on things that we believe are going to be critical for India, like water security. In the next 10 years, that's going to become a key problem. So what should be the roadmap? What should be the roadmap for food security? So we are working on areas like this, but I haven't yet started something on environment. If you have ideas, send. Happy to look at it.
Because air pollution is a recent problem.
Yeah, there's a lot of people working on it, so I try to pick problems that is not being addressed, because there are a lot of people working on air pollution. And it's a now problem. Again, keep in mind the Frontier Tech Hub looks at a 10-year horizon, right? Yeah, if they don't solve it now, we'll all be dead, so we'll have to figure out what to do. But it's a good idea. Maybe I'll go back and think about it.
Thank you.
Okay, thank you very much.
Okay, thank you, ma'am. So we are really delighted that you have taken your time and visited IIT Kharagpur and shared your words with us. So I'll request you to stay back for a few more minutes.
Thank you once again, ma'am, for a very encouraging and thought-provoking talk. I now invite Prof. Partha Pratim Chakraborty from the Department of Computer Science and Engineering, IIT Kharagpur, to kindly felicitate Ms. Devjani Ghosh.
How are you?
Now I request Prof. PPC to share few words of wisdom.
So, first of all, I would like to welcome all of you again. And I'm sorry for not being there in the first part. You know, we have one puja that we have to do, without which it doesn't work. So I had classes from 8 to 10. So I just completed my class and came. First of all, I would like to thank Debjani. We've been in committees even in the last few days on the ACM committee and things like that. And from prior to NASSCOM days, we have been connected. She brings a level of integral thought and the whole pathway to achieve it in a manner in which she has driven NASSCOM and today at Niti Aayog. And all of us must understand that if we are not going to transform teaching and research from whatever she said, today the student who goes out should be able to sit down and work in a team to design the next level turbine, processor, engine, or a climate model, or whatever. And that whole process of integrated thinking with the three layers of the science, the digital, and the physical. This combination must transform our teaching, and wherever we have been working, we are saying, what will the students need at 2030, 2035? Otherwise, we will become gig workers. Even in the academic sense, we will become gig workers. So I think we must build on what she has said, and I would request Niloy and others, and I'll be happy to be part of it, to engage with Niti Aayog and a follow-up engagement so that an IIT Kharagpur strategy can be formulated with Debjani's help and get to a point where we can formulate the next level of action items based on this trend map, rather than just go and hear everything. I will request, I was talking to Niloy, that we will follow up with you. We'll have a separate meeting at Niti Aayog and follow up on each of these items. I again thank many of my friends and others who have come here for presenting this. IIT Kharagpur, as Niloy and Suman may have already pointed out to you, has its own uniqueness of integrating several things. So we are now moving into the direction of, as you just mentioned, cyber-physical AI. We are not in the business of making large LLMs and things like that. We are going into the cyber-physical space where we want to target each of these focused categories, and we want to work with the others so that we are able to build this chain. So to all of you who have come here, thank you very much, and we look forward, Anup and Prasenjit and everybody else who are here. I wish that this goes on well, but since you have come to IIT Kharagpur, I would request somebody from our teams, and I request Niloy and Devaditya and others, to find a follow-up roadmap of this, so that maybe 3 months, 6 months down the line, we can have a very concrete proposal which we can send to SHAVE, which we can post on with others at MeitY or things like that. So I will request everybody's help, and particularly would request Debjani to become our ambassador and we will work with you in details. Thanks everybody, looking forward to a great conference.
Thank you, Professor, for your valuable reflections. With this, I now hand over the session to Professor Pawan Goyal from the Department of Computer Science and Engineering for the next key segment of today's program.
Thank you very much, ma'am. Thank you very much, Professor PPC and our director. We had a very exciting inauguration session, but it's just the start. So now we will be moving on to the 3 technical sessions. So the first session itself, as you can see, would have speakers from academia, industry, and research labs. And they will be giving you the state of the art that is happening currently. So without taking away time from them, because we are very, very short on time, and my apologies, we are only providing very strict 15 minutes talk, followed by 5 minutes of discussion, and I will be a little strict session chair already. I want to say sorry for that. So I'll read out the bio for the first speaker. So let me call on the stage Professor Anup Krishnan, who is the first speaker for the session. So Professor Krishnan is an associate professor in the Department of Civil Engineering, IIT Delhi, with a joint appointment in the Yardley School of AI. So Anup completed his PhD in civil engineering from, not able, this is fine? Okay. Yeah. So Anup completed his PhD in civil engineering from ISC Bangalore in 2015, after which he worked as a postdoc in UCLA from 2015-2017. He did his BTech from civil engineering from NIT Calicut. So he works at the intersection of materials, mechanics, simulations, and AI ML with the goal of accelerating materials modeling and discovery. So he's published more than 120 international peer-reviewed journal publications, has 2 granted patents, and he has won several awards, including Sir Pilkington Award by the Society of Glass Technology UK, Alexander von Humboldt Fellowship for Experienced Researchers, Google Research Scholar Award, and I can just keep naming those, including INAE, Young Engineer, Young Scientist Award. So yeah, without taking much time, Anup, over to you. Looking forward. Thank you. I'll show you whenever you have 5 minutes and 2 minutes left, and when you have 15 minutes over, I may come on the stage. Okay. Sorry.
Great. It's truly an honor and pleasure to be here and part of this symposium. I am Anup Krishnan from IIT Delhi from the Department of Civil. We have just had a renaming, so it's a Civil and Environmental Engineering Department and School of Artificial Intelligence at IIT Delhi. So when we think of this problem of materials discovery, I mean, we have had enough. Sorry, is it pointing to me? No, right? Yeah. So just by the way, just feel free to ask any questions if you have. I've not pledged that I will complete all my slides, but I would be more happy to engage with people than to complete all my slides. So when we think of this problem of materials discovery, typically the design to deploy periods is somewhere between 20 to 30 years. Okay, an example of that is this Gorilla Glass that you have in your phone. This Gorilla Glass was invented 15 years before the application of that glass was found. Okay, it was too expensive, so they could not find any application for that glass, and then they actually, I mean, Steve Jobs was looking for a particular glass that can be scratch resistant, and that's when they came together. There's a story to it. I don't have time to go into this, but they came together and found an application for it. So typically in materials discovery, a very small percentage of materials get discovered, and an even smaller percentage of that gets commercialized or applied. So how do we really look at this particular problem is what we've been thinking of for last less than a decade or so. And of course, with the advent of data-driven modeling, now you can actually think of it in a completely different fashion. And what we've been thinking of is from an end-to-end framework. Okay, so for example, if a person comes and says, I need the next material for this application, how do you go about this problem? What you need to do first is to go into the literature, get all the information from the literature about these materials, related materials, the synthesis pathways, the processing conditions, and create a knowledge base and distill this knowledge base to understand what are the spaces that you should be looking at, right? and come up with a few candidate materials. Once you have these candidate materials, what you do is simulation of this, because you don't want to directly go to the lab and make those. So you want to test them and then see in silico, test them in silico and then see if this works out or not. And that's where AI driven simulation comes in. And once you have that, then you go towards the next part of it, which is automated experiments or self-driving experiments or agentic experiments. It could be, all of these are different, have different flavors and are applied in different contexts, but all of this could potentially automate experiments. And once you do this experiment, primarily synthesis and characterization, the output goes back, and most probably you would not have discovered a new material, but the knowledge that you discovered in this process goes back, and the loop continues until you actually discover the new material and become a billionaire, right? So that rarely happens, which also tells us why material discovery is very difficult. There is one more aspect to this after this, which is industrial scale manufacturing. So we have been trying to look at all of these four pillars and then see how to put all of this together in a meaningful fashion so that we can accelerate discovery. So I'll give you one example of all 4 pillars that we've been doing and how it can potentially have some impact. So the first one was, when we started working on this problem, we realized that extracting information from text is a challenge. Okay? And to address this problem, we developed in 2022, one of the first material science language model in the world, which is called MathScibert. It's a very modest effort. We just took 150,000 research papers and then trained a masked word modeling on this existing Scibert language model. It worked well for the context. Now this work has been utilized extensively, more than 1 million downloads from Hugging Face and more than 300 citations for the paper. So it tells you that the level of interest the community has in such tools, right? But there is a problem. We developed this work in 2022, and by end of 2022, GPT came in and the work became obsolete, right? So then we said, okay, so let's try to evaluate if GPT is actually good for this application or not. And we created this benchmark called MacBench, which is materials and chemistry benchmark for evaluating multimodal language models. And what we did was, when we did this, we created completely new data, because all these models are trained on data in the internet. So what we did was, we did lab experiments, created data, and used that data to benchmark the models. Okay, so that means in some sense this is completely new data, around 1,500 questions. And then whenever we were having plots, we remade all the plots in our own format and made sure that they are different from how it is presented in the literature, etc. So due diligence was done. And then we also took some photos of the laboratory experiments. For example, a person taking sulfuric acid and then pouring it into a sink, and then ask the question whether is it a safe action or not, right? Because we are saying that language models can be a tool for safety, evaluating construction safety, evaluating lab safety, etc. But then we should have a sense of whether they actually understand whether some actions are safe or not. And the outcome was very interesting, and this is a published paper, so you can again go and look at it, the details. None of the language models had a performance gain more than 50% to a random baseline, okay? So if you ask simple questions like, what is the viscosity of the fiber at temperature 2073, a question human will be able to instantaneously answer if you show the plot, language models were not able to do it, right? So there are several challenges that needs to be addressed to make it useful. They are good, they are, they are useful, but they are not truly reliable is the only point that I am trying to make. And to address this, what we did was, we developed a language model for materials. This is a much larger effort than the previous one. What we did was, we took around 6 million papers from literature and then did continuous pre-training of a Llama model, and then developed this model called LaMAT, which is large language model for materials. This is also available in Hugging Face, so if you are interested, you can have a look at it. This paper is also accepted. But this had much more tasks in it. So we created, large data sets for instruction fine-tuning of this language model, which included OpenORCA, which is publicly available, but something like, Maths NLP, MASCA is basically material science question answer, and things like that. And evaluated it on 42 tasks related to material science, okay? And the tasks are given in detail in the paper. But the outcome was quite interesting, that we were able to, substantially outperform general purpose language models on material science tasks, okay? And it's important, if you ask me, is this model as good as Gemini? No, it's not as good as Gemini GPT or any of those general purpose model. But for the context of materials, it does have much better understanding and give you much better results, right? Which is also pointing towards the fact that maybe small language models fine-tuned for a domain is the way to go, rather than trying to make a general purpose language model which will work for everything, which will also incur much more cost for you, right? And more interestingly, we also had a crystal generator from it, which is Lemaitre-Sif, and we were able to generate crystals from it. I would not call crystal generation materials discovery. There is a difference, large difference between crystal generation and materials discovery. Crystal generation is basically just generating a few crystals in computer. It does not guarantee that those crystals are meaningful. It does not guarantee that the crystals could be synthesized. And even if it is evaluated from DFT or any other quantum theories, it does not guarantee that it is a scalable material that we have produced, right. So, there is a distinction between crystal generation and materials discovery, just wanted to make it clear. But the interesting part is, once you have a language model, it enables both conditional and unconditional generation. That means you can ask it to generate a crystal, but you can also ask it to generate a crystal having silicon and carbon in it, having a density of this and having a lattice parameter of this, because it is just taking English language instructions. So, just like you ask ChatGPT to write a recommendation letter or write an email for your supervisor, or whatever you ask it to do, you can now ask it to generate a crystal, right. And this was quite the interesting part of this work. The second thing that we tried to do was extract information from table. Again, it is a published work, so I will not go towards this, interested people can look at it. But what we understood was, when you look at table as a structure, and especially material science tables, this is very, very different from conventional tables that you see, because you will have composition, you will have properties, some of them are written in a single row, some of them are written with an equation, and all of those challenges. And what we tried to solve some of those challenges, and here is the again performance of Mathscraft, which is the model that we developed for extracting information from tables. What we see is that again developing domain specific models helps us in extracting more meaningful and accurate information from tables than using GPT and things like that. So, now we have a database which is compositions that are extracted from table. We have a language model that understands material science, and this is probably the way to go towards the first step of materials discovery, where you combine this language model with the knowledge base that you have and then ask questions, let it debate whether extract information, let it debate on whether the extracted information is meaningful, etc., and then ground it up on the synthesis and testing conditions, so that we can potentially start predicting new materials. Okay, so with this I go towards the second part of it, which is simulations, right. Once you have these candidate materials, how do you really do meaningful simulations? And simulations are one of the challenging things to do, because like the previous speaker said, discovery is an important part of simulation, in the sense that we should be having accurate interactions. It could be intraatomic potentials, it could be a functional density functional that you are using, but getting accurate interaction is very important to get any meaningful simulations. This is a trajectory of a molecular dynamics simulations. In the interest of time, I am skipping it. So, what we try to do is that purely from observations, can we learn interactions? This is the question that we try to ask, okay. For example, I have trajectories of particles, trajectories of colloidal systems, etc. Can we learn interactions from it? And what we see, for this we developed this system using something called Hamiltonian graph neural network, where we constrained a graph neural network with physics informed information, like it should respect momentum conservation, it should respect energy conservation, etc. And what we see is that once you do this, here is the predicted phase space of material, and here is the actual, and here is the energy and force that is predicted without training it on energy or force, okay. We are training it only on trajectory. That means it is almost like saying, you see how a human walks, and from there predict everything about the human, that particular human's capability, for instance, right. I mean, some sense like that. So, we are able to predict it by purely training it on trajectory, and we try to then take it forward and then try to really understand and get symbolically whether these equations make sense. So, we were able to recover it for very simple systems and even for binary systems, but when we went to more complex systems, it did not work. So, I am only showing the success story, but there are failure stories as well. If you are interested, please ask me. And we did it for silica and many other systems. So one of the ongoing work that we've been doing is called benchmarking of universal interatomic potential. So there are several of these universal potentials available, and this is another work where we have extensively benchmarked this universal interatomic potentials. So again available in archive. So if you are interested, please go and have a look at this UniFF bench. The last minute of my talk, I mean, I'm just going to skip these results basically, it's available in the paper. The only point I want to make is this universal interatomic potentials have a long way to go to be applicable in practical applications. The last particular thing that we wanted to do is on self-driving laboratories, where we have developed this thing called autonomous atomic force microscopy. So we have created an agentic framework where you can simply ask questions like capture an AFM image and get me the friction of this. And it actually performs this entire experiments. Do I get to play this? Yes. Okay. So basically here is a simple demo of this. We have now a much better interface for this. But what we did was we have an agentic framework which can interact with humans. So you can type in whatever experiment what you want to do, and it will actually create the code for it and then run the complete experiment, analyze the results, and then finally tell you what is the output of this. And to benchmark the system, we created 100 experiments and evaluated Claude, GPT, and many of these language models on it. So here you can see an example. It was completely performing the experiments autonomously. The scan is being completed. We just asked it to scan and then save the image. So it just completes and then finally saves the image, analyzes the friction, and then tells you the friction is the following. So what we did, when we did this, what we did was evaluate it on 5 different language models, sorry, oops. Yeah, 5 different language models, GPT, Gemini, Llama, Claude, etc. The interesting part was none of these frameworks, none of these language models as the backbone on the agentic framework were able to complete 100 experiments successfully. But a more concerning, so the best was GPT-4 at that point of time, which completed 80 of the experiment, which is a good success rate, but still not 100%. But a more concerning error that we had was called instruction adherence. That means these language models do not follow the instruction that you ask it to do. Sometimes it does beyond what you ask it to do. An example is if you ask the AFM to just move the tip down and touch the sample, it touches the sample, but it also completes the scan, saves the image. But we have not instructed it to complete the scan and save the image, right? And the other example is when we ask it to analyze an image. If it's not able to analyze the image, it starts searching for some software packages or tries to start installing some Python packages so that it can actually start analyzing this image. So these are some of the important points. I mean, I think whether AI will take over humanity or not is a large question, but I think there are several other smaller questions that are much more important before deploying the system. For example, if AI can corrupt your computer, that can have some serious consequences. Maybe not more serious than AI taking over humanity, but a much more serious consequence in the immediate future, right? So with this, I hope I have been able to kind of convince you that these 3, we can actually use AI for accelerated materials discovery and some demo of these 3 brief pillars. I just want to leave this slide with you as a thought as what is the next frontier, right? I mean, what are we thinking as a big vision? I think science gives you the unique opportunity to test a hypothesis, right? So you can have a lab experiment wherein once you give the hypothesis, it can actually set up the simulation or the experiment, get the feedback, and then see whether this particular hypothesis is right or wrong. And this is the best way to learn the world, right? Because humanity has been learning the world, about the world, through designing experiments, through hypothesis. And maybe material science could provide the next world model, enable development of next world model through this loop of autonomous experiments and simulations. And I think that's one of the frontier where it's not just AI for material science, but then material science could be for AI as well. Thank you, and I hope the stage is open for
Thank
questions.
you, Anuj. Wonderful talk, very exciting talk. We have time for at least 2 questions. Yes?
Hi, thank you for a wonderful talk. In your last slide, you already mentioned it, but I'll still ask. Can you, integrate these models with, more physics-based principles such as non-equilibrium, statmech, and things like that to predict emergent properties? For example, if you have soft materials which are responsive to electrical impulses, can you respond, can you kind of predict if they are piezo responsive and things like that? So these are more emergent properties, maybe not static properties. So I was wondering if you're in kind of planning to go in that direction.
This requires a longer conversation and setting up the context, but I can quickly try to give you a flair of this. So AI is only as good as the data that you use to train it, right? So you can potentially predict emergent phenomenon provided you have at least some sparse observations of those phenomenon, and you also know what is the underlying principles to a reasonable extent, okay, not to the complete extent. To give you an example, some area that we have been working extensively on is enhanced sampling, right? So for example, can you discover new phases, can you discover new particular configurations that are not seen, but by driving it towards those regions of the energy landscape that are unexplored, you know, things like that. So there are very interesting ways to do this, and generative modeling, for example, diffusion models and other models could be used for addressing this problem. So we can discuss about this if you are interested more, but yeah, you know, I have not touched upon that topic in this because it's, you know, too small to cover everything. So yeah, I did not, but thank you for raising this question.
Good morning, sir. My question is to search for a alternative for biodegradable plastic. How to do that with a fresh new laptop? How much time it take to?
Right. So this is a very active research area, by the way. So you should look at some of these papers that were published. One in, I mean, I don't exactly remember the authors. I can find the paper and send you. One was in Nature Nanotechnology, and the other was in Nature Sustainability, exactly on biodegradable plastics. What they tried to use was to actually create a closed loop system. And the reason why it's much more well defined for the context of plastic is because you can have these robotic systems that perform precise, you know, chemical reactions and then control it. So you can have this high throughput screening. So these robotic screening facilities are available. In fact, most of the shampoos that are designed by GlaxoSmithKline and many other things, they have a very, very nice workflow installed in this. It's completely automated. You know, no human does this lab experiment in their labs and then does this performance, does this discovery, right? So the challenge there is constraining the physical space, and you know, there are too many options that you have, and what would work and what would not is the space that one needs to look at, and this can be done very well by AI. So in summary, I think this developing biodegradable plastics is a very, very interesting area, and there is already active work and published literature on this area. So if you are thinking of an end-to-end framework combining this with a biodegradable plastic, I think that's a lot of potential and doable. Yeah.
So I think we would have really loved to continue the conversation, but given the time constraints, I request if the questions can be taken.
I will surely talk to you. I'm here today and
so
tomorrow.
All the speakers are thankfully
so
here for both the
me.
days.
Right.
So please make use of their availability and you can discuss a lot, right? So we again thank Professor Anu, very wonderful talk, and on the behalf of the workshop, we'll give you a small memento. Next, I'll call Professor Prasenjit Sen from HRI Prayagraj. So Professor Prasenjit Sen is a professor of physics at HRI Prayagraj. He completed his PhD from IIT Kanpur in theoretical condensed matter physics in 1997. He did postdoc at TIFR Mumbai and UIUC and many North Carolina State University. So he has been at HRI since 2004. He has worked on a wide variety of problems related to material science, including atomic clusters, 2D materials, materials for battery electrodes, materials for hydrogen generation via water electrolysis, design of rare earth free magnets, etc., using the first principles, electronic structure calculations. So recently he has been applying ML and AI to address some of the materials problems. So Professor Sen has been on the editorial board of Physica Scripta and a regular associate of the Adbus Salam ICTP Italy from 2012 to 2017. He's a member of the Materials Research Society of India. He also spent a year at ISER Tirupati, where he was a dean faculty. So we look forward to your talk, Professor Sen.
Thank you. Am I audible? It's a great pleasure to be here in this sort of unique meeting, and I thank the organizers for inviting me here and sharing, giving the opportunity to share some of the work we have been doing. And the fantastic talk by Anup just before me made my task a lot easier. So I'll talk about a specific problem on which we have spent some time over the last few years. It just went away this. Oh, it's there, okay. And this is a problem of great interest in the Indian context, accelerated design of rare earth free magnets. So I'll talk about the models, but more than the details of the models is the context of the problem and what can follow such design sort of efforts is what we should be carrying away. Okay, so yeah, so we all know that materials are all important for our technologies, and as Anup has highlighted, so the timeline from the discovery of a material to its full commercial utilization is decades. And the goal is to accelerate that discovery and deployment. And that is where we are trying to apply AI. The specific problem, it's magnets are everywhere. In modern technology, almost anything you can think of, anything that has a motor, the power generator, data storage devices, laptops, mobile phones, computers, anything, you need magnets. So magnets are everywhere, they are all important, and for many applications, in fact, all the applications and gadgets that I mentioned, the magnets we need are what are called permanent magnets. Now, what are permanent magnets? These are magnets in which the magnetization direction doesn't, flip around. They are fixed in a specific direction relative to the crystal structure of the material, which is magnetic. So these are called permanent magnets. And so why do we want to design permanent magnets without rare earths? See, most of the permanent magnets that are used are based on rare earth materials. If you remember your basic chemistry, these are the rare earth materials, the lanthanide series, and the most widely used materials are neodymium and samarium. And if you have been following the recent news, you know that there are geopolitical tensions related to these elements. And although India had a reasonable reserve, it's the third highest reserve of rare earth elements, critical elements, India doesn't have the capacity to sort of mine and produce these elements, not as yet. And most of the world is reliant on China. So that is why practically one is looking to go beyond rare earths. Now, why do rare earths are good for permanent magnets? Now, this whole effect is, if I go to basic physics, is related to an effect that comes from special relativity, and it is sort of proportional to the atomic number of the element, and because rare earths are heavy elements, they give rise to a stronger effect which causes most of these magnets to be permanent magnets. What we are trying to do is to build magnets which would have same properties, that is, they would also be permanent magnets, but they would not involve these rare earths. And specifically, the design targets we have is that they have to be, of course, stable materials, they have to have large magnetization, and the units in which one measures this is called Tesla. So they should have large magnetization, at least greater than 1 Tesla. And a phenomenological constant which is measured, which is used to measure the sort of tendency of this permanent magnet is called K1, the anisotropy constant, which has to be greater than 1 megajoule per meter cubed. And of course, it has to have large critical temperature so that it doesn't lose its magnetization. So these are some of the design targets one is after. Now, why is it difficult to find a new material, whether permanent magnets, anything for any application? The reason is that the chemical space of materials is huge. If you look at, ICSD or any other experimental database, for example, it contains, you know, of the order of 10 to the 5 inorganic materials. So I'm talking of inorganic materials, and if you sort of look at it or try to estimate it combinatorially, the total number of inorganic materials would easily be tens of billions of more. So therefore, in such a large space of possible materials, it is impossible to sort of do an exhaustive search and find out the one or few that would be appropriate for a specific application. So the whole question is how to search this space efficiently, and that is where AI comes in, AI or traditional machine learning. So traditional way of finding or designing materials, of course, has been experimentation, right? Trial and error experimentation, which is slow, expensive, uncertain, and so on. You could replace that by theory. You first do high level theory, quantum mechanical theory, and you only do experiments on the promising materials. You can go one step further, use your existing data to train surrogate models which would predict properties, so you don't have to do the expensive quantum calculations, and that way you screen out a set of materials on which you do experiments. So these paradigms are either theory driven or data driven, but they are traditional approaches in which you have materials and you predict or calculate their properties and then do experiments. What we're trying to do is to invert the question and ask, okay, I know what properties my materials should have. Now, can I design materials with these properties, which is called the inverse design paradigm. So given properties, we are trying to map it to the possible set of materials, and then the question is what materials those are, can one design and synthesize those. Yeah. So now I come to the two models that we have specifically designed developed for this purpose of rare earth free permanent magnets. One is based on variational autoencoder where you have some materials representation, you reduce it to a lower dimensional representation, and then you decode it to the original, this is the usual original idea of variational autoencoders. But then, and here the material is represented as an image. So I am not going to into the details of these technicalities, but anyone interested, I can discuss. In this context, we proposed what is called an invertible real space crystallographic representation, which is a very simple representation, pictorial representation of any crystalline material. And that is used as an image for this variational autoencoder. But then as it turns out, if you just train a variational autoencoder, the conditional generation of high magnetization or large K1 or whatever else you want is not possible. So we sort of conditioned it on the properties of interest, and the two properties we focused on are, of course, formation energy, which is basically tells me whether the material is stable or not. We want materials to have negative formation energy and large magnetization. So when we train this model conditioned on these properties, what happens is that the latent space is organized according to these properties. As you can see here, 4 classes of materials: stable magnetic, unstable magnetic, etc. These 4 classes of materials are nicely separated out in this latent space. And then what we used was we further constructed a graph structure on the representation of the materials in this latent space. So if we say we calculate what is called the similarity index between 2 materials, A and B, we used particularly the Tanimoto similarity index, and we set a threshold beforehand. If the similarity is greater than the threshold, we say there is an edge connecting the 2 nodes represented by the materials. If it is below that, then there is no edge. So that gives me a graph structure. And what we find is that in the graph structure, materials in the same class, for example, stable magnetic, there are many more connections between stable magnetic materials than between stable magnetic and any other class of material. So which again basically tells me that the latent space is nicely organized according to property. And then what we do is 5 minutes, great, I'll finish. So then what we do is See, the target is to generate materials that are stable and have large magnetization. So we pick up a point in the latent space that is a mapping of a stable magnetic material and perturb around that point, go to a new point and then decode it to a new material. And what happens is the way we perturb it is that this is the Z of the parent material, point in the, for the parent material in the latent space. This is a random number and this is a scale factor, and that's how we generate new points. As it turns out, if we change the scale factor, as the scale factor increases, the composition of the material keeps changing and you generate newer and newer compositions. So that way you can play with both the security of knowing that you are around a stable magnetic material, and at the same time, if you change the scale factor, you can go further and get new compositions. Well, once the new point is found, this target learning branches that was part of the conditional variational autoencoder tells me whether or predicts whether it has negative formation energy or large magnetization and so on. And finally, the ones that satisfy the design targets are calculated using density functional theory, the quantum mechanical approach. Now, what do we gain by doing this graph analysis? So that is what I want to focus on. If we do not consider the structure of the latent space, we just randomly pick up points around the stable magnetic materials, the 77% of all generated new materials would satisfy the design targets. Whereas if we consider the connectivity of the materials and say that I will perturb only around those materials which have 80% of their connections to be with other stable magnetic materials, that 96% of the generated materials was found to satisfy both the design targets. So therefore, the message here is that by understanding and exploiting the structure of the latent space, one can significantly increase the efficiency of materials generation with targeted design. Now, these are the two most interesting materials that we found with large K1 values, as you can see, and large magnetization. Okay, so this is impressive, but as it turns out, and this is a problem with all variational autoencoder based models, is that they generate low symmetry structures. So they don't understand the symmetry very well. So therefore, after that we trained a diffusion based model. As you know, diffusion based models are you just add diffusion to your existing data and then denoise them, and in the process you generate new materials. In the interest of time, I will skip this. So after we trained the diffusion model, we generated 1.3 million new crystal structures. We relaxed them to the lowest energy structure in equilibrium in the nearest point using two different methods, both DFT and machine learning force fields or universal potentials. And finally, we discovered or identified a few interesting materials which I will highlight these two. This is a simple oxide materials, and this is a material involving iron, nickel, silicon. So these are ferromagnets with large K1 and large magnetization and so on. And so remember that we were trying to design permanent magnets without rare earth elements. So these are examples of that. We also found some antiferromagnetic materials, and these are this. All right, so that is all fine, but then what is the road ahead? So these are two models that I presented to you for a specific design problem. There are similar such models in the literature. What is next? What is next is that integrating this material design with material synthesis, fast, quick synthesis, characterization of materials, testing of the material properties in experiments, and this integrating this entire workflow from materials design to testing through autonomous experiment is something that one should be aiming at in the next stage. And these are some of the people who did this work, and thank you very much.
Thank you very much, Professor Sen. So we have time for questions.
So you were perturbing the, what you told, you have a point and then you perturb and then choose. So can you tell me how smooth is that perturbation? Have you checked how smooth?
What do you mean by perturbation? Smooth?
Means the point, the property at that point and the property at the perturbed point, how smooth is that? Means it can so happen that the embedded space is not so smooth, so a perturbation can lead to a completely different sort of material space.
If you ask me in terms of properties, I can't answer that immediately, but in terms of composition, I can answer that. Can I have the slides, please? Oops. Well, it's taking time, but what I can tell you is that as I change that scale factor, the composition changes continuously, and continuously in the sense that if the scale factor is say 0.1 or 0.2, you would essentially get the same, maybe the stoichiometry will change a bit, but the elements would remain the same as the parent material. But as you increase it to say 1 or 1.2 and all the way to 1.8 or 2 we varied, the composition changes, newer elements come in, and so on.
Any other question? So I think we can thank the speaker again. Thank you, Professor Sen, for taking out your time. So on the behalf of the workshop, we will present a small memento. So we are moving on to the third talk of this session, just before the tea break. So let me invite on the stage Professor Gaur Prasad Das. So he's a condensed matter physicist cum material scientist, specializing in the field of first principles investigation of clusters, solids, and heterostructures with specific applications in material science and nano devices. His field of research includes alloys and intermetallics, 2D materials, semiconductor, spintronics, quantum structures, topological materials, and energy materials. He served in senior positions at BARC Mumbai, IACS Kolkata, he was at IIT Kharagpur, and he is currently an emeritus professor in the Research Institute for Sustainable Energy, RISE, at TCG Crest, Kolkata. So he has served as visiting scientist in several institutes, including Max Planck Institute of Solid State Research, Stuttgart, Germany, Virginia Commonwealth University, Richmond, USA, and so on. I can keep on taking names. So he's authored and co-authored about 200 peer-reviewed publications, review articles and book chapters, and also has a number of research programs that he has spearheaded nationally and internationally. So he has recently been honored with Lifetime Achievement Award at the Asian Consortium for Computational Material Science. So we are looking forward to your talk, Professor Das. And you can use the pointer. Thank you.
Let me first of all thank the organizers for giving me this opportunity to come to this very interesting meeting on AI for science and technology. Well, for the past nearly 4 decades, I have been working basically on computing in the field of computational material science, and in different institutes, in the Department of Atomic Energy, in the Department of Science and Technology, and more recently in IIT Kharagpur. And right now I am in this Research Institute for Sustainable Energy, and so I am going to talk about a specific application that we are right now involved in, but after giving a kind of a broad introductory things on how the DFT AI Alliance help us for computational design of the next gen smart materials. So, this is our institute where I am currently associated with, and our major focus is on lithium ion, sodium ion and all solid state batteries, and also particularly on the earth abundant materials for cost effective applications. We also work on hydrogen, on different kinds of catalysis, and of course for all these we need backup of computational and modeling, and more recently we have been involved in extensive AI/ML applications for these kinds of battery research. So let me So let me start with the challenge of the next gen smart materials. Where exactly do we stand as far as experiment, theory, computation and AI/ML is concerned? Now, as we all know that advanced synthesis, be it chemically guided or physically guided, and also characterization tools which may be diffraction, scattering, spectroscopy, microscopic tools which are available, but these are time consuming and labor intensive. We all know about the unprecedented growth of computer power from gigaflop to petaflop to exaflop, and still we are far from simulating really the realistic system with all its complexities. There is a remarkable array of simulation techniques covering different length scales and time scales. In fact, it was talked about a little bit by my previous speaker. And then the advanced computational algorithms based on classical, statistical and quantum mechanical laws. For example, density functional theory, molecular dynamics, Monte Carlo and quantum chemical tools, which are indeed highly accurate, but computationally they are very intensive and time consuming. The question is how to tackle this challenge of prediction, design and discovery of the next gen smart materials that quite often need long research and design cycle. The advent of AI/ML platforms suggested for prediction of material properties based on existing data sets from the data sets can be from experiments, simulation and or available databases are really today making a kind of a drastic change in the entire scenario, as you have already heard from different speakers before me. Now, the ML models trained on existing data provide rapid preliminary assessments. Only the promising candidate that needs to undergo more detailed analysis. Such integration of AI-driven approaches and high throughput computing such as DFT, molecular dynamics, etc., that leads to an efficient low cost materials discovery. Well, we all know about the different paradigms of in material science. We started with the experimentally driven paradigm, which is, we call it the first paradigm. The second paradigm is theory driven. The third one is computer simulation driven. The fourth one is the data driven AI/ML. And of course, today we have entered into the fifth paradigm in material science, which is knowledge centric, trying to seamlessly connect computational and data intensive paradigms. So we are really today in a era of cognitive computing. We are combining HPC high performance algorithms, deep learning approaches and of course human wisdom. So this fifth paradigm which is intersection in this Venn diagram is through this we are entering this new era of a well defined framework capable of promoting an unprecedented development in material science. So let us start with some examples of the next gen smart materials, and I have coined this word strategic priorities from what Dr. Debjani talked about just some time back. So a few examples, and I am a little biased because these are the examples on which I myself have worked in course of the last 2 decades, okay, with several students who did their PhD with me. So the graphene inspired 2D and quasi 2D materials and their van der Waals heterostructures, a very, very important area. Then the shape memory alloys and also high entropy alloys. lightweight, high strength intermetallics for aerospace as well as for nuclear reactor materials, topological insulators, quantum structures, and etc., etc. Then high ZT thermoelectric materials, and the last but not the least, in my own experience, that is the all solid state lithium ion and sodium ion battery, which is a game changer today in the renewable energy. Their application areas in fact cover a humongous thing, right from the clean energy storage to the defense applications. I do not want to go into the details. But today I am going to concentrate only on the last one, this one. Whatever time I have, I will talk about the batteries applications. So the motivation for our recent work on batteries is twofold. Number one, developing new electrode materials with high energy density and long life cycle. And better understanding of electrochemical properties via optimum choice of what we call descriptors. Now, when we probe the new materials for batteries, what are the bottlenecks and what are the possible solutions? So, we carry out synthesis that we do in our RISE lab, the research institute that I am here right now. Okay. It requires a significantly large number of off-stoichiometric compound. Remember that when lithium goes out or sodium goes out of the electrode, it becomes off-stoichiometric. And quite often we do by trial and error, although sometimes serendipity might come to one's rescue, but that is more of a luck than a rule. Then the complexity of the crystalline structures, for example, the solid state electrolytes, that requires inclusion of various kinds of vacancies, grain boundaries, defects, etc., which the material scientists are well aware of, but they are all inbuilt inside the sample. Then the computer simulation of a realistic electrode-electrolyte interface. This is the most treacherous thing. I mean, ultimately, the physics and the material science information comes from the interface, which is quite often it needs enormous amount of computational resource that are highly CPU and memory intensive. And so it quite often goes very high in scaling to n to the power 7, where n is the number of atoms in the unit cell. Machine learning protocols indeed offer fast, accurate and alternative to time consuming high throughput DFT calculations for predicting physical and chemical properties of battery materials. And many of you in the audience, you know, for example, Gerbrand Seder's group that works extensively on this, but that's not the only group. There are many other groups all over the world. Now, there is abundant and accessible machine learning database resources, for example, from shallow learning to deep learning, and that lower the barrier to its adoption in material science, cutting computational costs and shortening development cycles. So, we do various kinds of designs like structure-oriented design, element-oriented design, inverse design, which Prosenjit talked about just now in terms of the non-rare earth magnets. Okay, so DFT, MD and ML for next generation batteries and energy materials, what they can do. DFT can help us in terms of the structural stability estimation, in terms of cohesive energy, formation energy, phonon dispersion, etc. It gives us Gibbs free energy calculations for electrochemical reactions and so on. It analyzes the molecular orbitals, band structure, density of states, charge distribution, etc. and also it helps simulation of adsorption process. When it comes to molecular dynamics, as I think Anup talked about a little bit about it, time-dependent phenomena such as diffusion pathways as a function of temperature, transport properties, and ionic conductivity, very important, remember, in batteries, it is the ionic conductivity. And finally, how AI/ML can help. The available databases are there. I have only given a few materials project and so on, but there are others which you know. And once trained on the high quality DFT and experimental data, AI/ML can predict material properties with much higher efficiency, allowing rapid screening and vast chemical space. So the properties such as formation energy, chemical reactions, band gaps, battery voltage, that is what I am going to talk about in the next few minutes. And you will know the key methodologies in this field include deep learning, convolution neural network, graph neural network, Bayesian optimization, and so on and so forth. Okay, so let me now come to the example that I promised to give you, namely lithium ion and sodium ion. Now, lithium versus sodium is something which is illustrated schematically here. So ultimately, why is it that sodium wins a little bit over lithium, even though, as we all know, that lithium is today the reference in the industry. But still, we are going towards sodium because of various reasons. One of the most important reasons is the cost and the availability. Okay. So we, in our a combined work which we have done between our institute and IKST, we have developed a scheme by combining high throughput data, the fully connected deep neural network and selective DFT checks. Then this approach is an efficient and robust screen then validate workflow that significantly accelerates sodium-ion battery composition prediction, paving the way towards the discovery and optimization of advanced battery materials. It has just been published in Small Methods, okay, this particular work. Now the workflow is, the details is given of course in our paper, but the workflow of the FCDNN model architecture, that is the fully connected deep neural network, is given in this figure, where we start with the data retrieval, we do the various kinds of feature extraction, and then we do the deep neural network analysis, in order to ultimately our objective is to come up with what is the average voltage that we predict. Okay? So our focus on technologically important layered oxide cathodes for sodium-ion batteries, that is our ultimate aim. Can we really come up with the efficient sodium-ion battery? Now we proposed a series of new structures which is called O3 and P2 type NaMO2 compositions, where M actually is a mixture of the transition metals with promising voltage and satisfactory estimated stability. A lot of work has already gone inside this in the literature, but without going into the details, let me tell you that this O3 and P2, the two structures that I told you, for these two structures, we have predicted the voltage and their deviation. Both experiment and DFT calculations have been done and compared with the machine learning deep neural network prediction. So interestingly, the voltage prediction which we have done via the AI that agree with the full DFT calculation to within about 1 to 2%, and also with the experimental data for known commercial materials to within roughly 0.05 voltage on the average. And that is pretty good, I will say. Okay? And you can see how the matching, the excellent agreement in capturing the electrochemical behavior of sodium-ion materials. So here is a table. I don't have time to go into the details, but let me just tell you that the FCDNN predicted versus experimental, this is the FCDNN predicted numbers versus the experimental as well as the DFT voltages. Look at the numbers, okay? The numbers, in fact, I will say it has got a very reasonable agreement which we get, and at a fraction of a cost, much less than what experiment and DFT will give. We have done a detailed analysis, okay, various kind of descriptors, etc., and here is the D-band center, okay. I don't have time to go into the details about what is the D-band center, but it is there, the details in our paper. The D-band center trends and the electrochemical implication which we have computed, and as a function of voltage, we have plotted this D-band center for both O3 as well as the P2, and this is something which is done in details for our materials. So. So what are the take-home messages really that we have in this work? The take-home message. Now, integration of AI-driven approach and high-throughput DFT computation indeed leads to an efficient low-cost materials discovery, and is ready to take up challenge of complexity in handling the next-gen smart materials. In general, although I have given you example of only the sodium-ion batteries, but in general, this particular philosophy, this particular approach is hopefully going to be extremely useful. Second, the IKST RISE team our recent work, we have developed a unique that DFT plus DNN workflow that can accurately predict the operating voltage of battery materials, and that paves the way for faster discovery of next generation sodium ion batteries. Okay. Such AI guided design will be critical for bringing sodium ion batteries seen as a strong low cost complement to lithium ion technology. Remember, whatever you do, lithium ion still is holding the uniqueness of its, that it is the industry reference. But as you all know that the availability of lithium, etc., is a big challenge, and we have to really face this challenge. Okay, via AI route, that's what we have tried. Okay, so this this is something, this AI guided design is really leading us into a large scale use in grid storage, electric mobility, and also renewable energy integration. That is our ultimate goal. So we are entering into this new era of knowledge-centric cognitive computing that combines deep learning approaches with high performance computing like DFT. So this is the paper. With those of you, especially the youngsters in the audience who are interested, you can have a look at this paper, which is entitled Integrating Density Functional Theory with Deep Neural Network for Accurate Voltage Prediction in Alkali Metal Ion Battery Materials. And this paper is something which has just come out as a New Year 2026 dhamaka. Okay, and you see that the publication date is 1st of January 2026. Okay, and here is Shatodeep, who is there in the audience and who is going to be a speaker next. So our collaboration, the Shatodeep is in IKST Bangalore. So our collaboration between IKST Bangalore and our RISE lab in Kolkata, that has led to this thing. And I am proud to tell you that this is coming out in as a recent news item, that smart AI finds smarter sodium ion batteries. Okay, cheaper and sustainable. So the IKST RISE team has shown how AI can actually speed up battery materials discovery, not just in principle, but in practice. So this is what is the news item. So with that, I'll stop. Thanking you for your attention.
Thank you very much, Professor Das. Wonderful talk. We have time for a question. Yes.
Yeah.
Thank you, sir. It was quite an insightful lecture. So in your lecture, you have mentioned about this AI-ML Alliance for computational design of smart materials. Would you kindly comment on the computational design of structure material also, like design in the sense of compositional design as well as process design? The structural material meaning titanium alloys or nickel-based superalloys?
I couldn't really.
Can you just speak?
Okay. Can you hold the mic?
Yeah. Now is it audible?
Yeah, tell me.
Sir, you have mentioned about the computational design of this smart material. Would you kindly comment on the this computational design of structural materials like high temperature materials, titanium alloys, where the compositional complexity is much more, and design as if compositional design as well as process design?
Yeah.
Thank you, sir.
Yeah. So a good point. I didn't have time to discuss. See, for example, let me just give you one example. In aerospace, you need to have a lightweight and high strength material, which all of us know. But one of the biggest challenge is ductility. I mean, there are metallurgists here in the audience, they know the ductility is as a function of temperature. It's a big challenge. So what we do is that we try to explore how, by a very small addition, for example, of niobium in, say, lithium, aluminum, nickel molybdenum alloys, it is possible for you to increase the ductility by orders of magnitude. Now, here the chemical space, as we call it, is something which can be probed via AI. It is still, the work is still not complete, it is going on. But AI can tell you that, okay, how, as a function of the concentration of that particular third element, which we can call it a ternary this thing, how it is possible for you to really enhance the ductility. Because if you do not have ductility, then your aerospace will break, you know, you don't want that. So this is something which is going on, but I can discuss with you the details later, yeah.
Thank you very much, Professor Das. In the interest of time, we will just break for the tea now. Before that, let me hand over a small memento from the workshop. So we'll break for tea, but we have to come back exactly at 11:10. So we will have 4 more talks in this session. So 11:10 we'll come back and start with the next talk. 12:10, I'm sorry, 12:10. 11:10 is gone. 12:10, yeah. We'll come back at 12:10. Thank you.
एक्चुअली नहीं आ रहा है.
This is the thing.
So we have to orient it this side, right?
No, no, no. It works.
Anywhere it
Anywhere
works?
it works.
And the laser also works or
Yes,
not?
yes.
Laser will not work there, right? It's very
No, no,
faint.
laser will work.
Oh, very faint. Okay.
Ah,
Yeah,
yes,
it's very
good.
faint from laser. But it's at least something.
Thanks everyone. So we had a very short, but I hope engaging tea break. So we are ready to start again. So we have 4 more talks from industry speakers, research labs. So I'll be starting with the first. I'll introduce the first speaker, Dr. Foram Thakkar from Shell. So Dr. Foram Thakkar is a senior researcher at Shell. Since 2012, He has worked across the energy spectrum, from molecular modeling of complex fluids and catalytical materials to porous media, membranes, electrochemical devices, and system-level optimization. His current focus is on advancing multi-scale modeling by integrating physics-based approaches with AI-driven methods, aiming to combine physical rigor with data-centric flexibility for reliable simulations at scale. He has earned an MTech from IIT Kharagpur and a PhD in chemical engineering from ISC Bangalore, completed postdoc research at MIT, and previously worked at Samsung Research in Bangalore. So we are looking forward to your talk. Over to you, Dr. Furam Thakkar. Slides and you can slide changes, which here. Just see if you can, if this one should work. Yeah, and I'll just show you 5 different things.
Hi everyone, am I audible? Am I audible? Am I audible now? Yeah. Thank you, Professor Goel and the organizers for inviting me to such a nice workshop. Is it better now?
ABCL गड्ढा को बैटरी चेंज करते हैं.
Yeah. Thank you, Professor Goel, and the organizers for inviting me to this event. Okay, yeah, so assuming that coffee has kicked in and people are awake, the slides are done. And we've had quite an engaging session starting from Debjani Ghosh and following a very nice, very engaging sessions. This is going to be a slight shift from what we have seen in the morning, where we focused more on large language models, generative models, and the more newer trends. This is going slightly back, looking more into more established MLs and trying to see how we can make use of that into more, so more engaging workflow, something that can deliver value as of today. So that's going to be the focus, and the focus of the talk as a subject is the materials that are relevant for energy transition. Shell is an energy company. An energy company is, in today's world, generally responsible for putting a lot of carbon out in the world, and it's the carbon in the form of CO2 that is the main culprit of the energy related problems that we are facing in the world today. So I'm going to take you through the journey of where in the value chain of the carbon this kind of energy transitions materials play a role and where we do something. Okay. But before going to that, I am legally required to show you a very small fonted slide okay, now this has stopped. This has, yeah, it has, okay, yeah. It wasn't, it has become very slow. So now it is working fine. Yeah. Okay, yeah. Sorry, apologies for that. So the slide basically tells that do not make your investment decisions basis what I say. I am legally required to show this slide before I commence my talk. Once we can go past this. The focus, as I was talking about CO2, that's the key molecule that is creating the problem of today. And the main problem with CO2 can be addressed by doing major aspects that are capture of CO2 that comes as a point source capture or a direct air capture, but also we have to figure out what can we do with the CO2. We can capture, collect all the CO2, transport it, and then put the CO2 either back in the ground, that's a storage, or under sea or somewhere else. Or we can start figuring out how to use the CO2 in a more meaningful way and create a circular carbon economy. So that's the focus that we wanted to address. And if we start looking at how to make this CO2 as the building block for the future world, that's where the carbon value chain that comes, where CO2 is the critical feedstock. At this point, people might start asking questions as to what has Shell got to do with this, because most of these problems are materials problem, and Shell is an energy company. What does Shell do? So the answer is nearly everything, be it the parts where CO2 capture comes with, be it part where utilization comes with. Utilization also inherently involves converting CO2 into something else, so that indirectly links with catalysis. And wherever you are involving flow of material, CO2, other reactants that are associated with CO2 or any other reactants in general, corrosion also plays a big role. And all of these processes we expect that will be driven by renewable energy. So the materials for renewable energy themselves and the storage that you would require along with it would also play a big role. So in essence, Shell has got everything to do with in the entire material value chain. The same perspective on a slightly different way is put up this way. So you basically get CO2 and water from the environment. You convert the water via electrolysis, make hydrogen. You use the CO2 to some extent, reduce it and make it CO. These are the main building blocks of the future material, they being chemicals, value-added products, intermediates, or even future fuel molecules. That's the syngas or the CO and hydrogen mixture is going to be the base of everything that we see today. And to do this, we have to supply renewable energy, and renewable energy is not available 24/7. It is intermittent as the sun rises or falls or as the wind cycle moves. So we do need a storage, some or the other form of storage. So for the first part, we'll focus on the energy storage and how we do the molecular discovery or materials discovery in that part. And if time permits, we will look at one more example of doing CO2 reduction process. Sorry? Yeah. Okay, so if we want to deploy this kind of materials at a gigantic scale, at a really large scale, we need energy storage devices that are also operating at that kind of a scale, something that can basically feed the entire plant. To give a context, the complete petrochemical refining plant along with the chemicals building unit would easily consume power that can basically power a small village. So that's a huge amount of energy requirement, and current state of the art, what we know lithium ion batteries or upcoming future sodium ion batteries are not at this stage where they can do massive giga scale storage. Okay. So we have to look beyond these two. And one of the answer is the redox flow batteries, where you basically scale the amount of energy storage required by simply scaling the tank of the flow materials that is circulating along the side. So that's the idea. What is a flow battery? Yeah. What is a flow battery? Basically, flow battery is something where you have two tanks with the cell that converts the energy, either charge or discharge, and the tanks basically have something that will release or store electrons in the energy format. So in this particular example, what I am showing is different kinds of quinones going through the cycle. That's essentially the idea, and we are looking for newer molecules, newer materials that are more efficient at doing the same process. So what are we looking for in the material is this, that it has to have a small size to basically that helps higher charge to weight ratio, it has to have a faster kinetics, because we want the batteries to instantly kick in and give us energy when we switch it on, not really after 5 minutes. Okay. It should also have a suitable redox potential. The higher the redox potential, basically it translates to higher power. That really helps us. It should be higher water solubility, because the material is typically dissolved in water and circulated. It should have a good stability, as in it should not oxidize or degrade with time, because otherwise we will have to replace it, and that also adds to cost. Overall, the material itself should have lower cost and higher availability, and we want to discover this from plethora of organic molecules that are out there. So ideally we have to figure out how to do this, and all we know is that we know some amount of structures, chemical structures, like we know that quinones and aziaromatics, for example, work. But how do we tell computers that this works and this is what we want to search for? So that's where some of the descriptors come in. So we know that these are only organic materials, so it has carbon, hydrogen, oxygen, nitrogen, and sometimes sulfur. Rarely heavy metals will be there, rarely any other elements will be there. So we could apply elemental filters. We could then translate some of the materials some of the properties that we could easily compute. For example, we could easily compute the energy of this reaction, the transition reaction of charge or discharge. But it's not straightforward to get to the voltage. But then we have seen via different kind of models, typically ML models, that these two correlate very well. So we use some of these information packed together and put it in a discovery platform. Make this as a workflow. So as a workflow, we start here. We take the published chemicals database, which has roughly 112 million entities. Start doing filtering, start figuring out what are the redox active substitute structures that are the key to this whole reaction. Get to the structural similarity that reduces from 112 million to all the way to 229K. So that's the significant materials that we have discarded, made the search narrow. Go from there and start putting the filters that we have designed, that is, for example, the reaction energy and the voltage that we talked about. There is yet another filter that was similar, that was on the solubility level, because we mentioned that solubility is important. So that was again a solubility model that was designed on experimental data, not on a computed data, but the same filter was applied. At the end of the solubility, we got 678 molecules. So significant down selection all the way from here to here has happened. Now we apply the availability filter. So first was the price. We don't really want a high cost material, so we put a available price indexes to the material, get down to about 200 such materials, and when we start applying the availability from the vendors, the material number goes down to roughly 67. Yeah, and we could do that entire workflow from 112 million to 67 molecules in roughly 1 month of time, entirely on a laptop. So this whole thing has been now designed as a web app. It's called RedCat. It's published here. The work entirely was done by Dutch Institute of Future Energy Research and PTG Eindhoven. That, and I wanted to touch upon the CO2 reduction, but I guess there is very limited time, so I'll flash only a couple of slides there. So CO2 electroreduction is a thermodynamically possible but kinetically very, very stubborn reaction to play, and the catalysis does play a quite important role there. Yeah, and so what we know is that it's not the catalysis alone, but it's also a role of the environment, role of the solvent or the electrolyte, that also is important in establishing the reaction mechanism. So that we know, and how do we utilize that in framing the workflows? In the interest of time, I'll skip the slide. This is how we do things in a traditional way, which is very time consuming. The same thing can be established in a workflow where we basically take late transition metal database and put D-band characteristics as their main descriptors, and binding energy of CO is our main key KPI. We put machine learning models. In this particular case, we have developed a particular algorithm along with JNCASR that's called bootstrap projected gradient descent method. That is what we have used, and once we have that, we come back to the results. And after doing the same exercise for the CO2 reduction, what we saw is that the predicted property versus the actual property has a fairly decent match, in this case the property being CO binding energy, and the filling of the D band was the major indicator, and it indicates that the alloys of gold, copper and silver are the main catalysts that we could use. Now this is not entirely unknown per se, but this kind of serves that you do get something that is scientifically tested in the past, something that is reliable, trustworthy, and we could use this forward for something where we do not really know much. So this kind of serves as a benchmark for ML to be valid in the space of catalysis. Yeah, so that is where I will stop. I will thank my collaborators, thanks my colleagues and our supervisors for giving us the result. Yeah, thank you.
Thank you very much.
I think that is stop.
Thank you very much, Dr. Thakkar. So, very interesting talk. Yeah. We have time for a question, one or two questions. Yes.
Thank you for the interesting talk. I have a question on the CO2 adsorption. So you talked about various organic molecules which undergoes a redox reaction particularly.
CO2 or the redox reaction?
Redox reaction, sorry.
Okay, yeah.
So there are inorganic materials which also undergo redox reaction. So you have only shown the organic materials. And the second question is how to scale up these things.
So the organic molecules, the reason we wanted to look for organic molecules is for easier scale. Because organic molecules you can get, and if you do have this carbon neutral pathways, it's a journey towards carbon neutral pathways, but once the carbon becomes available, you could make different organic materials easily compared to, say for example, vanadium based pathway for redox flow batteries. That is always going to be limited by the supply chain of vanadium, and something that happened with lithium. If that happens with vanadium as well, we are back to square one where we started. So that's basically the reason to look for organic material that makes it more ubiquitous and easily accessible across the globe.
Thank you.
Thank you very much. Is there any other question? So we thank again Dr. Thakkar for taking your time and very interesting talk. I'll request a memento from the workshop.
Thank you.
So we are moving to the fifth talk of the session. So it's a pleasure to invite Dr. Chandan Chaudhary. So he's a computational chemist with expertise in quantum and molecular simulations, as well as AI-based drug and materials discovery. So he earned his PhD in computational chemistry from CSIR National Chemical Laboratory, Pune, and subsequently completed postdoctoral research at Clemson University, USA. Since 2020, Dr. Chaudhary has been an integral member of Prescience in Silico Private Limited, Bangalore, a deep tech enterprise focused on expediting drug and materials innovation through artificial intelligence, machine learning, and physics-based multi-scale simulations. In his current role as manager of the material science R&D, he leads the application of computational methodologies of the design of advanced materials encompassing alloys, polymers, formulations, and sustainable solutions. Dr. Chaudhary has authored 20 publications in peer-reviewed journals with robust training in computational chemistry and extensive experience on both academic and industrial fronts. He is dedicated to advancing computational tools that drive meaningful progress in material science and pharmaceuticals. So looking forward to your talk. Over to you, Dr. Chandrachal.
Thank you, Professor Goyal, and thank you, committee, for inviting me. So I am basically from Prescience in Silico Private Limited. It's a Bangalore-based company. What I'll be talking here basically about the agentic front capabilities that we are developing in-house. So before I go into the details, I will just take you through what we do as a company. So we basically cater to materials, chemicals, pharma, FMCG, and all these sectors. The idea is to build a sustainable world through our technologies in this space, and doing so we use innovative and physics-based method to build a better world. What we work on: food and beverages, energy, oil, lubricants, paint, dyes, polymers, personal and home care products, and also in drug formulations. I would also like to add here that we are the first, we are one of the company, in silico company, which has end-to-end drug design and screening protocol. So where you can screen a million compounds at one go. So this helps us to reduce the experiment time, the bench experiment time. We have developed various in silico technologies in-house, like we have digital hair model, digital skin model. We also model enamels, saliva, and we also have this digital formulation tool where you can predict the stability of any formulations which are used for personal care or home care. We have also developed products. Prince 3, it's a drug discovery platform where you can screen millions of compounds for target. We also have generative AI based platform for drug discovery. But in this session, what I will take you through is the scientific agent that we have developed. It's called Aura. So when we talk about agent, we come across agent in a various day-to-day lives in various forms, like travel agents, insurance agents, real estate, and so on. What I'll be talking here, and which the audience can relate it to the agent, is called scientific agent. So the problem what we have in hand is any company client can come to a SMEs or a scientist or a PI with some sort of problem statement, like I have a surfactant which I want to generate a list of surfactant which have this properties. How should we go about it? So scientists would go and do some work in the lab and then come up with some solution. Yeah, so the talks that goes in the background, and with that it comes with a list of probable compounds which satisfies the client constraints, client conditions. So what goes in the background is the PI transfers the problem statement to the project manager. Project manager can be a postdoc. So what they do is that they define the project, design the project, define the tasks, assigns various teams and team members. So this is the how the PI or the manager would further split the work. They can create a team which are specialized in cheminformatics, bioinformatics, biology team, or a MB team. So what I'm trying to show you is that a big chunk of problem statement is being distributed to various teams, and each of these teams are capable to work on these problems, and at the end the professor gets the desired list of surfactants was the client was looking for. Now when we talk of an agent, so these things can be orchestrated as an agentic form. Here the PI or the manager becomes an orchestrator. He orchestrates the problem statement to a router agent. A router routes the problem to various specific domains. These are called specialized agents or worker agents who does the work, transfers the data back to the router agent, and followed by the orchestrator agent collects the data, filters them, and gives the output. So the idea here is to connect the scientist with the scientific agent, and to do that we have our platform called Aura. So Aura is basically an agentic AI platform which has a beautiful UI. It hits various LLM services, uses cloud computing, and it is basically a domain specific solutions for any given R&D problem. So what is this agent can do? So it can perform scientific studies, complement scientists, speeds up the R&D process. So it helps to create knowledge in setting up and running those talks, analyzing and reporting back to the manager. So here basically we go to the knowledge base databases, and from there it curates and the requirements based on the problem statement, and it runs specialized agents to perform those talks. The agents can be quantum calculations, classical MD, or continuum mechanics, and from there the data is gathered, analyzed, presented, and a report is generated. So this is whole the agentic platform is all about. In doing so, we have a research agent which does all the research activities, goes to the database, gets the information, then it connects it to the MD agent, followed by chem agent, and also if required it can do quantum calculations, and this platform also has a capability to bring your own agent. We can patch it up and the workflow can be followed. So the problem statement we are looking here is to in a home care unit where we have some surfactant molecules, and the idea is to remove dirt from the fabric. So how would one go about it? So the idea is to first have a research agent work on the problem, go to the database, collect those molecules, compounds, surfactants, and validate those information. Thereafter the setup agent kicks in, it screens the database, setups the condition, and generates a workflow for the simulation agent to carry out the simulations, and the analyze agent and the report agent would further come in to analyze the output result and generate the report. So here what we do is that we basically have LLMs, and we also have domain specific small LLMs which does this work. So we have various agents. These all the tasks are being performed in a containerized environment suited for those specific tasks, and these containers, the tasks are the high end tasks are run on HPC cloud. So this full workflow we have incorporated in Aura, our agentic AI platform. So here I will show you a small demo to show how this agentic AI performs. So we have, so the problem statement where we are looking at is to simulate a surfactant in water. So what happened is that I have uploaded the surfactant with the required force field files, and the Aura we have given some prompt to with some constraint that I have a specific weight percent of surfactant that I am interested in, and since this is a MD simulation, I have also constrained, okay, I do not want to go beyond 10,000 or say 20,000 atom size. You can go beyond that as well, that becomes computationally expensive, but here I just want to show the concept behind how Aura functions. So this is then with the prompt, the Aura plans whatever constraints is been given, and it sets up the simulation box. And then it will run all those software specific workflows one by one automatically. What I also want to mention here is that Aura is capable of following the workflow, and also if there are some errors, Aura can rectify it. Here I would like to show you that there was a mismatch in the topology. Aura got that error, and then it has rectified the topology all by itself. So here there is no human interruption. So thus it reduces the time. So the only human comes in the picture when we have to approve the delegation. If the workflow that's been presented by Aura, do we approve it, then it goes one by one and it does it follows the workflow. So once your simulation is run, we can the Aura platform has the capability, we can visualize the trajectory, and we can see that the surfactant molecules in water with those constraints been given, the Aura is able to simulate it, and we are able to visualize them within the platform. So this all good. So we are able to run this simulation in an automatic fashion with almost zero human intervention. Though we need human in the loop to approve the delegations, to approve the workflow. That is very important process. So that's where the human comes into picture. Otherwise, everything is automated. So once the MD simulations is run, we look to analyze the system. So we can give a prompt to, okay, we have this simulation run. Can you analyze some quantities, some meaningful quantities for us? So here what it does is that the prompt is to analyze the diffusion coefficient of SDS molecule in this simulation box. It analyzes, it does the calculations, calls the GROMACS agent or calls the analysis agent, and it analyzes the trajectory. We can also visualize the plot there. So Aura has both the capabilities of doing the simulation, visualizing the trajectory, visualizing the plots. This is all about Aura I want to share with you. So this is a preview version. If anyone is interested to use the platform, please reach out to me. We'll be very happy to share the platform with you all. So thank you, and I'm happy to take any questions.
Time for some questions. Anybody any questions?
Yeah, thank you for the talk. So, so this Aura is a simulation framework.
Not exactly, but now it is capable of doing a simulation. It can also do QM calculations, and also those DFT calculations can also be done. So it basically depends on the containerized module what we have there. So as of now, we can do DFT studies, MD studies as of now. Yeah. But it is still in the developing phase. We'll be adding a few more.
So what does the agent exactly do?
So agent basically it orchestrates your problem statement. So you give a prompt that I want to simulate a surfactant in water for application. So agent would go to the database, looks, let's say you have not given the name of any surfactant. So it will go to the database, and the knowledge base it has. It will extract those surfactants that's been studied, and it will come up. It will give you a list of surfactants which you are interested in. So basically, you have list of surfactant. Then it's your call. That's human in the loop comes into the picture to decide which surfactants you want to go ahead with.
Very nice work.
I know.
So I was wondering, you know this also well, that for different systems we use different force fields,
yes,
different data sets,
yes,
different simulation packages.
Yes.
So you're talking about surfactants, for instance.
Yes.
But if you think of, let's say, alloys, we might be using LAMPs.
Yeah.
If you are, sometimes people use GROMACS, NAMD,
yeah,
depending on biological systems, etc.
Yeah.
So are you looking at only one family of materials right now, or can I basically ask for any simulation that I want? And that's one question. And second is the level of complexity. For example, I'm interested in doing a scratch simulation. You know that it requires, for example, a creation of a slab, equilibration of it, creation of a tip, moving down, and then doing a simulation of scratch. So this requires a thinking of how the simulation itself should be performed, right?
Yeah.
So these are the two questions. Is it generic to all material families, simulation packages? Second, how complex orchestrations can it plan and do? And again, I'm not asking about scientific hypothesis generation and evaluation, just simply setting up the workflows and running.
Yeah, so currently as of today, it is mainly confined to this surfactant, but it's not limited to. We have the idea in the pipeline to have lamps also involved there. So yes, we are going to explore all the length and breadth because that's why we cater to various FMCG physics companies. Yeah, so the idea is to go beyond what we have and build up further. And coming to your next second problem is to how to build slabs structures. So that's a very tricky thing you have mentioned. Thank you for that. Yeah. So since it's a knowledge base, it extracts the data what is already been trained with. So if it goes beyond the capability, then of course the human in the loop comes in the picture, and it try to assist the agent how to go about it. Okay, thank you, Anupam.
Very nice work. So my question is, in terms of analysis,
yeah,
can it do system-specific analysis? For example, I understand it can do generic analysis, for example, MSD or maybe RDF, but let's say I want to compare two surfactants and their after simulation, what is happening to our chemical environments.
Yeah.
And then the agent needs to figure out the atom names, the water models, maybe all those chemical details.
Yeah.
So can it do that?
So these chemical names and all this all will be taken care of. That is that's not an not a concern. But coming to your different sets of analysis, I would give you an example where we have just thrown the prompt that I have not given anything, I just asked him to, okay, do me a simulations. I have not mentioned the time frame. So what it does is that the Aura could simulate it a few nanoseconds, and since it was a surfactant, it decides by itself to compute the number of clusters in the box. It says that, okay, there is no cluster formed yet. It has to run again, run it longer, right? So it orchestrates by itself that it then ran it longer. This is one thing. And second thing is coming to your analysis. Yes, of course, we are limited by analysis because it depends on the knowledge base, and if they are, and we have been doing like research where you have to write your own code that is not already available, then the human in the loop comes into the picture. Yeah, thank you.
Thanks again, Dr. Chandan Chaudhary, and very nice discussions. So in the interest of time, we will thank again and give a small memento from the workshop.
Thank you.
So we are moving on to the next speaker, Dr. T. Umashankar Patro. So he obtained his MSc Chemistry from Berhampur University, MTech in Materials Technology from erstwhile IIT BHU, currently IIT BHU, and PhD in Chemical Engineering from IIT Bombay. Subsequently, he was a Feinberg postdoctoral fellow at Weizmann Institute of Science in Israel from 2008 to 10. Currently, he is working as an associate professor in the Department of Metallurgical and Materials Engineering in the Defense Institute of Advanced Technology, Pune, DIIT Pune. So he has published around 70 international journal papers, including 3 book chapters, and has 2 patents granted. His research interests include the development of polymer nanocomposites for EMI shielding, environmental remediation, and biological scaffolds, structure property relationships in polymer composites, polyurethane synthesis, AIML for material property prediction, and polymeric and carbon foams for acoustic insulation and energy storage. So looking forward to your talk, Dr. Patro.
Thank you, Professor Goel, for the kind introduction. Can you put on the slides, please? So I thank Professor Ganguly, Professor Kaustubre, and the team for giving me this opportunity. So today I am going to talk about a machine learning approach to predict properties of elastomeric polymer and polymer derived carbon foam, a different realm than what you have heard today morning. So I come from Defense Institute of Advanced Technology, as mentioned. It is a DRDO funded, Ministry of Defense funded institute. We are particularly postgraduate institute. We work closely with DRDO on various defense activities. So today I am going to touch upon 2 themes by asking question, can machine learning predict the elastic behavior of elastomeric polymers? This work has been done in collaboration with Professor Hari Krishnan of Chemical Engineering, IIT Kharagpur, in this institute. How precisely can the machine learning algorithm predict the properties of carbon foam? So I am going to talk about a little bit about carbon foam. To start with, elastomeric polymers are a large class of family in the polymer, and they show varied chemistry, such as they could be thermoset, thermoplastics, they could be unsaturated, saturated, and they display wide range of properties because of their chemical structure, different chemical structure. So one common property which define the entire class of material is their mechanical property. They exhibit a large recoverable state. So to understand, you can see over here, this is how they look like in a relaxed state. So these are like entangled chains, long chains, and then connected with these crosslinks, these black dots. So something which crudely resembles to Maggi and Mutter, green peas. And then when you apply stretch, when you stretch or apply load, so they will align in the direction of applied load, applied stress, and then when you again unload, they come back to the original position without breaking any bond. So these dots act as a memory points, so that makes them bring them to the original shape. So the stress strain behavior is quite sensitive because of this kind of chemical structures, quite sensitive to the chemical structure like cross-linking. Therefore, prediction of elastic behavior of such materials is very important for the current application as well as the designing new elastomers. Elastomers find a large application areas starting from a simple rubber band to tires, biomedical catheters, and then you have aerospace, construction, automobile, so on and so forth. So to illustrate how the chemical species influence various properties in polyurethane elastomer, here in an example, so by having a disulfide bond and a di-Alders reaction, which is a reversible bond which breaks and forms, and then when you have this kind of species, it gets self-healed, and you can see over here it gains its mechanical property back to the normal, and then by having these two concepts together, you can get a optimum strength and toughness. So in another example, if you use two chain extenders, please do not bother about the structures, two chain extenders in polyurethane, so it provides a mismatched hydrogen bonding, and because of this mismatched hydrogen bonding, it results into a very high mechanical strength which can reach up to 70 MPa with a large extension. So that kind of strength and elongation is quite unusual for elastomeric material. In another example, you can see if you have this kind of molecule, and then these are stimuli responsive. Stimuli responsive means if you have a molecule and then apply force, so some bond breaks and then another forms, and because of this the material shows change in its color. So as you can see over here, so this concept is known as mechanochromic, and then the same material changes its color by application of UV light. So when the material is exposed to UV light, you can see over here it changes color to pink. The same phenomena occurs over here, and then that particular concept is known as photochromic response, and then this can be probably used in information encryption. So as we saw that a small change in the molecule can influence the properties significantly, drastically. So there is a requirement to understand the properties by computational methods. So the present state of the art, the computation depends on molecular simulations, generalized equation of states, and empirical relationships. However, these methods have their limitations, they are member specific and depend on abstract thermodynamic parameters that are experimentally very difficult to measure. Therefore, there is a lack of generalized model to compute the elastic response of these kinds of elastomers. So we resorted to machine learning by using the literature data as well as experimental data to train the ML algorithm. So we used extreme gradient boosting algorithm. The experimental data for PDMS, polydimethylsiloxane, and carboxylated nitrile butadiene rubber, these are very important class of materials which are used in biomedical and automotive applications. So these experimental data were generated to train the algorithm, and this trained model was applied to compute not only the PDMS and XNBR, but also another elastomer which is styrene butadiene rubber, which is completely unknown to the algorithm. So this is the workflow. This work has been published recently in this year. So we calculated the correlation matrix for different descriptors such as base polymer, crosslinker, and the crosslinker molecular weight, polymer time. There are large number of parameters, and as you can see, the diagonal will be always 1, and then the parameter varies from -1 to 1, 1 being directly correlated, -1 being indirectly. So here the highlighted ones are the ones which have greater than 0.97 factor. So the test, the model was performed, the performance was checked on the test data. Here you can see there is a good correlation between the test data and the predicted data for PDMS and XNBR, giving R square 0.98, and for SBR rubber, which is completely unknown to the model, also shows a good value, which is 0.87, so which is quite decent. So here we compared the stress strain profiles of the experimental values with that of the ML predicted, and then here you can see this is for PDMS, it matches quite well as for XNBR. So these are for various experiments, in fact the different COPs are by composition, changes in composition. So the model also was compared with that of SBR, which is completely unknown to the model. Yes. So the model has the potential to compute the elastic properties of unknown elastomer. I come to the last part of my presentation, we will be talking about carbon foam, or known as reticulated vitreous carbon foam. It is a open shell, glassy, macroporous 3D interconnected structure. It is electrically conducting and thermal insulating. It is prepared from carbonization of polymeric precursors like polyurethane, melamine, coal tar, etc. The structure is complex turbostratic graphite. The graphitic content depends on the pyrolation temperature, and the carbonation temperature or pyrolation is done between 400 to 3000 degrees Celsius in inert atmosphere. The first patent appeared way back in 1960s, but the material still holds relevance because of its wide range of applications in electrode, energy storage, metal slag filters, and recently NASA has used this material in Parker solar vehicle as a thermal insulation. This is what the material, this is the carbon foam. So we have been working on this carbon foam for some time. Here we try to prepare a superhydrophobic carbon foam. So here you can by silicon deposition for oil water separation. So this is the process, we got a patent granted for this particular process. We got a very high contact angle. Yeah, so this is the demonstration of oil water separation. We have poured engine oil water emulsion, and then here you can see at the bottom it passes water. The foam now allows water to pass through, whereas the engine oil remains on the top. So we coated nickel cobalt oxide onto this RBC foam by hydrothermal method, and during the process this the material grown into nanoneedle structures, giving very high surface area, and as a consequence the microwave absorption properties of this material increase significantly. We demonstrated the energy storage capability of this material, and then you can see over here it glows LEDs. We have extensively characterized by electrochemical methods, which I am not going in detail. When we incorporate graphene oxide into this foam, it significantly improves the osteogenic differentiation. So, I'm just, yeah, we were trying to model using continuum mechanics, and by taking micro tomography of this carbon foam, the images are not very clear, but these are the typical images, representative images. We have collected large number of images and then put them together to create this kind of STEP file, and that was converted to CAD file and then finally a model, but we could not actually succeed. Still it is going on because of some memory and then message requirements. Meanwhile, we resorted to machine learning to predict the properties, mechanical property as well as other properties. So, I will quickly go through them. So, we compiled the literature data, the data set was 300. From machine learning parlance, probably this is a small data set, but from material science it is acceptable. So, the input parameters were carbonization temperature, heating rate, holding time, so on and so forth. The targeted were compressive, thermal conductivity, electrical conductivity, EMI shielding. And then we used physics informed XGBoost. We took sensitivity, data augmentation because of sparsity of data points within the physically admissible ranges. We took 75-25 train test data combination, SAP analysis were done. The EMI shielding properties were physics derived rather than the ML predicted. So, the important features were bulk density, relative density, porosity, carbonization temperature in that order for predicting compressive strength, electrical conductivity and thermal conductivity. However, for EMI shielding the most important was electrical conductivity. So, we compared the actual versus the predicted data. I will be finishing in 2-3 more slides. So, you can see for compressive strength the R square was 0.91, whereas for thermal conductivity and electrical conductivity it is pretty well matching. And then we have yes, directly, yeah. So, we have made a very simple HTML calculator, interactive calculator. So, can you please click, yeah. So, it can predict by giving the input data points, input data here. So, if you change it, can you please change the relative density and then porosity and then again predict it, yes. Yeah, so it does work. Yes, can you go back to the slide please? Yeah, thanks. Okay, so with this I come to the conclusion of my talk by saying a generalized ML model can compute the stress strain behavior of unknown elastomer. ML model can predict the properties of carbon foam reasonably well by considering some of the parameters. So, the way forward could be inclusion of molecular scale features, entanglement effect, chain conformation, so on and so forth. ANN model may be used to predict the complex nonlinear foam properties. Last but not least, de novo design of new materials using AI/ML is the way forward, moving away from the traditional time intensive trial and error methods. And with this I thank my collaborators, students and the funding agencies, and thank you for your kind attention.
Thank you very much, Dr.
I'd be
Patro.
happy to answer any question if time
do we have
permits.
any question? I think we'll have more questions during the lunch. So let me thank again.
I
And
think somebody has raised hand.
question.
Hi,
So we will
sorry.
hand over a memento from the organizers. So we are moving to our final talk of the session. It's a long-term collaborator of ours, Dr. Sarabhi Bhattacharjee. So from Indo-Korea Science and Technology Center, Bangalore. So he's heading the research and development at Indo-Korea Science and Technology Center in Bangalore, India. He received his PhD from the University of Madras while working as a research fellow at the Indira Gandhi Center for Atomic Research. He worked as a postdoc researcher at the University of Bonn in Germany and the University in Liège in Belgium. He then worked as a researcher at Uppsala University, Sweden, and University of Arkansas in USA. His research interests encompass a broad aspect of materials theory, and that includes magnetic materials, spintronics, the role of magnetism in heterogeneous catalysis, electron transport in compound semiconductors, and the development of machine learning models for functional materials. He's also interested in code development and contributes to open source codes. So yeah, looking forward to your talk. Thank
you. So first of all, I would like to apologize for being UN lunch, in between UN lunch. So in this short presentation, I will discuss a little bit about our recent work on ML and data-driven approaches for energy materials. So these are the things basically I am going to say. First, I will have a small introduction about the energy materials, and then the methodologies which I have used. I will not talk in coherent way, so it's just they will appear. And then I will do some demonstrative results about hydrogen storage materials and also some single atom catalyst for important reactions. So by energy materials, what do we mean? These are the materials which are important for energy storage, conversion, and utilization. So they are very much related to our recent focus on this decarbonization and sustainable fuel chemical across energy system. So the typical examples are, for example, hydrogen storage material. So you have to store the hydrogen to run the car. You imagine that you will run the car using hydrogen, and it's reality nowadays. And also things like electrocatalyst for important reactions such as hydrogen evolution reaction, oxygen reduction reaction, etc. So for example, in fuel cell, from the oxygen you get water and clean electricity in this fuel cell, and we need the material for the cathode. So the typical performance metrics are capacity, then overpotential, and of course the cost and criticality, etc. So for example, for hydrogen storage, there are some issues. For example, we need targets are high capacity and fast charging and recharging at ambient pressure and temperature. But there are issues such as the materials that bind hydrogen strongly, they don't liberate hydrogen at normal temperature and pressure. And there are other issues such as scaling related issues and the reversibility issues. So the typical things which we calculate for this sort of material is the formation energies across various composition, hydrogen binding, and hydrogen diffusion. Diffusion barrier means how hydrogen propagates in the system. For electrocatalysts, the major target is to obtaining low overpotential. By overpotential, we mean the extra voltage which you need to provide to the system so that the reaction would take place. And the other stuffs which are, there are some issues such as like overbinding here also and corrosion, etc. So the things we calculate for this sort of material is like we obtain these descriptors like adjusted energy, Gibbs-free energy, etc. And we can calculate overpotential from our simulations. So why machine learning or data analytic approach helps? Because the design space is huge, so we can reduce it. And also we can use this DFT based data to train models such as cluster expansion, symbolic regression, deep neural network, etc. So solid has the actual problem is solid is in quantum mechanical many body problem where electrons and ions are there, but it's difficult problem to solve because it involves large high dimensional coupled partial differential equation. For example, for water molecule you have 39 dimensional partial coupled differential equation. So DFT always come as a kind of rescuer. Why it's not moving? Yeah. So now where we replace this many body problem using a single electron problem, where each electron move in an effective field provided by other electrons and ions, and from this one we can calculate the total energy, forces and other properties. So here, for example, I am collaborating with IIT Kharagpur, where computer science people are using this sort of databases, which are basically obtained by DFT, where you use the simple inputs such as atomic positions, unit cell size, and you can get the forces and optimized structures and band gap from the eigenspectrum of this sort of equation, formation energies, etc. So, and also you can calculate the hydrogen storage capacities using DFT directly. So, another data analytic method which we use for hydrogen storage is cluster expansion method. So, this is used for studying alloys. So, suppose you have an alloy containing different sort of atoms. So, this is a kind of effective Hamiltonian approach. You consider different configuration of the atoms and make a DFT database and then map it to an effective Hamiltonian which has this sort of structure, which has a correlation matrix which depends on the position of the atoms, and there are some coupling constant which you calculate by fitting with usually methods such as lasso or other regression approaches. And you can do it for different sort of alloys, binary, ternary, and mixture of binary, ternary alloys, etc. So, now we have used this cluster expansion approach to design new hydrogen storage material from max phase, which is a kind of material where you have the layered structure and there are lots of spaces to put the hydrogen. So, you have to find out which space is best for the hydrogen, and then you put lot of different atoms and find out which atom give you the best energy. So, this is the parent phase and we use different sort of atoms and we found that copper gives the best result. The next thing is that we make a small database using DFT and train this cluster expansion model. So, once this effective Hamiltonian is ready, you can calculate the formation energy of any number of atoms, any number of configurations. So, we have computed for 1000 composition with different copper concentration. And so, we found some materials which are much better than the parent material. So, next thing what we have done for hydrogen storage is we use deep learning to design new hydrogen storage materials. So, here the thing is for the hydrogen storage materials usually the database is very small and you can have many features. So, as a result it is a high dimensional feature space with very small number of targets. And so, what we do is that so we used a hybrid approach. There is a predictive engine which comprised of a unsupervised feature learning and then followed by a predicting MLP, and then you can predict the hydrogen storage capacity using such approach. And then we have a generative engine which is basically a small fine-tuned large language model, the older version of the GPT, GPT-2. And from this one we generate lot of structures and we calculate the hydrogen storage capacity using this this machine learning, this hybrid model. So, as I said that it contains this sort of autoencoder and an MLP, and if you look at the performance, this hybrid approach has best performance. It has highest R square and smallest RMSE compared to if you use this only 5-layer MLP or the standard machine learning approach such as lasso or gradient boosting regression. So, we also use this sort of method and tested it how it works with different materials which we come up with feature based material selection. And then we have used, sorry, it's not going back. Yes. So as I said that we have used this GPT-2 transformer for generating different materials, and then we test with our model, and we finally verified with DFT calculations. So another approach we have used is the symbolic regression approach. So this is a very old technique. So in normal regression you have the features and you do a regression, but here in symbolic regression what you do is that you combine different features, and basically this is your feature space now, and you can use it for predicting properties. It was used in ancient time, probably is the first and most famous example. Johann Kepler used the planetary data from Tycho Brahe, and he came up with 3 laws of planetary motion. So when Sir Isaac Newton came up with his universal law of gravitation, the first thing he actually found out that whether they satisfy, I mean, you can derive these 3 laws from this universal force law. So we have now better situation than Johann Kepler time. We use genetic algorithm and compressed sensing. So in this work, for example, we have used compressed sensing. So you start with some physically meaningful feature, and then you combine and generate large number of feature space, but in a physically meaningful way. You mean you don't add up kg with centimeter like that, and then you find out the features which are, I mean the descriptors which are highly correlated to the target and also mutually independent. And then you do a sparsification to get the property, the mathematical expression of the properties. So we use such approach for this sort of industrial chemical reactions like HER, OER and ORR. So the main target is the overpotential. As I said that overpotential is nothing but the extra voltage which you have to give to the system to form the product from the reactants. And so the usual workflow is that you have the DFT data of this overpotential, and you feed the symbolic model to manipulate or control the overpotential. So yeah, so we use single atom catalyst on this sort of Maxine surface, and we obtain DFT overpotential data, and then we feed the symbolic regression model. And if we analyze this model, you can see that it is kind of giving, I mean the model gives result in terms of important stuffs like Bethe charge, electronegativity, demand center, etc. So the same we have done for trifunctional catalyst, where same atom participates in 3 reactions. So this is OER plus HER for the electrocatalysis, and this is for the metal ion battery. And here also by doing this sort of symbolic regression, we got important physically meaningful results where the descriptor came out to be the charge transfer between the surface and the single atom catalyst. So this is the work I think already Professor Das mentioned about this sodium ion battery, so I will not go for, I will not talk about it. The last thing which I will mention, like the collaboration which I am doing with Professor Ganguly and Professor Goyal. So this is graph based generative model for new materials design. So here we use both large language model and also the diffusion model. So large language model is used to generate the atom types or atom types, and this is retained, and the diffusion model is used to generate the crystal structure, sorry, the lattice positions and the crystal structure. So this result was published in this NIPS last year 2025, and so that's it. Here are my collaborators, and thank you so much. Thank you for your attention.
Thank you very much, Radeep, for finishing in time. Time for 1 or 2 quick questions.
Okay, Nilada has a question.
So is it possible to combine this symbolic reasoning with like generative models, diffusion models?
So there are neuro-symbolic these things are there, like using neural network you can do the symbolic regression. I did not mention them because of the time, but so since they can be coupled to neural net, I mean you can do it with neural network, I think it is possible to make a generative model also. So you are saying doing inverse generation, I mean inverse generation using symbolic this thing and neural network. Yeah, it's possible I think. It's not done, so it's possible. But it will be very heavily computationally this thing because you have to search through this feature space.
So one more thing, like you are showing generative models. How much are you generating that is not known? Are we really generating materials, or we are generating all known materials?
Yeah, sometimes it generates the known materials, of course. You have, when you generate like say 500 new materials, some of them are basically repetition. So they exist somewhere. I mean, of course, you don't generate the one which you train actually, you generate the new samples. But some, it is not there in your training data set, but maybe somewhere in the experiment or somewhere it is available.
Maybe just as a follow-up to the first question on this. By the way, very nice work.
Can you speak a little louder because I cannot.
So as a follow-up to the first question, you know, there are, for example, you are talking about neurosymbolic methods, but maybe symmetry-aware methods might be more interesting. For example, how do you enforce and incorporate symmetries into crystal generation? Because we are looking primarily at crystal generation, and we know that basically there are only 230 space groups. It should follow one of those space group ultimately. Unless you are looking at disordered materials or compositionally disordered materials, I think that makes it a bit more complex. But here we are looking at pure crystal generation, right?
Yeah, so you are saying like symmetry-aware neurosymbolic approach.
So there is this idea of combining neurosymbolic with constraint generation.
Okay.
The idea is that, right? So you can, now symmetry is a constraint, right? And yeah, so symmetry can be put in, it's like Sudoku solving. I think this is one of the first classic problems that people have been looking at, because it's a constraint generation problem. It has to add up this way, it has to add up, etc. So the same way,
Krishnan, the neurosymbolic method, as far as I know, is not used in material science. So there is something called AI Feynman. So that is used in quantum electrodynamics or some other stuffs like cosmology and all these things. So they are, you know, for high energy systems, the symmetry is very, I mean, symmetry constraints are not that much there because they are highly symmetric. But for materials, as you said, it's very important because here the symmetry is important.
Yeah, but people have used it, in fact, not drumming my own beats, but I also had a slide where we also used symbolic regression to, you know, for example, learn the interaction laws and other things. I think that's a separate angle. I was asking about constraint generation, but I think this is a longer conversation. We can talk afterwards. But thank you. Thanks a lot. Yeah.
Thank you very much. Very interesting to see there were many food for thought before food for stomach. So a lot of discussions. So let's thank the speaker again. I will have a small memento from the organizers. So this also completes our first theme session. Professor Arnav has some announcement to make.
So I'll take just 2 minutes of your time before we break out for lunch. We have an interesting brainstorming session at 5 p.m. In the evening. It's a 1.5 hour packed session. It will be held at the second floor of the Takshashila building, which is just beside this building. So after these sessions end here, we will all go together to the second floor of the Takshashila building. The name of the session is From Ideas to Impact, AI Collaborative Research Brainstorming. And the objective is to arrive at nationally relevant AI research problems focused on 3 thematic areas along the thematic lines on which this whole workshop is organized: materials, and then climate and bio. So in this session, we will have focused discussions. And the idea is to go beyond talks to actual research problems and arrive at concept notes which can be further taken up into next level more focused research discussions, and finally arrive at sponsored research problems through the AI impact Impact AI mission or the ANRF, etc. Now, one important announcement here is that for the materials group, we will have moderators for each group. For the materials group, the moderators are Professor Pavan Goel and Professor Kaushtab Roy. For the climate group, the moderators are Professor Advay Mitra and Professor Rajiv Maiti. And for the bio group, the moderators are Professor Debaditya Roy and Professor Shorangshu Bhattacharya. So we will all be there, and we will together try to use this focus session to build a nice, very structured concept note. And this concept note structure has been shared with the moderators. So it will be a live working document, and we will finalize the live working document by the end of the session. And hopefully, it will be a nice document which we will be able to actually take up towards an achievable sponsored project, cutting edge course material, etc. That's it. We all break out for lunch. Enjoy lunch.
We are coming back at 2:30. We'll be starting sharp at 2:30, the next session.
A single storm can drain millions from a
हेलो
मस्ट स्टार्ट फर्स्ट ना वहाँ पे वो आपको साइन देंगे तब स्टार्ट करिए यहाँ खड़ी हो कैमरा कर
Welcome back everyone to the session on AI for science and technology. We hope you have enjoyed all the sessions so far and there is a plenty more exciting content coming forward. With that, I am delighted to hand over the session on AI for weather and climate modeling to Professor Sudeshna Sarkar from the Department of Computer Science and Engineering, IIT Kharagpur.
So thank you. So we begin the afternoon session, which brings to us one of the most consequential frontiers where AI is being used in weather and climate modeling. So as we know that climate systems are complex and nonlinear, but it also has very high stakes for decision making in climate is very important. Fortunately, there's also lot of data in climate. This is very data rich, and therefore there is an opportunity where modern AI can make a transformative difference. So in this context, we know that advances in AI architectures as well as high performance computing can address this important challenge. And what was once limited by computational resource and model resolution can today be addressed by deep learning, data-driven discovery. But also, it is very important to work with hybrid physics AI models because the credibility, the scientific credibility, as well as interpretability plays an equally or much more important role. So in this session, we bring together leaders from climate science, operational metrology, industry, as well as geo-AI, and all these disciplines have a very important role to play in addressing climate change. So both AI researchers and climate scientists need to work together to address these challenges. So with that, we will begin today's session on AI for climate and weather modeling. So for this session, we begin with Professor Bhupendranath Goswami, who is one of India's most eminent climate scientists and a global authority on monsoon dynamics and climate predictability. Currently an honorary distinguished professor at Guwahati University, he earlier was a director at IITM Pune, where he played a pivotal role in advancing climate research capabilities in India and improving vastly the forecast of the different climate models. And Professor Goswami has many awards as a recipient of the Shanti Swarup Bhatnagar Award and a fellow of all major Indian national science academies. He has seminal research in monsoon and climate predictability, and it has shaped both fundamental science and operational forecasting. Today he will share his vision why this is the time to think big scientifically and computationally about the future of climate and weather modeling. Please welcome Professor Goswami.
Thank you very much. Thank you very much, Professor Sarkar, for that kind introduction, and welcome everybody to the afternoon session. And I hope that after a heavy lunch, I am able to keep you interested in the topic. That's a difficult job. So I like to start with this picture because I think this particular paper was highlighted in the first page, top cover of the Science magazine, and then in the next year, NASA considered this as one of the top 10 newsmakers, science newsmakers. Okay, so I think this particular work actually was a disruptive development, which actually ushered in the second revolution of weather forecasting. Okay, so that is why I think this is a very, very important development. So within 2 years, this paper has been cited by more than about 2,000 times. So that is the kind of, so that second revolution of weather forecasting has started. Now what was the first revolution? And the first revolution actually started in 1950 when I was just born. And in my, I have grown up with that first revolution. From 1950 to 2000, over about 70 years, the climate scientists worked very hard to improve the skill and predictability horizon, prediction horizon of the weather and climate. And we have achieved a great deal today, and that is why today I think the meteorologists are has no longer become the the subject matter of cartoonists. I grew up by you know, so all the cartoonists making fun of meteorologists. But today I think you have not seen over the last few years IMD's forecast. People don't really make fun of it. They have realized that the forecasts have improved. And how did it improve? It is because of, through that revolution, a lot of research in the basic research of understanding the physical processes and improving the models and improving the data as input. So both things have improved, and that was the first revolution. And however, we have missed that first revolution in India, because when I joined 2009, at IITM, we realized that India's skill of forecast as well as the forecast system quality and has been about 30 years behind the rest of the world. Somehow the India missed the first revolution. It missed the bus of the first revolution. So my concern has been that, and then when the second revolution comes in, I'll tell you why we missed it, and that is a story. We'll try to work on why we should avoid that. So my concern that we realized 6 years ago, that I realized about 6 years ago after my retirement, that this revolution is coming. And I started learning a little bit about artificial intelligence with Adobe and all that. And then slowly I realized, and then that thing came true. In 2023, it really made this kind of a breakthrough in terms of applying this artificial intelligence techniques to improve weather forecast and go beyond the horizon of capability of the dynamical models. So I was quite concerned that we should not miss this bus of the second revolution, and that is the context of my title of this talk. So that we don't miss, and what I am going to discuss that what we should do not to miss, and so that will be the theme of the topic. But why we are talking about this is because I think for all these all the bread and butter of all our research work of the weather and climate scientists is to improve forecast, because forecast of weather and climate, and because improvement of forecast even one day in advance of the same quality, good quality forecast, if I can make one day advance, that makes a huge difference in the socio-economic impact on the people immediately. And in fact, that is exactly what we have established after I joined the IITM in 2006, when we were 30 years behind. And we worked very hard with some of my young colleagues that I recruited, and help of MOES. We worked very hard to bring this system to that level of the sort of international equivalent to the best in the world. And that we did. And that is what then was transferred into IMD. IMD's quality of forecast improved tremendously in that period. And then there was a study which actually was conducted between 2014 and 2019 by a reputed agency, and they figured out that improvement of forecast led to about $1 billion savings for farmers and fishermen in saving their damages and improving the productivity because of the good quality early forecasting. So there is a huge importance of increasing the forecast. So it was 30 years when we were behind. The Indian people did not get the benefit of improved forecast that was able to give us that benefit. So we lost that, and we should not lose that in the second revolution. That is my concern. That is the context of this story. So, with that, let me start. And that why that happened is, I think, it is an important issue to recognize. Is that in India, I think, in generally, but particularly meteorological community, we don't have a long-term vision. And when I was growing up, I was doing in my young days of professional life, my peers did not think that modeling, the physical modeling, physical based modeling is going to improve forecast and is useful. But they discouraged the capacity building requirement or the computer requirement. As a result, the community like me who is growing up in that actually suffered. And then we had to do, because we could not do the kind of research that we could have done. I came back from America by doing this cutting edge research in modeling, but when I landed in India and I was committed to do something in India, but I had no resources, and nationally there is not available because we have not thought that we need it. Although there are sanctions at that time, but even if we had sanctions, if the community said that we need it, we could have done it. Like ISRO did it when there are sanctions, but it is the community who did not think that we need it. And that is what is something that is a very important thing to recognize today, that in the second revolution, when it is going to improve this forecast, we should have a long-term vision. And that is what I am going to talk about. And that long term, and another thing that is that we have ailed our society, our sort of community, is that we don't want to really work hard to build our own thing. So I think we talk about this Atmanirbhar Bharat or whatever it is, but today also I see that we are not willing to work hard on build something of our own. We will be happy to borrow and then start using it. I think this mentality is still happening. It happened before my time, and it is also happening after my time retirement. So I think this is something that we should try to avoid. So I'll talk about a little bit about the first revolution, and why the first revolution has come to a saturation. And we need, actually, that is exactly the time when the second revolution has started. And that is, I think, is a contextually a very, very exciting development. So this is a story anyway. I'll already telling you this story. So I'm quite excited about this opportunity. So this also provides this opportunity. And for the last 6-7 years, I have been working with Adway and learning And I realized that there is communication between computer scientists and the meteorologists is very poor in our country. And I have independently talked about many computer scientists in other different, I did not see anybody's interest in see the improvement in the second revolution started at computer scientists. Very little input from, they learned what is needed, they worked hard, of course they have commercial interests, but they worked hard, that was the vision. From 10 years they worked, Google and other people, they worked for before 10 years and 23 that matured. But in India, I don't see neither from climate scientists, not for computer scientists, that vision, that I did not recognize it. So we need to recognize that that is very important, that what is expected figures. But 6 years ago I did recognize, but I was out of circulation. I could not influence any policies. And I tried and I failed because they did not listen, because I am not in the system. So this is something that, that needs to be recognized. I think we should be aware of this and hope that my juniors, the young scientists that are coming up, have the right environment to have. And this is what makes me a little happy, that in this new proposal of ANRF and all that, there is computer scientists and the meteorologists are coming together. And this conversation I think is very, very good, and I am hoping, I am getting excited about it, that we should not think big. That is why I am talking. Think big and we can make a big difference and mark in the global stage. So this is an opportunity. So I think this opportunity we should not lose, because this particular technique or the understanding of this particular, what this AI ML can do to improve our forecast is an opportunity. And this opportunity, you are not limited by the infrastructure that I was limited with. Today infrastructure is there. What we need is your intent or willingness to dream big and work on it. So if we have that, I think we can succeed and make a big difference. So let me talk about a little very quickly. I will go through the slides. I am not going to spend too much time. So the first revolution of weather forecast started in 1950 when Professor Jules Charney at Princeton and demonstrated for the first time that the geophysical equations can be solved and made meaningful forecast of how the weather predictions are formed and propagates. And that was a proof of concept, and that started the first revolution. And then started growing, then the complexities, we started building better and better model, we started introducing more and more realistic physics, and that is how the models grew. So I was fortunate to work as a postdoc with Professor Jules Charney, by the way, for a couple of years. And then from that time onward, the quality of the forecast improved, and today we have this is the forecast skill from one of the top weather prediction centers, ECMWF, and these are the skill, evolution of skill from 1980 to recent years. This is kind of a correlation between the observations and the predictions. So 0.9 means 9 correlation of 0.9, that means pretty good. So today 3-day forecasts in extratropics are like 0.98% accurate, and they are really good. So, and what has happened is that, and today the 7-day forecasts are as good as 3-day forecasts 3 decades ago or 4 decades ago. So that means in those things we have improved about 4-day advanced forecast we can do of the same skill that we could do 4 decades ago. So that is the kind of progress that we have made, and that made a huge difference in terms of its capability to application for the users community, saving energy, saving lives, and reducing damage, and a whole lot of benefits for the society, and that is what we have to target. And then so there is a lot of but these forecasts are always limited by what we call deterministic chaos. The system is chaotic, multi-scale interactions, and the small initial errors grow very fast, and the forecast becomes very unreliable, because we can divert from your observations by significantly, and that is called deterministic chaos. And in 1969, Professor Lawrence estimated that because of this, whether you can, the limit on weather predictability may be maximum 15 days. And today, as you see, we have reached that limit almost, we have reached almost, the 1 day forecasts are almost accurate up to about, so 7-day forecasts are good. So we have, and almost up to 10 days we can make reasonable forecast in many things, in the extratropic. In tropics maybe 3 to 5 days in advance. So that is a big advance. So almost reach the predictability limit. But there is some gap, and we are not able to bridge that gap between the limit of predictability and achievable prediction skill. And that is the problem. So and it is happening over the last 10 years. If you see, our forecast skill is not, it is flat, it has not improved. So it kind of, this thing is getting flat. That flat means we are improving the models, improving the data, still not, skill has not improved. That is because of the growth of errors. There are errors, some small errors are inevitable, and that error grows and makes even the large scale forecast, because of the multi-scale interaction, it makes the large scale forecast poor. And so we are getting to this first revolution is coming to a standstill, because now even if we do more work on improving the models and improving the data, we are not able to push the horizon of forecast. And that is when, exactly when the second revolution started. And we must, so that is when the second revolution comes into effect, and we must work hard to take advantage of this. So that is exactly when in 2023, 2-3 different papers came into one time, almost the same year. And so I am not going to go on, most of the people who are following this will know, and I am not going to go into what technique they have used, what not. I am not going to, I am just going to talk about broadly how this evolution has been taking place over the last 4 or 5 years. It is taking at a very breakneck speed, because initially it started with somewhat simpler models and simpler achievement. Now we have more complex models are now being used, and now a little bit better, but there are certain limitations still, and we have to work on that. Now why did it happen in this time? I think one of the things that I think very interesting to see historically, suddenly why 2023 this explosive development took place. It is because of 2 things. First the atmospheric, the climate weather system is a 3-dimensional geophysical global system, and we need to train weather system. Time scale starts from 2 to 3 hours or 3 to 6 hours. The thunderstorms have 3 to 6 hours. These thunderstorms give rise to mesoscale system of about 1 day. And so you have to be able to train the systems from that 2 to 3 hour time scale. To do that, you have to have data, 1 hour data. So 1 hour data, observational data globally was not available until what is called era 5, that data was available in 2020. So that is when this computer models were being developed, but then they did not have the good data to train. Now they found suddenly, so hourly data is available. So that was a big thing. Second thing, the third thing, second thing, important thing was to train them onto the geophysical 3-dimensional patterns, like clouds for example, or a mesoscale system has a very complex 3-dimensional structure, and we have to be able to train them. So you need good 3-dimensional neural network, and that was also became available just around the same time. So I think these two things actually made a big impact, and so by that time we were able to make this. So this paper by Sonia and et al. I think made a huge impact in terms of the vision transforms to make very meaningful 3-dimensional. Also important thing is that the Earth's geometry is 3-dimensional. There is a geometrical 3-dimensional pattern is embedded. So you have to be able to take that out of the system in some way. So you have to transform the geometrical system, or transform the data into system which is geometry independent. So this kind of a development was also required, and that also happened around that time. So, and this actually made so much way. I was very fascinated by this paper, because it is one of the topmost now of centuries topmost cited papers. Now it has become 7th in the last year. It became the 7th but this paper was published only in 2017. And then it became out of last 100 years topmost cited paper, top 7. And in the last, after 2000, after 2000, the first, in this century, it is the topmost cited paper. So this is a disruptive technology that has now been available, and that technology we should use for the benefit of weather and forecast. And so this person also, this is another person who has contributed significantly. I think his paper, this is one person, first person in the world I think has more than 1 million citation. He is Yeshua Bengio, and he is a Canadian scientist, and he has done sort of, it's one of his generative adversarial nets is more than 1 lakh times cited and so on. So suddenly this 3-dimensional neural network and their applications are exploding, and that is the part of the story. So it also provides a opportunity that our forecast was limited, forecast horizon was limited by the growth of small errors. Even if there is some inevitable small error, it will limit my forecast beyond a certain point of time by using the dynamical models, because dynamical models have this error growth problem. Now, since we are doing this data driven model, it gives us an opportunity to circumvent that error growth problem and still keeping it physically meaningful, and that is another important thing. So in a way, it is like finding analogs in the past. Just your LLMs are like analog finding models, right? So if you give a string of inquiry, and so it is like a pattern. That pattern how many times occurred exactly in past and what followed that pattern gives you something like a prediction, right? So this is a kind of analog prediction. We recognize this way back in the past. Lawrence recognized it in 69, but at the time we did not have enough observational data to make real good prediction, and today we have good data and we can make that prediction. So there are other issues, but so now there are so many foundation models of this 3-dimensional prediction of weather, but it is missing one thing. None of these can predict rainfall. They can predict all the other fields which are smoothly varying, like the winds, temperature, geopotential light and so on, surface pressure, all that is good and useful, no doubt. But precipitation is very important for physically in tropical countries. Without precipitation is a driver, and we need that. And so that is still missing, because precipitation has a lot of small scale variability and we do not have enough data to train it. So next milestone. So even the next milestone is something is that even if we take one of the foundation model and find out innovative way of predicting precipitation, even at synoptic scale, the weather prediction lows and depression scale and meso scale, even if you can do that, that will be another milestone development. I think that is something that we should work on India, and that is what I am suggesting, that we need to work on that. And another thing that we should think big, as I said, by thinking big means we should have our own AI models. So we are now, there is a whole lot of several foundation models. Why can't we have our own foundation model? So we should not be simply borrowing and going downstream application. Do that. You can do that, lot of downstream applications. So now I think downstream applications can be done by simple graduate students, undergraduate students will also do if you tell them exactly what to do. But we have to do in the bigger thing. Bigger thing is to get our own monsoon model, for example, a global monsoon model. We need a global monsoon model, and we can develop it. And also we can develop a foundation model which is coming from India. Why India cannot produce one foundation model? I think we have brilliant computer scientists. We have reasonably good understanding of monsoon system or the climate system. If we can combine our head, we can come up with one. I think if we can come up with such a foundation model of our own in the next 1 year, I think that will elevate India's image in the whole world. I think it is doable. We are not thinking about it. We are not thinking big. That is where I am saying we must think big, and that is possible, doable today. So what are the challenges? Challenges is, one of the big challenges is the precipitation forecast. And why precipitation forecast is challenging? Because because this problem, this ERA 5 is in a sort of has become a household name for training AI models, because this is a very good data set, but the precipitation is quite horrible, I will say, for training rainfall in that, because this particular rainfall, probability distribution of that rainfall, I am sorry, this is a small figure unfortunately, but think about this. This is a probability distribution of hourly rainfall, and these are the extreme event. So, this is the rain rates going up to 110 millimeter per hour, and that is the kind of rainfall that events are there in the observation. They come from satellite data and rain gauge, hourly rain gauge data from few stations. So, that is the kind of observed curve, and this is the hourly data rain from ERA 5. ERA 5 does not produce even more than 35 millimeter per hour extreme events. So, they simply cannot produce any extreme, and then I found out what happened, that if you do a frequency distribution of the duration of these events, extreme event, it turns out that that moderate extreme events are very long, and they are unphysically long, and they produce reasonably daily accumulated rainfall is okay. But the hourly values are terrible, and they are producing daily correct rainfall through a very unphysical mechanism. So, they are terrible to be trained. So, then where do you get better data? So, only data that is there is this satellite data, but satellite data is only is about only 25 years. So how do you, but that is not enough because of the small scale variability. The satellite data is not sufficient to train for the rainfall variability at that scale. So, we need to generate. So where do you get that? This is a big challenge, and this is going to be a fundamental challenge, and if you can make some dent on this, I think we will make another milestone, and that I believe so what do we need? We actually need about 100 years of hourly rain reanalysis with a non-hydrostatic high resolution model. By the way, why does ERA 5 fails? Because all these analysis is using a forecast model, hydrostatic forecast model, because non-hydrostatic analysis takes a very long time, because the global non-hydrostatic reanalysis at hourly scale takes a long computer resources, and that people have not done that today, and so that is the problem. So, because hydrostatic models do not allow strong vertical motion, and therefore deep convection, it does not allow extreme events are underestimated. So, so recently, so instead of that, suppose I have either a high resolution non-hydrostatic 100 years analysis, that will help. If not, if I have a high resolution climate model, atmospheric model, non-hydrostatic atmospheric model, which is also run freely for about 100 years, that will also be good, and that kind of model is being available today almost, and that is very recently, 13 January. This thing has come. This is a European group who has come out with a called ICON. It is a non-hydrostatic icosahedral model, global, and they have integrated it for about 10 years. So, 10 years very good data is available, still 10 years only. So, this is still a challenge. So, what can we do? I think we can do something. So, they have actually reasonably good simulation, but of course, they still have certain biases of precipitation, too much rain over the ocean. Too much rain over the ocean compared to observations, and there are certain biases, but the frequency distribution of hourly rainfall is pretty good, So I think this is an important development. It's a big important. So this kind of very important developments are taking place at a very rapid rate, and we need to be. So what else can we do? I think one thing we can do is something called augmented data. I think suppose I take this 25 years of observations, and I create a very similar copy of that for 100 years. There will be no time stamp on that, because I have to make copies and then by using. So we have done an exercise we are doing with one of my colleague at IITM, older postdoc which worked with me. So we are doing this kind of temporal wrapping, magnitude modulation and spatiotemporal noise addition using it's generated about 100 years of augmented data, and we are trying to think that we may be able to use that as the tool to train. But there are challenges, it is not so simple, because now if I go and use that with ERA 5 circulation data, then there will be mismatch about the coupling, because the convective coupling. So there will be a serious, okay, but I pointed it out yesterday, and I am grateful. I think something we will need, there are challenges remaining, and we'll have to do it. So I will skip a lot of things in the, and we have seen some of the things that it is doable, but I will not, so I'll skip all this. I'll come to the conclusion what we need to do in a minute. But just let me tell you something that we are doing on climate. So climate, 2 minutes, right? Climate, it's still a much bigger problem. But the problem, the one good thing about climate, doing climate is that we have a lot of climate model simulation data, and we can train on them, and so that. And then the sort of use observations to fine tune the model, and that way I think there is potential for doing that, but still there is not much work was going on, and we have done a little bit of studies in doing monsoon prediction. We have published a couple of papers recently, and some interesting idea about long lead predictability. I think it is a quite fundamental work, but I have not much time to talk about it, and we are able to make good prediction up to about 18 months lead. And this is, people could not believe it, and so we had a lot of problem publishing this paper. Finally we have published, but there is a good physical basis of doing that. And so but today I think there is no, for last couple of years, the development in the coupled modeling using data driven coupled modeling was missing. But just recently, very recently, this year, last year, towards the end of last year, models have come up. This is a development, recent development, and they have actually made a coupled model which actually seems to work, because there are challenges of actually ocean model part, because ocean model is very difficult to simulate because of the boundary. Boundaries are like precipitation, there are complexities, and that is what, but they have been able to. So problems are getting solved, the challenges are getting solved, and this progress is taking place rapidly. So I will not go into greater, then come to my just concluding remarks. So the concluding remarks is that let us recognize that progress is taking place at a breakneck speed, okay. Then we have to focus something and put lot of effort to do it faster. And then three things I mentioned, that one is either here or some last page, a minute, sorry. So I think we should do three things. One is a foundation model, which is our own. A neural network component is our own, basically core part is at least our own. The other parts have become standard, it is like architecture. You take some of the transformer is okay, but basic thing, physically meaningful way, if I can add, it will be our model. Second, you develop any foundation model which will do precipitation. So the first part you do without precipitation, that will build a foundation model. The second part will be with precipitation, these two things. And the third thing is something on the seasonal and intra-seasonal time scale. You develop a monsoon specific S2S model. And this is also a very clear idea, we have clear ideas about it. I think these three projects we can consider as very focused, needed things. With that, I will stop. Thank you.
Thank you, Professor Goswami, for that wonderful talk, for sharing your experience and giving the roadmap to the current researchers. So we have time for a couple of quick questions.
Yes, sir. It's a wonderful talk, actually.
Thank
you. Touched upon very important things. But my question was, any AI model is very data intensive. Okay, we need to have a better physical model which provides a long-term data set. Then only AI can be used as an interface, or you wanted to develop a model where physical equations are no longer required and only AI can do everything and without any physics.
I agree. I agree. No, you cannot abandon the physical models. No, not at all. Because so what we are going to do is actually doing the forecast is very computer intensive, okay, and the skill is not becoming good. Now by using the AI models, we can do actual forecast, but the research and development must continue because we need better and better data to train. Okay. So the research and development can go without being hampered by the deadline of forecast. So they can do aram se and without too much pressure on the computing resources. Whereas because forecasting requires a lot of computer in a very short time, you have to deliver tomorrow's forecast today afternoon, then only I can disseminate it, right. So that time requirement requires a huge computer. So without that, this forecast will do in a laptop once it is trained. So the operational forecast now can be done with very little resources, computer resources by the AI forecast. Then you do developmental part which it is continue to do that, and the climate models also need to be improved, so that for training the climate model, the coupled climate models, data driven coupled models, we need better and better data and longer simulations. So
okay. In the interest of time, we'll stop now.
Thank you.
To give a memento
Thank you.
to Professor Goswami.
Thank you so much.
One more picture.
One more picture, sorry. Thank you. Thank you so much. Okay. Can you take up?
So building on that vision, our next speaker turns to the intersection of climate science and AI. It is my pleasure to introduce Dr. Rajiv Chattopadhyay, Senior Scientist at IITM Pune. Dr. Chattopadhyay is at the forefront of integrating machine learning with dynamical models, with a focused mission for improving predictions of monsoon and climate variability. His talk today directly addresses a central AI challenge in climate science, which is evaluating and understanding forecasting skill. Welcome, Doctor.
Thanks. So, thank you for introducing. Last talk by Professor Goswami actually is a very important, and I think I have lot of slides which are common, but I'll able to skip it. So this is the data-driven AI prediction frontiers which we are staying today. This is not exhaustive list. And here you can see that there are enterprises which are private enterprises which are developed, as Professor BNG has mentioned, and these are some of the operational forecasters who are now started using these forecasters. One interesting thing is the role of these big enterprises are very significant compared to the first revolution of AI, which first revolution of NWP, where many things come from the NWP from the universities. So I think that's a different point, but it's a point to think about it. Now AI in weather has tremendously improved many things, mostly like track errors of tropical cyclones and these things. Now I am talking about AI in climate, so which has actually little longer than the weather forecasting time scale, beyond a few days, so it should be months or something like that. So this work is, I acknowledge this is a PhD work of one of my students, and also I acknowledge the organizers for providing the opportunity to bring this work in front of you.
So this is about ENSO forecast, and ENSO forecast does not require any, because it's a billion-dollar question, actually trillion-dollar income losses are reported. So ENSO forecast is, so when we talk about climate forecast, so it is natural that people will start looking into the ENSO forecast very seriously. I think it's not going. So what we are looking into ENSO forecast is basically we try to forecast a time series like this. We all create some index, and which is, so it's a basically, although it's a ENSO is in the Pacific and SST evolve, and we create a time series in the time series, and this is, so our aim is to predict the amplitude of this time series and the phase of the time series both. So earlier generations of models which has created this understanding of the ENSO system, which simulated this thing. So this uses some temperature evolution equations, and they are able to use the ENSO forecast from the ENSO time periodicity and the amplitude from few basic assumptions, which I will not go in details here. Now the kind of problem that we face here in traditional forecasting method, which I am, one is called the spring barrier. So which means that if you start forecasting, so this black line is the El Nino line from the observation. If you start forecasting from July, for example, you will be able to catch the amplitude. At least some good models will be able to catch the amplitude. And then if you start forecasting, for example, from December, this black line goes one direction, the model goes one direction. So this is one of the very important significant problems in the traditional modeling framework. So and so the amplitude and the phase errors are very, it was not solvable for many years. Now this paper came actually in 2023, that they said that this CNN model can overcome the spring barrier. In fact, it is actually written in the abstract. Okay, and however, even that model, if you see, if you start forecasting from some places like October or November, so they are saying that the prediction skill extended long time. But as Professor BNG was talking about AI foundation models, recently Google has already Times FM, there is a paper just few days back came, and actually this is now available in GitHub. So what they have noticed in this thing is that unlike the NLP, there is no well-defined vocabulary or grammar for a time series. So it means that the options are enormous, and we need to understand the physical system better, and we need to create different types of initiatives to understand the AI-based climate forecast. So coming to our thing. So I think before that there is one slide I want to keep it, that any physical prediction model of El Nino, which is a temperature forecast basically of the ocean sea surface temperature, requires these type of terms which are actually nonlinear terms, and these are the forcing terms which are also sometimes predictable and sometimes not fully known. So we need to know data, and also we need to handle mathematical complexities in this, so as to understand so to get a good prediction or temperature tendency, to understand the temperature tendency, we need to handle nonlinearity plus this, and plus of course other forms of noise and other terms. So if we see the ENSO, we have all these type of models which are actually used in various formats, and these are some of the detailed model which I have collected, and this is from the paper. So there are a lot of interest in this type of things, but so at the end of the day, however, this is the traditional dynamical modeling which we use this thing. So, and this is a latest 3D geoformers, this is CNN and this thing, and this is dynamical. You can see this, if I start from this December, actually the AI forecast follow the same pattern as the traditional. So the skill is initially high, and if we start from June, July, the spring barrier is not overcome. So the physical question remain, although the skill became a little improved compared to the same thing. So all this format shows the same thing. So we did something like this. So one thing we understood earlier work, this is with Professor Goswami himself, that there is a east-west very strong SST gradient, and these SST gradients play important role in the development of El Nino type of situations. So we started with the question that if these gradients can be used to understand, and then we find recent works, several recent works, for example, I think it's not moving clearly. So we find that there are mechanisms those cause ENSO creates those gradients. So there is something called West Pacific oscillator and East Pacific oscillator, or East and Central Pacific. So both these things create this periodicity and these things, and if we go to the time series analysis, we see that the east-west gradients are very important in the temperature between in different time lags. So, and these are some of the results which says that CMIP models are not good in getting the this east minus west gradients, although they play a very important role in the atmospheric response of the El Nino type of situations. And so we thought we will test this hypothesis. So there are two things. One is we need to have a spatial pattern improvement. As we know, there are advective terms and other things which improves which requires a spatial pattern. The other part is the memory part. So we need a past time series which is temporal embedding to get into the prediction part. So this is the convolution. So spatial deconvolution or denoising is very well known. So there are Gaussian filters, averages, smoothing, and different types of smoothings are there. So we thought that we will use the CNN model, and so this was the paper which I am talking. And additionally, we will do that these weights of the CNN models are actually having initial conditions, or the initial weights we can vary in a different way, because every realization would lead to a different model. So we simulated say 10,000 or 20,000 models, and we created this type of architecture, and this is the details of the architecture, and this is the model. So we did two experiments. One is we are calling it as the whole Pacific experiment. One is the east and another is the west, to understand if the SST biases in the east and the west are actually useful in getting the predictions. So these are some of the things. So prediction will use the Nino 3.4 SST, which is mostly representing the Central Pacific. And for each of these 5,000 to 10,000 ensembles we simulated. And what we find is, if we use this whole Pacific is the control we are calling, and east and west are the two simulations, we find that the West Pacific experiments show better results in compared to East Pacific. So in terms of skill improvement, West Pacific plays a important role in this CNN model with past data, 12-month past data experiment. So, and the other important thing is that, so this is the skill plot. The spring barrier, of course, we will have a spring barrier does not go in this experiment, only if we use the SST in the Pacific. But there are some ensembles which can actually give. So I think if we use one or two ensemble simulations, then it would be falsely, it can be represented as we have overcome the spring barrier, but it may not be so. So most of my results actually show here that there is a strong spread in the SST, which you can see some models can simulate very low root mean square error, and some models are very high. So we really need to have a multi-ensemble simulations for this type of model to get a better results. So as we see that the peaks, like the problems of peaking is problematic, but sometimes in the phase is getting better in compared to this. And west also, the West Pacific SSTs are more important in the sense that in the CNN model gets the better picture compared to the if we train it using the East Pacific. So these are some individual cases. However, interestingly, for some cases neither west, neither east, neither the total, the ENSO amplitudes are not simulated. It implies that we have a problem. It's not the Pacific oscillations only in the important, so global, but this is known, the results are known, but we just check this in the hypothesis in this model. Same is for the La Nina. So one important thing is for El Nino, West Pacific is more important, for La Nina, East Pacific is important. So La Nina amplitudes are better captured in the East Pacific and El Nino amplitudes are better captured in the West Pacific. So I come to the summary that relative role of SST was we tried to understand East versus West based on the physical theory of ENSO, and we find that the West Pacific is important for El Nino and East Pacific is important for La Nina. And the problem is we need to have, really need to have a lot of ensemble simulations if we really have to claim big that it is a spring barrier is overcome or not. So we find that spring barrier may or may not be really physically overcome because there is no way to check it is a physical, one ensemble or 5 ensemble is a better ensemble. So we need to create a lot of ensembles, especially when we are training the model based on denoising, any type of denoising, and we need to create different types of filters and to see if the denoising has been done in the convolutional nets. So one proposition from this platform is we really need a customized models which we are trying to use to simulate the climate, because some of the denoising may not work for the climate simulation, some of the denoising methods works well for the climate. So these customized solutions is the request from the as a climate community to the AI community who can work together to get these customized models where the denoising part works better for the AI models. So I think that's all. This is the, I think these are general slides. So thank you.
Thank you, Dr. Chattopadhyay. We have time for some questions.
So, what is physics informed thing in El Nino?
So, for example, in El Nino, when we are talking El Nino, it is the temperature over the Pacific, whether it is increasing or decreasing. So, there are different physical process which brings those warm water in the Pacific, because normally if you see the normal condition and the warm phase and the cold phase, which is La Nina, these are dependent on physical process. So one process is how the warm water is coming from the subsurface and it is creating so because of the some patterns of sea surface climatological patterns, those patterns are at a neutral stage. Now they due to some perturbations like wind and other things, those systems change from one state to another state. So if we have to create a better model, these type of things has to be captured. Number one is this, number two is the nonlinear advective terms which are actually creating lot of, so it is a multi-scale problem. Those have a advective terms or some process have 1 to 7 days or 10 days, whereas we are looking at a system into say for example 5 years oscillations. So it is a gradual talking of the scales. So to isolate the noise from different scales to this thing, so we need a better physics informed system so as to get the phase reversals as well as the extremes of the phase better. So this is what we tried to see. Hypothesis of the 1980s were given first, so this we tested using this CNN based model.
Any other questions? Okay, we'd like to thank Dr. Chattopadhyay for that wonderful talk. And on behalf of the summit.
Thank you. Thank you, madam.
Thank you. So now from seasonal prediction, we turn to the global challenges for climate accountability. Our next speaker is Dr. Kamal Das from IBM Research. Dr. Das works at the cutting edge of geo-AI and climate action, developing methods to track and analyze carbon emissions with the precision. His research focuses on harnessing AI and geospatial data to enable real-time accountability at scale, a step towards addressing global climate challenges. In this talk, Dr. Kamal Das will share how advanced AI techniques can transform the way we monitor emissions and empower climate solutions.
Good afternoon everyone, and thanks a lot for this opportunity. And I came here as a speaker as opposed to I was a student here 15 years back. So this work is one of this early stage work, and we want to share some of the early results with this extreme knowledgeable community here. So this work I actually translate into a form to presentations where starts with literature survey, and then what are the existing arts there and what we can do, and what are the differentiating factors we are bringing in this solution. So this kind of typical presentations what we see in the academia. So if I go to next slides. How do I go? Okay, great. So it works. Yeah, so I think climate change, when we talk about, right, most of the things we see as this kind of chart, right, where yeah. So this is a typical chart to explain how the carbon dioxide is depositing in the atmosphere, right. This is kind of mean across the globe. So sort of saying that we are going towards the directions, and each and every year there will be some sort of 2.5 ppm. I mean ppm means parts per million CO2 particle is basically accumulating in the atmosphere. And typical behavior of carbon dioxide is that once it comes to the atmosphere, it almost remains forever, right. So that's the major cause of all of this frequent climate crisis we have been observing. And of course there are various agencies, they try to give, I mean government agencies try to give incentive to if you are doing some reductions of this kind of carbon emissions, but the systems needs to be placed to measure that how much emissions you are producing or how much emissions you are basically shrinking, right. That system is not pretty much there as of now. So some of the basically problem is in the western south is that we do not have a good system to measure all of these sources where the emissions are coming from, right. Even if you do have some of these existing solutions which take care of or let's say measure all of these details, but they are fewer latency. So if you see some of this inventories data comes, right, like EDGAR, ODX, right, they are available 3 years from the real time. So by the time some of the emissions come from these sources, it is almost many years latency. And also the resolution, spatial resolution. So far I will show some of this existing data which shows that the carbon emissions in terms of concentration, not as a flux, flux is the most important one we want to see, are there, but they are in a 100 of kilometers resolution, right. Maybe you have one data points in a one state, something like that resolution exists. So how we can basically address those issues through AI and also the observations, existing observations. Yeah, so this is a typical chart of state of art. So there are these two approaches. Let us start with the bottom up approach. For example, if we have a well established systems to collect the data, you have different sources which are producing emissions, right. You have their emission rate or let's say activity durations, and you just multiply them and then you get each sources how much emissions are there. So this is a purely bottom up approach, and you aggregate through a nations and you get the quantity for particular year how much emissions is produces by India or some country, right. and where there is another systems exist which is called top down approach. So, top down approach starts with, let us say you have a measurements, atmospheric concentration measurements, and then from there you can convert them into the flux, right, and this conversions happens through various model, and one of the traditional model is called inverse modeling. I will try to explain that, and then there is a truncated version of that is called mass balance, and recently there are this branch of data driven approach coming up which are trying to solve the same problem, which basically very high intensity of computing resource required, but through AI they are able to solve in a very relatively low compute resource scenarios, and there are some excellent works are happening across the globe. Yeah, so I guess before going into more details, our approach is the top down one. So, we will start with the observations which are there. So, when we say observation, then there are list of satellite which are designed particularly for capturing the GHG gases, right. So, so you see this timeline, I think most of these recent satellites are going to come in a year or two, they are going to be in the kilometer scale, but still not there. So, the satellite which are there are basically particularly two for OCO2 and OCO3, these are the two typical sensor from NASA. They used to produce carbon dioxide concentration in the atmosphere at a 1.5 kilometer square grid and every 15 or 16 days frequency. And there are issues of also this data because of the cloud condition, all these data are not clean, but after filtering through all this filter you may get 10 or 20% valid data points from this satellite. So, coming back to the state of art again little bit explaining those three approach. So, one of this is inverse modeling, basically we start with the concentration which are measured by satellite, we can call it results, right, and basically then we try to model this process, the atmospheric dynamic process, right, all this transportation dispersion continuously happening, and then we come to the flux. Flux means the how much kgs of carbon dioxide produced by some particular source and some time durations, right. So, that is the typical process, and this modeling approach, inverse modeling approach has to be applied in a global sense and similar to climate model, and there the limitation is that you cannot go up to resolutions what we want. And then there is a truncated version of such approaches called mass balance. I just gave a simple equations where you can think of that, hey, I have a CO2 concentration, right, and if I use this expressions where V is my wind conditions and L can be some of the characteristic length of the locations where I want to find. So, can I convert this complex inverse process to the simplified one? Of course, you can do, but then it is also very specifically for some hotspot locations like power plants, super emitter. This kind of approach is applicable for super emitter. And the third approach is data driven. I think one of these classic examples comes from one of the missions from European Space Agency. They are going to launch another satellite called CO2M. So, they release some data along with the data driven approach. So, they have simulated carbon dioxide concentrations and they use the weather data and some of this supervised learning technique. They want to show that this is a feasible approach to compute the CO2 emission flux in a super emitter like power plants. So, we have enhanced that solutions with let us say satellite observation, real satellite observations, and this work we have presented in NeurIPS last year. And going back to our objectives, so we actually before generalizing this to other regions, we chose the regions where more or less everything is source, like Saudi Arabia, right. There are not much vegetation, the entire country is basically producing or burning lot of fossil fuels, and we do have support from Saudi Authority of Data and AI. They provided us some of the ground truth data to validate such solutions. So, we start with that country. So, we have a satellite observations. What we want to map across the country is that CO2 emission rate. Let us say how much kgs of CO2 per pixel is coming from per week. So, we actually started from there, and if I show that what exists so far today, right. So, one of the closest form of solution exists is basically the NASA's GEOS L3 CO2 concentration map, which provides daily CO2 concentration map at a resolution of 55 kilometer by I guess 68 kilometers, very coarse, right. and this is daily and 1 year latency. So, data you will get from 1 year back for 2 days, right. And we do only get the CO2 concentration, not the flux, which is most important factor for any decision making or climate actions planning point of view. Where we develop our solutions, which is basically 1 kilometer square grid. Every day we provide this CO2 concentrations, and latency is only few days, maximum a week. And in terms of concentration, we also provide the flux, which is basically the need for these hours, right. How we do that? So, that part I will try to explain. So, there are 3 major technical challenges. So, first challenge is basically when we look into the existing satellite observations. So, this is entire Saudi Arabia, I am just showing some strap. So, we basically let us say any given day we have around thousands data points from the satellite, but if we want to cover across the nations, we need around 2 million data points in a 1 kilometer grid. So, that is the scarcity of the data, right, from the satellite. So, first challenge is that we have to fill those data, whatever we are getting from satellite and remaining void places, you have to fill those data. Even if we fill that, the second challenge will be like CO2 is basically we are adding very delta amounts each and every day from different sources, right. So, think about current ppm value of CO2 in Kharagpur may be around 420 ppm, and let us say some power plant in nearby regions may add delta amount 0.001% of it, right. So, that is the delta part we want to decompose from the super background values. So, it is like how we can decompose that part, the delta part, which is due to the anthropogenic activity happening in the surface areas. So, even if we do solve this second challenge, and then the third challenge remains is that the constant dispersion and the transportation happening on the surface areas, right. How we can process this convert this the concentration to flux. So, these are the 3 technical challenges, and we will try to give very high level overview of the diagrams. So, this is kind of system diagrams where you take different satellite observations along with the CO2 satellite observations. We also take proxy data from other satellite sources, which are like Sentinel-5P that gives a lot of trace gases like NO2. So, if there is a fossil fuel burning, CO2 will produce, and along with that NO2 will also be produced, right. So, those kind of proxy data we use, and also some of the commercial satellite like methane set data is also we acquired. And then weather, of course, we use weather data. We need one of this hyperscaler weather data in the resolution scale. So, we use the source from TWC, they provide around 3 kilometer resolution weather data. And there are some other activity in the anthropogenic sense is like population dynamics, and also nighttime light, how they are changing on each and every pixels. So, through series of AI models. So, first model is basically filling those satellite void, the satellite missing data from the satellite, right, and that is one model. So, once we done that part, the second part is the challenge 2 is like discard this huge background value and only take this small quantity which is produced by some sources, right. So, that the decomposition part, there are several block of it, and it goes into the final part, which basically converting that small delta part of the concentration to flux through a geospatial foundation model. Here we use Prithivi. So, Prithivi is our own model, I am also one of the contributor in that model. Yeah. So, first model is of course filling this void values. So, there we take a lot of this weather data to learn or understand how this concentration dynamics happen across the country, right. So, this leads to a accuracy around let us say ppm of 0.5 RMSE, and this is kind of same order of accuracy of sensor noise. So, this is a problem, right. We need to go further reduce that accuracy. So far we are not able to go beyond 0.5 RMSE ppm values, right. Of course, we try to show this in different regions, and one of the critical work has been done in US regions where we do have a sensor measurements at various points, and of course we reported that numbers, and there we basically got little better than this. The reason being we have very fine resolution weather data along with other proxy data in US region. So, data scarcity region, this can be one of the problem of further enhancing this resolution accuracy. Yeah, the second part is a bit of busy chart, but the goal is to basically you have concentration, we want to decompose into two parts. One is the huge value of background and one is the delta part, which is due to the anthropogenetic activity. How we do that? So we take this satellite observation from Sentinel-5P NO2. So we basically NO2 has a very sharp background versus foreground. Whenever there is a let us say car is going through a road, you can specifically see there is a plume in the NO2 values, but you can't see that in the CO2, right. So you use that NO2 along with the CO2 values and try to learn a segmentation model, a simple segmentation model, say binary kind of task. Okay, I will try to finish in 5 minutes. So that is one of this map. Okay, we now know each of these pixels, whether this pixel is producing emissions or not. So that's simple binary task. And now on each of these binary pixels, wherever there is a emission is coming, we learn some sort of relations between NO2 and XCO2 and kind of get this delta XCO2 part as a map. So now that is the map we produce at a daily and weekly frequency, and that is our final output, which will go for converting into this to flux, I mean the emission rate. So how we do that? So we can do of course full-fledged physics based approach, but what we have adopted here, the 2 slide previous, yeah, here please. So what we do basically in terms of things we know is basically delta XCO2, that the contribution from local sources of emissions, and some of the points we know the annual emissions. What we do not know this let us say scale factor, right, or this CF in this particular equations. So this is just for showing, but how actually we do, basically we take a encoder or decoder based transformer based geospatial foundation model, and we basically pass through lot of this other source of multispectral satellite observation as a input features, and we put this condition as a loss function and we do as a fine tuning task, and we basically produce weekly CO2 emission map across the country. So this is just one validation chart across the country. So there are different 3 sources are there, and one of our sources we show, and they are pretty much matched. But one thing is different between other 3 sources is that you have only single number for one country, whereas our solution has every pixels of 1 kilometer resolution weekly basis, right. That's the difference. And the acid test, I mean one of the critical tests we did is basically for electricity industry, for power plant. There are 71 power plant in Saudi Arabia. We have specifically each power plants we have they have shared the data with us, and we put this as a reference axis X and our estimation in Y. There are some match and there are some overestimation from our model, and reason being that our model is producing 1 kilometer resolution get one single emission data, right. So there are city like Al Jubail, which is the highest petrochemical city in the world, largest petrochemical city in the world. So there within 1 pixel there are multiple things are there, not only power plants, there are multiple other sources of emissions coming from. So that is why there are some overestimation from our model, otherwise it has been a good match. So this is a kind of ongoing work. What we want to pose this as a problem as a foundation model, and we want to publish this as open source in pretty soon as a something called GHG foundation model or PTB GHG foundation model. And of course we are also expanding this for Indian regions, and some of our collaborator is basically, next slide please. Yeah. These are IBM team, and of course Professor Hendrik is part of IBM team, was part of IBM team, and Professor Kevin is basically distinguished researcher in this GHG space. So many of this inventory data comes from his team, and he is also collaborating with us on this work. Yeah, I will stop here for questions.
So thank you, Dr. Shorish, for this very important work and very influential work. We have time for only a small quick question.
Hello. I have one just question that in the last slide you are having 1.1 kilometer that range and some other you are having 1 kilometer. In other slide you are having something 55 kilometer that precision whatever you call. Why this number is not regular? Is there any reason for that?
Sir, the 55 kilometer resolution is the reference work from NASA. They have a product called GEOS L3 CO2 concentration product, that is to show that state of art versus ours. So, our work is on 1 kilometer square grid consistently across concentration as well as for the emission rate. The one I referred is the NASA solution, which is a reference work, which is very coarse 55 kilometer by 78 kilometer, sorry 68 kilometer.
Okay, thank you very much.
Quick question please.
Oh, sorry.
Quick.
So, this emission from the CO2 plant, is that there is variation, huh? Daily variation, seasonal variation?
Yes sir, absolutely. We have hourly, this solution is not hourly, this is weekly, because we want to cover across the nation. So, one of the solutions we presented last year in Nurif's workshop is that we can produce or we can estimate the fluctuation of power plants emissions hourly basis, that is the separate work, but that is use only the data driven approach. We need to have the data. If we have hourly variations data which can support that kind of conversion, that is possible. But since the data does not support, that is why we, even if we have a concentration at a daily level, but we convert the emission rate at weekly basis, because the data is not there to support in the daily scale. In future this can be translated into daily or hourly.
Take it up.
Yeah, thank you.
So let us thank Dr. Kamal Das for this talk, and on behalf of the conference we have a small hand.
Thanks. Thank you.
So from global emissions, we now turn to the operational front lines of metrology. Their forecasts meet real lives, and we are most familiar to as lay people. Our next speaker, Dr. Shorish Bandopadhyay from the Regional Meteorology Center, Kolkata, works at the interface of weather services and decision making in the age of AI. With deep experience in operational metrology with the IMD, he understands firsthand what it means to deliver timely, reliable forecasts, whether for cyclone warnings, aviation, or daily public advisories. In this talk, he'll share the services provided by RMC Kolkata and explore how AI ML can strengthen operational forecasting and service delivery. So please welcome Dr. Shorish Bandopadhyay.
So, good afternoon, respected delegates, all respected members, and of course, the young mind present here. It is a great opportunity for me to be present here with this brilliant audience and experts and eminent scientists present here. So, Professor B.N. Goswami has already said in his lecture that the second revolution in weather forecasting, we missed the first one and we do not want to miss this one, sir. So, we are working as operational forecaster in Regional Meteorological Center, Kolkata. This is the regional headquarters of Eastern India. Our main headquarters is at Delhi. Our area of responsibility is mainly Eastern India, and primary focus has been over West Bengal and all the districts of West Bengal, all locations. So, who are the stakeholders of services of IMD? Who needs the forecast? In nowadays, we find that almost everyone needs somehow. It affects directly or indirectly starting from farmers, which are the most vulnerable sectors. India is a agricultural based economy, and West Bengal also. West Bengal is rich in economy, agriculture. Lot of farmers are present here, and the fields, farm, we cannot protect from the sky, from the weather related hazards. That is why they are the most vulnerable sectors. It is open to the sky and exposed to all the kinds of hazards, weather related hazards. Aviation is very dangerous one for the pilots. We may not bother about the weather when we are sitting in an aeroplane, but the pilots, they are very much concerned because they find it dangerous if they find themselves stuck in a turbulence. They can crash the aircraft. Larger aircraft can survive, they can manage easily, but when the lighter aircrafts or like helicopters, they are more in risk category. That will be very difficult for them to survive if they are caught in intense turbulence like thing, particularly during the takeoff and landing time. So, all aviation purposes, no flight can take off landing possible without meteorological clearance. Same is needed for the VVIP forecast also, like Prime Minister visit, that is very sensitive. Chief Minister visit, all these things, because they are often travel in smaller aircrafts or helicopters, which are very sensitive to the meteorological information. Also all other things like power sectors, whether it is economically useful information. The power suppliers like state electricity department, CESC, they find it very useful from their business point of view. How much amount of power they needed in their grid, that is very much related to weather related hazard. Like for example, say in the month of May, you may have a heat wave like condition. Suddenly in the afternoon there may be a strong nor'easter with intense precipitation. That will immediately reduce the temperature. The power supply requirement will go down drastically. So, their power management for the electricity suppliers is very much related to weather related hazards. They are very much concerned from their business point of view. It is economic highly. Our tourism also, for example, say you want to visit to Uttarakhand in the month of August or September. One would like to check what is the prevailing weather there, because it is a landslide prone area. If you are stuck there, then it is very difficult to escape from that. So, information of weather is also very important for tourism purposes. People find it business point of view also. Nowadays, we also get call from the cricket board also. So, suppose there is an IPL match, whether it is possible to conduct today, sometimes we get such kind of calls like that, whether we need to shift the IPL to another day, because it is a big lot of amount of money is involved in such kind of situation. A play in an open field, if some rainfall activity or intense thunderstorm activity takes place, that will spoil the entire arrangement. So, they are very much concerned. So, almost everyone is somehow directly or indirectly related to it. So, different range of forecast that we have been providing, starting from climate prediction, which is a longer lead time. Long range forecast from month to season, for example, monsoon forecast. Who are concerned about monsoon forecast? Farmers, because of their agricultural activity. Policy makers, because India's GDP is very much connected to that. So, policy makers, they are very much concerned about those things. As a common people, who are not farmer or directly not related to that, they may not bother about such kind of long range forecast. Extended range forecast is up to 1 month we can provide, but accuracy will be less as we go to longer lead time. Then we have medium range forecast up to 10 days, short range up to 3 days, and nowcasting up to few hours. Why we need nowcasting when we have already 10 days forecast? This is because when we are issuing a 10 days forecast, it is very difficult to pinpoint whether there will be thunderstorm activity over Kharagpur in the month of May at 4 p.m. That pinpoint forecast is still very challenging in spatial and temporal scale. We are issuing forecast, we are issuing warning up to 7 days at present operationally that thunderstorm northwest severe episode can happen over a location, but that for a 24 hours period, not exactly at which location and what time. We are at present using it at district level. For example, West Midnapur we have issued a warning with 7 days lead time, and that is also happening also, but at what time it will happen, that we cover in nowcast scale. Where AI ML can play here? In all this category, AI ML can boost the forecasting activities, particularly when we talk about nowcasting, few hours lead time. During this period actually, we have several numerical weather prediction models, but the models actually struggle very much during this short lead time. Because of this noise to settle down, it takes much time to settle down. Initial hours after the model, they are very much actually perturbed by the noisy situation. In medium range also, in all kind of situation, AI ML can play a big role, particularly AI for automation purposes in our weather forecasting, that we have been already utilizing it for many purposes, for automated bulletin generation, automated dissemination to stakeholders. These are the various weather hazards that we face: cyclone, heavy rainfall, hailstorm, thunderstorm, lightning, etc. All can be very fatal. Cyclone, we have seen that in recent times loss of life has been minimized, less than 100 in all cases. Even 0 casualties has been reported in recent times in various cyclones over our regions. In all cases, machine learning, deep learning model can play a big role here. It can make more precise. Already cyclone forecasting has improved, but to make it more precise, machine learning is not what we are proposing, that it is not going to replace the basic fundamental models. What it needs for forecasting? Fast monitoring system is needed. Monitoring, we have satellite, ground based observation, upper air observation, everything is needed. These are various observation networks that I am skipping, from surface, automatic weather station, manual station. Manual stations are still needed. We are not going to say that it is obsolete, because automated sensors has their own limitation. Everything comes with their own merit and demerit. These are typical automated our continuous data taking stations. This is the vertical profile typical example of RSRW observation. Surface observation is not enough, it is a 3-dimensional system. I am skipping all those. So, how forecast is generated? Observation taken from various sources, satellite, surface, ground. Then numerical weather prediction models. Large number of models we have been using at IMD. At IMD model, international model, ECMWF models, NCM models, all these things we are taking into account. And finally, it is not enough, only models are not enough. We have large number of checkpoints also, which model to go with. we have checkpoint based on surface observation, vertical observation and other derived parameters also. As our Goswami sir, Professor Goswami highlighted that rainfall prediction model does not capture well, but we have the parameters that can capture if we use machine learning, deep learning. Parameters are well predicted, so we can use bias correction and other things which can interpolate and extrapolate the things based on the parameters. That can be very useful information using machine learning. These are Doppler weather radar images which are very much effective for current condition monitoring. It will give precise estimate of current convection, its height, intensity, but it is not a forecasting tool. It is more a monitoring tool for nowcasting purposes. It will give the exact severity, but when the system has already developed, that time only. For example, if we have a such severe convection, severe lightning associated with such system, 3 to 4 hours prior to that, we may not have any signature either in radar or satellite. We may have a clear sky at 12 in the noon and a severe convective system at 4 p.m. So, we can monitor it. For example, this is a satellite image. If we go on only image processing, what will be the rain rate? Satellite is taking observation from the top. It is not, it is seeing the only head, not the bottom. So, it may not capture everything. But we can use it various parameters, derived things and combine this together to have better machine learning, deep learning models. These are vulnerability maps of our different regions. This is a track of cyclone Rimal. This is what I was saying, that various NWP models. You can see that large number of models are there. Difference among them, which one to go with. Here machine learning, deep learning can play a big role. At present we are using MME, but that still there is scope of improvement. Which one to go, based on various checkpoints we can apply more here. We are already applying a lot of checkpoints, but still there is a lot of scope for improvement here. These are accuracies I am saving it. What NWP models are actually taking into account various basic fundamentals equation actually taking. So, that is why the data based AI, ML, deep learning is not going to fully replace NWP models in at least in in near future, because they are based on solid fundamental principle of conservation of momentum, conservation of energy, mass and so on things. All these things are incorporated actually, observation, forecasting incorporated in our decision support system, and I am skipping all these services from dissemination. This is what actually experimentally we have been utilizing machine learning, deep learning models, AI for automation, for speedy dissemination, speedy decision making. Machine learning models we have at least at the experimental stage we are now. We are not in an operational position at present. Our operational accuracy for various severe hazards are 80 to 90% accurate, along with a detection probability. POD is important here. For example, if we predict heavy rainfall over Kharagpur, 365 days, total number of events of heavy rainfall over Kharagpur will be on an average 5 days in a year. So, if we say every day there will be heavy rainfall over Kharagpur and none of them is realized, even in that case percentage correct will be 99%. So, percentage correct is incomplete information. Our priority remains over the detection probability, which over the severe weather hazards which can cause most damage. At present our machine learning models, deep learning models have accuracy of 70% around the POD and percentage correct, and we are working on it to improve, match our operational forecast and finally beat our operational forecast. Thank you.
So, let us thank Dr. Shorish for the talk. So, I invite any questions from the audience.
Thank you. Thank you for the talk. So if someone wants to apply say machine learning, deep learning models on these data, do you provide these data publicly, or from where can one obtain say large scale data?
You wanted data?
Yeah.
Yes, from our national data center NDC, you can, there is open platform, you can apply there for weather related data. Also what kind of data you are asking for, that depends on various open source data are also there, like satellite data, model data, various open sources you can also consider. Official data are actually from national data center, it is available there.
But are they available publicly, or like one needs to apply?
You have to apply it. You have to apply. Some open sources data they are available publicly, like ECMWF data, ERA5 data, some satellite data, that you have to log in and apply it for it.
Okay, thank you.
Okay, any other questions? So let us thank again Dr. Shorish and present a small memento. Oh, okay, Avdar.
Yeah. Thank you for the talk. So I was just asking, like, is it like, do you collect rainfall data from maybe smaller regions of Kolkata, like maybe ward-wise or something, and is it possible to share
yes,
that data?
we are collecting data. At present our officially observatories are 3, but we have state rain gauge network that is very much dense over Kolkata. It is more than 20 or around 30 stations are there from the state department. Over Kolkata and surrounding we have a very dense network. At IMD we do not have, but from the state we can get those data. We have access to that actually. But for the other regions outside Kolkata, the network is not that much dense. For that we have to use other sources like satellite based product, radar based product, and interpolation, those things. We have graded rainfall also. That is IMD graded rainfall at.
That we are, most of us, many of us are familiar with already. Thank you.
So we'll like to present a small memento on behalf of the workshop. Thank you, Dr. Shorish. So finally, we turn to one of the most pressing challenges at the climate AI interface, that is urban flood resilience. Our next speaker is Dr. Divya Upadhyay from AI Rescue. Her work brings together climate science, data-driven methods, and AI-powered decision systems to help cities better prepare for and respond to extreme weather events. In her talk, Dr. Divya will explore how integrated AI-enabled approaches can support early warning, real-time response, and long-term urban resilience in a changing climate. Please join me in welcoming Dr. Divya.
Yeah. Good afternoon, everyone, and thank you for giving me this opportunity to represent my company, that is AI Rescue Climate Souls Private Limited. This is nothing but from starting of the day we are talking about that, from lab to the operational things. So this is the startup that is born out of the research work done at the IIT Gandhinagar, and sorry. Yeah. Yeah. So basically, we all are aware about the fact that flood is not a rare event anymore. It is the every monsoon we are facing this type of situation, and it's not the situation for only one particular city. Every city, major cities are facing this type of things. So I'll not go much into detail about the statistics. Everyone is aware about this. It's very well known problem. I'll directly go in consideration of the time. So what is the problem, main problem, and when we are talking about the operationalizing or handling flooding issue for particular cities. So mainly it is nothing but the how we are handling this type of situation on the ground. We don't have proper solutions or models to represent the city as a whole, and considering all the aspects that rainfall, how we are translating rainfall to the flooding event, for considering all the aspects of the particular cities. So I will explain that how we are considering different aspects and modeling the flood and translating rainfall to the flood event. And this flood is not the waterlogging problem anymore. It is translating to different networks also. So if you see these pictures, so this is the picture that if waterlogging is there, and if you need any emergency services systems and roads are blocked, you are no longer available, that roads are not available for the patients to transport from one location to another location. Similarly, we face this situation of road blocking, and this event, this is the scenario that we observed, that Central Crime Branch, they have shifted their office from one location to another location in the Bangalore, and where the water logging problem is there. And when they have shifted their office, just next monsoon they have faced the water logging situation, and many of their documents they have to lose that. Now the situation is like we are finding our solution at different wrong locations. So what we are mainly talking that where to search, what is the waterlogging roads, these are important aspects, I am not denying it, but we have to take this aspect also for the water modeling, that our drainage systems, whether it is equipped for taking that particular load, rainfall is coming, considering the fact that water is coming to the land, we have to make the way from, and we have to transport that water from one location to another location, so that the critical locations are safeguarded from the flooding situations. Then these are the different types of models which are already available. We all are aware about it. That first is data driven models are there. So data driven models, they are considering the different data sets. As we are saying that climate data, they are rich, and we can use that type of data set, but we have to consider the fact what are the positive. So it has a better predictability, but physical loss they are not considering most of the time. Some conceptual models are also available. Some long research has been done for the hydrological modeling from the decades. But we have to consider that these conceptual models, they are very good in representing different physical processes, but they are typically designed for the regional data set. So we cannot apply the same model from one location to another location. And if you consider third category, that is physics based models, they are considering different physics laws, but large data requirement is there. So we need to come up with the solution which will consider the positives and negatives of both the worlds, and that's why we have created the physics informed machine learning models. As most of the talk they have also mentioned that we have to consider different physical laws, conservation of mass, conservation of momentum, as well as we need to consider the advantage of the big data set that is available. But considering the fact that the data set, what is the quality of the data set, that also we need to mention when we are developing our models. So we have developed the rain to resilience suite, that is from the rain how we can provide the system and we can provide the decision support system. So we have developed this physics guided machine learning model, and which will provide the dynamical models with the time, what is the flooding area is there, and what is the depth of the water in different areas, and which we superimpose these particular maps on different critical infrastructures. We can quantify that what is the damage for different systems, and if we can quantify different damage for different networks, we can formalize different recovery strategies for the resilient infrastructures, and we can provide the decision support system so that we can visualize that for different what if scenarios how our system will perform. So this is how we are putting different layers into our models. So we consider different buildings, roads, rainfall networks, land use, land cover, digital elevation models, drainage network, different boundary conditions into that. Physics and our AI models which provide the different flood maps for different time intervals, and considering our input for the flood map and considering the road map, we have developed different network, considering different network algorithm. We have simulated the network traffic simulations, and we have developed one product that is Mobi Rescue. In this particular product, we have to select origin and destination, and we can identify what is the shortest path, and if flooding is occurring, how rerouting should be there for particular city. So here question comes that where AI comes into picture. So earlier, as we know that this hydrological modeling has been done in many decades, but this process, whole simulation takes months of the time. When AI comes into picture, it can reduce the time from months to the hours, or maybe in days, maybe in seconds. Sorry. So these are lightweight dashboards, and in this particular dashboards, if we can reduce the time of the simulation, we can simulate various what if scenario, and we can identify which strategies will work for different cities, and how much return on investment will be there for different strategies. For example, if we are including major road networks, drainage lines, then is it useful for our city, whether it is option 1 is useful, or whether it is option 2 is useful. And from this model, what kind of questions that we can answer, that which road is blocked and how much time is available, that if you know priorly that in 1 day, 6 hours in advance that this road is going to block, then we can take proper measures. We can put pumps, we can extract that water, pump out that water from that location prior in advance. So here this is one aspect. Another aspect is if we are having rainfall data, continuous rainfall data, we feed that data into our model, and we can get the estimation, flood estimation in near real time. So this is full rain to resilience suite. So we have our input data set. We feed that into our physics guided AI engine, and we can also estimate that I have already explained all these things, and these are the 3 products that we have developed in our dashboard. So quickly I will go, and just to visualize that whatever flooding data is there, to visualize that how flood will look like. Yeah. How flood will look like, we have also developed digital twin of the that, so that we can actually visualize that how water will be propagating and into different cities. So this is our core team, that foundational team for AI Rescue Climb Source, Professor Udit Bhatia, Professor Vivek Kapadia, I, and Professor Arup Gangoli. So this is our industry and research community partners, and this is the team that we are working on developing these models. Thank you. Now I would like to take opportunity to play one video for our dashboard and for my company. So please.
Every year, floods disrupt millions of lives, families stranded, emergency services. Every year, floods disrupt millions of lives, families stranded, emergency services delayed, businesses shut down. A single storm can drain millions from a city's economy and bring entire regions to a standstill. Despite billions invested in defenses, what cities and companies still lack is resilience and foresight, the ability to know which neighborhoods will flood, which roads will close, which hospitals will be cut off, and how fast recovery will take. That is why we built AI Rescue ClimeSolves, a deep tech startup born from world-class research at IIT Gandhinagar and collaborations worldwide. Our mission is not just to predict floods, but to turn rainfall into resilience for cities, communities, and markets, all in real time with a hyper-local focus. Our physics-guided AI emulators transform rainfall into street-level forecasts of flood depth, duration, and cascading impacts. We go beyond hazard maps, delivering decision intelligence, which assets are at risk, what the economic cost of inaction would be, and which resilience measures deliver the highest return. For cities, this means continuity of mobility, power, and communications. For the private sector, insurers, reinsurers, and investors, it means sharper underwriting, validated claims, portfolio stress testing, and credible resilience data that protects credit ratings and unlocks capital. Flood resilience is one of the defining challenges of our century. With AI Rescue, we combine science, technology, and vision into actionable solutions. We are already working with leading institutions and innovators to prove that together, we can turn climate risks into lasting resilience.
Thank you. And I would like to, I just need 2 minutes. I would like to take the opportunity to showcase our dashboard that we have developed at our company. Yeah, I'll just. And another thing I want to make an announcement that we have developed one ARC center under one project of AI COE, which enables that different data set, that is ARC center at Research Park of IIT Gandhinagar. So that will be inaugurated in next week. And I'll just take a quick look. So this is how our dashboard look like. So these are the different verticals that we can see. That first one is flood archive. So once we have two different models. One is simulator and one is emulator. So simulators which will simulate only physical processes which take a longer time, and which we and using AI we have converted that and we have developed our own emulator which also considers the physical aspect. So that is nothing but physics informed machine learning models. So it will provide the data output in terms of that how much area is flooded, what will be the depth of the water at different time steps. And as it is doing processes very fast, we can simulate different what if scenarios also, and we can identify what are the different hotspots, and we can superimpose different layers also just to visualize that how different layers will look like for a particular city. Yeah, you can do fast forward. And this is one of the product that I was talking about, that how we can consider this flooding aspect and how we can correlate it with the transportation network. So if we are superimposing transportation network, so we can select origin and destination from, and this is the data that I am showing, and we have done proof of concept for Gurugram city. So these are the actual result of Gurugram cities that we have taken from the municipal Gurugram Municipal Corporation, and we have implemented in our model, and these are the actual results from that particular city. So we can identify, and here real time traffic data is also shown. Yeah. With the interest of time, I would like to stop and
Yeah,
thank you.
I'm sorry to stop Dr. Upadhyay's enthusiastic presentation, but she is available and you can discuss with her. Any quick questions?
Yeah.
Yeah, thank you, Dr. Divya, for the nice talk. I just have a couple of questions. Like you told about this 24-hour rainfall forecasts. So where from you get that?
So we have taken global forecast models,
Okay.
and yeah,
GFM.
so that pipeline is under progress.
And what kind of AI models do you use for this inundation simulation?
So
And how do they compare with the standard physical-based models, for example, the SWMM and so on?
So here SWMM model is mainly for the drainage networks and all,
Yeah.
but here we have developed full rain to rain resilience forecast, this physics informed machine learning model. So AI model is our own, which consider different stages are there that I cannot reveal at this point of time, but it considers different physics, conservation
So
of
how
mass
does
and
it
moment.
perform performance-wise?
Performance wise, now we are comparing the performance of our physics informed machine learning model with the physics models, and we are also considering validating. So you are talking about the validation of the model, right? So at this point of time 80% of the points are matching with the simulation points, and we have also considered the satellite image and try to find out that how it is matching. So pattern is recognizable.
Yeah,
So
thank you.
we still need to work on it.
Yeah, thank you very much.
And on the aspect of validation, we are in the stage of deploying our own water depth sensors, because water depth data is not available for any of the cities. So we have to provide, we have to install that water depth sensor. So that work is in progress.
I have a question, Ms. Divya. Here.
Yeah.
So Kosi River changes its route every season. So how will you deal with those kind of floods in which the route is itself changing due to silt deposition?
Yeah, that's a good question, but at this point of time we have considered the land use pattern as a static variable. So once that model is fully ready, then we can convert that into the dynamic variable. Then we will be able to consider the changes in the land use. For example, that whatever you are talking about, that Kosi River is changing its path, right? So we can incorporate that kind of changes once we make that layer as a dynamic layer.
Okay, let's thank Dr. Upadhyay for this good talk, and hope her company is very successful and able to mitigate the challenges faced. So with this, we come to the closing of this session. Thank you all.
Can we have a photo with all the speakers? A group photo?
So can we have
Hello?
a photo with all the speakers before you start?
No, I just have one announcement to make, ma'am. Yeah, so the breakout session starts at 5. So for that, we gather together in front of the registration desk here, and we'll all go together to the second floor of the Takshashila building then for the breakout session. First, we will be all together in the classroom of computer science department in the second floor of the Takshashila building, and then we will go for focus discussion in 3 separate rooms. Thank you. At 4:45. So we gather together in front of the registration desk at 4:45 p.m.
হ্যাঁ এখন পোস্টার আছে